of experience with the Welding Research Institute, which is affiliated to BHEL Tiruchirappalli, and retired from WRI in 2017. His field of specialization is welding simulation using finite element method, prediction and control of distortion and residual stresses, design of static and fatigue loaded welded structures, experimental stress analysis, etc. He obtained a PhD degree from IIT Madras in the year 1996 for his work on the analysis of axis shift distortion and residual stress during circumferential welding of thin-walled pipes. He received the W.H. Hobart Memorial Award from the American Welding Society in the year 1997 for his research paper Prediction of Axis Shift Distortion during Circumferential Welding of Thin Pipes using Finite Element Method. He was a guest faculty for many educational institutes and handled class for both graduate and postgraduate program on welding engineering. After his retirement, he joined NMAM Institute of Technology, PT Karnataka, as an adjunct professor in the Mechanical Engineering Department. With this brief introduction, now I invite Dr. G. Ravichandran, former General Manager, WRI, Belt Ritchie, who is right person to deliver the inaugural address and offer felicitation to this participant online.
Thank you, sir. Thank you very much for your kind words. Respected dignitaries, Dr. Murugappan, Dr. Balasubramanian, other senior faculty members from Annamalai University, and dear participants of the FDP program. It gives me great pleasure to be here for the inauguration of the FDP, AICTE sponsored FDP program on a very important topic, that is simulation of welds and optimization technique. The topic is of great importance and relevance, not only for the academicians, it's also for the industry personnel. The academicians use this tool for getting a deeper understanding of various mechanisms which are associated with welding. You all know welding process is very complex in nature and it involves many phenomena relating to metallurgical, mechanical, electrical, chemical and magnetic phenomena. All of them are acting at the same time. And so to get an understanding of the effects, you have to study these phenomena in detail, then only a detailed understanding can be obtained. Whereas when it comes to industry personnel, they use it for problem solving. So the parameters for a given application is usually has to be selected from an optimum combination of a parameter, and there is a small window associated, and when the heat input parameters are selected on the lower side of this optimum window, there will be issues like fusion related issues and defects, etc. Whereas when the properties are selected on the higher side, then there will be many metallurgical and mechanical after effects like poor microstructure, inferior properties, mechanical properties, distortion, residual stresses, etc., etc. So you have to operate within the optimum parameter combination, and finding this optimum combination through experimental means is going to be very expensive. As rightly said earlier, it is going to be expensive because it involves a lot of material and it is also going to be time consuming. Whereas a simulation tool is the best handy tool for analyzing the various combinations and come with the optimum set. And when it comes to newer materials which are being introduced in the market, then the problem becomes all the more severe because the new materials have a very narrow range of optimum parameters. So you have to be very, very careful, and even if there is a deviation, there is going to be a great effect on the outcome. Final quality of the weld will not be acceptable. The need for modeling and simulation was felt as soon as the process was introduced in shipyards, because in the year 1920s and 30s, the welding process was introduced successfully. It displaced the riveting process and welded ships started getting manufactured. And as soon as the welding was employed, they faced the problem of distortion. And at that time, the knowledge was also much less. And so they had to develop some model to understand and take some corrective steps to overcome the problem of distortion. But unfortunately, they had at their disposal only analytical technique, which comes with many simplifying assumptions. And so they developed analytical come empirical relations for the purpose, but they were successful only for certain applications, whereas it could not be extended for other applications. And the accuracy was also very poor, and we were able to get only the trend, not the exact magnitude. But the scene changed when the computers entered the scene. So the numerical techniques like finite element method, they started becoming popular, and slowly people started using it for newer and newer applications. The main advantage of the numerical methods is that many phenomena can be represented or it can be incorporated in the model accurately, and because of this, the accuracy of the final outcome will be very good. But of course, the cost of running the analysis is going to be there. But with the entry of the powerful computers, this problem was also overcome. And nowadays, with the rise of power of computing, even complex industrial components can be analyzed, and we can get the useful results. But we have to remember a word of caution here. So however advanced a model may be, you can have a most advanced model which is having so many features which are incorporated and all that, but this is not going to be of any use unless there is a validation of this model through some means. And the best means will be the conduct of experimental trials. So you conduct experimental trials on a sample cases and try to match the results and prove the usefulness of the software, and then afterwards it can be taken up for analysis of more advanced cases. So this is one important point to remember. And one more application where the modeling and simulation technique will be of great use is in the analysis of residual life of industrial components. Most of the components are going to be welded components, and so the welds are going to be the weakest part, and they have to be analyzed in detail. And when the components are going to be put into service, they undergo some damage mechanisms right from day one. And so there is going to be a deterioration in the properties of the material, and this is especially true in the case of welds. And some of the mechanisms which are going to be responsible for this damage are the creep, the fatigue phenomena, the corrosion, erosion, etc. Of course, there is going to be an interactive influence as well. And so the designer of the industrial components, normally he takes care of this and then finalizes the design life of a component. But the fixing of the design life is going to be a rather conservative estimate, and very often we find that the components are still useful even at the end of the design life. So at the end of design life, the component may still have some useful life. And so if the component is going to be retired forcibly, it is going to be a huge economic wastage. So definitely a cost of putting up a new component is going to be very high. And so just like that, we cannot retire a active and useful component. But if the component is going to be operated beyond its useful life, there is a risk of catastrophic failure, and it is going to be a very dangerous thing. So the engineer has to take a correct decision. So he has to use the component to the fullest possible extent, but we should stop when the useful life is coming to an end. So for doing this analysis, the simulation packages and their modeling will be of great help. There are many advanced packages which can predict the creep damage, the fatigue crack growth. The crack is propagating and the component can still be used even though the component is having a crack, a growing crack. Since the crack, if it is going to be less than the critical size, then it can be safely operated. Once it reaches the critical size, then it has to be stopped. So this decision can be better taken with the help of a tool. So the topic is of great relevance for industry as well as academics, and I compliment the organizers for coming out with the program on this very important topic. And I went through the topics and I find that the topics are very extensive and they cover almost all the aspects which are required for the people. And the sessions, I'm happy to note that it is handled by both subject experts. academicians as well as the industry experts are going to handle this session. And I hope the participants will make the best use of these sessions. I'm extremely happy to inaugurate the program, and I wish the participants all the very best in future. Thank you.
Thank you, sir. Finally, I invite Dr. K. Srinivasan, Associate Professor, C Major, Department of Manufacturing Engineering, to deliver the vote of thanks.
Thank you, sir. Good morning to all. I am very happy to stand before you to express my heartfelt thanks to all those who involved in the successful conduct of this AICTE-sponsored faculty development program on simulation of weld and optimization techniques SWOT 21 from July 12th to July 16, 2021. I wish to record our sincere thanks to university authorities for permitting us to conduct the FDP program. We sincerely thank our beloved Dean Professor Dr. A. Murugappan, Faculty of Engineering and Technology, for delivering presidential address in this program. We sincerely thank our beloved Head of the Department and Director, Center for Material Joining and Research, Professor Dr. V. Balasubramanian, for delivering welcome address in this FDP program. We wish to express our gratitude and heartfelt thanks to Dr. G. Ravichandran, former General Manager, Welding Research Institute, Bharat Heavy Electrical Limited, Trichy, for readily accepting our invitation to inaugurate this FDP program and to deliver the inaugural address. I thank all the participants attending through online and offline from various parts of this country for their overwhelming support and response. I thank the professors, Dr. Ravi Shankar sir, Ravi sir, Sanmu sir, and other professors, the hosts, so they are attending through online for their gracious presence and making this inaugural function as a memorable one. I wish to thank all the speakers. They are going to present their lectures in the program for the next 5 days. Finally, I wish to place my heartfelt thanks to the various committee members, research scholars, supporting staffs, students, friends from the Department of Manufacturing Engineering for their tireless effort and hard work, which helped us to organize this FDP program in a successful manner. So thank you one and all behind this successful event, and thanks a lot.
Thank you, sir. Thank you all for joining this inaugural function. Please stay online for the first lecture by Dr. V. Balasubramanian, Professor and Head, Department of Manufacturing Engineering, which will commence shortly.
Good morning to all and welcome to today's session. It's a great honor for me to introduce today's presenter, Dr. V. Balasubramanian sir. Dr. V. Balasubramanian is working currently as Professor and Head Department of Manufacturing Engineering and Director, Center for Materials Joining Research, Annamalai University, Annamalai Nagar. He is graduated in Mechanical Engineering from Government College of Engineering, Salem, University of Madras in 1989 and obtained his post-graduation in Production Engineering from College of Engineering, Gindi, Anna University, Chennai in 1992. He obtained his PhD in Welding Engineering from Indian Institute of Technology, Madras, Chennai in 2000. He has 27 years of teaching experience and 22 years of research experience. He has published more than 400 papers in Scopus Index journals, and his current H index is 50. He has supervised 25 PhD scholars and guiding 6 more scholars. He has completed 30 R&D projects worth of 15 crores from various funding agencies. His areas of research interest are materials joining, surface engineering, and nanomaterials. He has visited countries like Singapore, Hong Kong, Canada, and USA for paper presentations. He was a member of Academic Council and member of Senate in Annamalai University. He is currently Board of Studies member for Mechanical Engineering, Anna University, Chennai, and Annamalai University. He received a Young Scientist Research Award from Department of Science and Technology, Government of India in 2003, and Young Engineer Research Award from Department of Atomic Energy, Government of India in 2004. He received a Distinguished Researcher Award from Annamalai University in 2005 and Professor Placid Rodriguez Memorial Lecture Award from Indian Institute of Welding in 2010 and Professor Dr. G. Achar Distinguished Academician Award from Indian Welding Society in 2013. He is a life member of ISTE, IAW, IWS, and IE. So from this introduction, let me invite Dr. V. Balasubramanian sir to take over the session.
Okay. Yeah, thank you for nice introduction. Once again, good morning to all. I welcome you all for this FDP program. The first lecture is Dr. Rajkumar, the coordinator, asked me to introduce the welding processes and also to describe about the importance of simulation and optimization techniques. So my lecture is because the first lecture, there are mixed participants from the younger generation to the experienced people. So I want to give basics, fundamentals, then I'll give some of the advanced processes also. So this understanding these processes will help you for the next lectures, one of the forthcoming lectures delivered by various speakers. So I hope that the participants will enjoy this introduction to advanced welding processes and need for simulation and optimization. So I have planned my lecture in this sequence. First, I will touch upon the fusion welding processes. Then I will give brief about solid-state welding processes because these two processes are dominating the materials joining field. And then I will spend a few minutes on the need for simulation and optimization because the remaining remaining lectures will be focused on simulation and optimization. So I don't want to touch upon that in depth. Anyway, I'll just give you a brief intro about the requirements of the simulation and optimization. Then about our center and department and university. That's a few slides only. And finally, if you have any questions, you can resolve the questions and you can interact with me at the end. So phase one is the fusion welding processes. You all know that welding is joining of two materials. There are three means it's normally used. One is by applying heat or by applying pressure, or some processes are involved both heat and pressure. So it is not only the heat, not only the pressure, sometimes heat and pressure simultaneously applied to get the joining. So any process, if you name it, any welding process you name it, any joining process you name it, that will fit into any one of this category. Either it is a heat-based process or pressure-based process or heat and pressure-based process. So to join two materials, you require either heat is required or the pressure is required. The production of heat for joining, there are many methods for producing the heat for joining the two materials. The very basic, the source is gas flame, and the another source is electric arc, and third one is nowadays it's laser beams are widely used, and electron beam, and chemical reactions also used for producing the heat. So in this lecture, I focus more on the electric arc rather than the laser and electron and the other things. I focus more on the electric arc because the reason is, even today, 75% of welding, material joining, is done by using the electric arc processes only. So that's why I want to focus on that process. If you take any welding process, especially the arc welding process, it will have 5 zones. These are all basics. Then I'll move to the advances. You should know the basics, then only you can understand the advanced welding processes. So in the arc welding process, basically you have an electrode and you have a workpiece. The workpiece is that should be joined. You need to join the workpiece. The material is called as the workpiece, and the electrode is always used in the arc welding process because that is the source to generate the heat or by means of electric arc. So here in this picture, if you see that in this image, if you see that it's the electrode is normally it will be connected to negative or positive. That's different. But it's the electrode. Through the electrode only the current will pass, and in the bottom lobe there is a gap between the electrode and the workpiece. That is known as the arc column or the arc gap. So in this we have 5 different regions. One is the cathode spot, and another one is anode spot. The cathode spot is whenever the electrode is connected to negative, the electrode will become cathode. Negative polarity is connected to negative polarity, it will become cathode. So the tip of the electrode is known as the cathode spot. And in the workpiece, if the electrode is connected to negative, and obviously workpiece will be connected to the positive terminal. So if the workpiece is connected to positive, that region is called as the anode. So in the top surface of the workpiece is called as the anode spot. So in between the cathode spot and the anode spot, that region is called as it's a very important region that's called as the plasma zone. It's a plasma region because here the plasma is generated here and plasma is produced here. So plasma, you know that it is the ionized gas. It's nothing but the ionized gas. So the plasma region will have full of ions, positive ions and negative ions. So nearer to the cathode spot and just below the cathode spot, there is a cathode drop zone. There the voltage will drop here. And similarly, in the nearer to the workpiece zone, there is the anode drop zone. So that is a very intricate zones. But not generally, from the cathode spot to the anode spot, the whole region is called as the plasma region. So in the plasma region only ions will be produced, ionization will take place, positive ions will move towards the cathode and negative ions will move towards the anode. So this is taking place in the arc physics is concerned. So here this polarity is very important because to understand the whole arc welding process, the polarity and current flow is very, very important because this only decides the amount of heat generation that will be taken place in the anode spot or in the cathode spot. So generally there are 3 polarities are used. So I'll go to the next slide. So here this is the 3 polarities used in the arc welding process. One is the DC. DC means direct current. If you use the direct current, you have 2 polarities. One is electrode negative. The name itself suggests that DCEN means the electrode is connected to negative polarity. So if the electrode is connected to negative and workpiece is automatically it will be connected to the positive polarity. So this is the first one. And second one is DC electrode positive. You can connect the electrode to the positive also, positive polarity. If you connect the electrode to the positive, then obviously the workpiece will become negative. So this is called the DC electrode positive. And there is a AC polarity, alternating current polarity. So that is also used for some of the materials like reactive materials. aluminum alloys and titanium alloys, they preferred to go for the alternating current polarity because it has some advantages over the direct current polarity. And in the DCEN, direct current electrode negative, if you see that the heat balance, if you see the heat balance, 70% of the heat is generated at the work end. Work end means the workpiece end, let's say positive polarity. And the 30% heat will be generated on the electrode end. So this is always true because the positive side, the heat generation is more, or heat supplied is more. The reason is from the negative side, from the electrode, if the electrode is connected to negative, electrons will be emitted from the electrode, and those electrons will bombard on the workpiece surface. So electrons are typical characters. They are the very tiny elements. They are very tiny elements, smaller in size, and they move very fast. So here the energy level of electron is decided by the half mv square. Kinetic energy is given by the half mv square. So the electrons, more number of electrons will bombard on the workpiece side, and each electron is having higher kinetic energy because they are lighter in weight, they move faster than the positive ions. So that's why the reason wherever the electrons are bombarding, that bombardment region will have more energy, more heat will be produced there. But in the opposite side, the positive ions will move towards the electrode because the electrode is connected to negative. Positive ions always attracted towards the negative terminal, but the positive ions, the protons are heavier in size, and they are also bigger in size. They move slowly. So because of this slow movement, the energy carried by the positive ions is very, very less compared to the electrons. So that's why the energy the generated in the negative side is very less because of the less number of positive ions are bombarding, and each positive ions are carrying very less amount of energy. So energy will be there, heat will be produced here, both the ends. But when you compare, 2/3 of energy will be on the positive side and 1/3 of energy will be on the negative side. This is happening here. So if you reverse the polarity, if you change the electrode as the positive and workpiece as negative, the positive side, the electrodes will receive more heat will be generated in the electrode side, and the very less heat will be generated on the workpiece side. So this is if you see that 30% at the workpiece end and 70% heat at the electrode end. So if you see the depth of penetration, so here in the ECN, DCEN, deeper penetration and narrow the weld zone. But here in the DCEP, it's a shallow penetration. Penetration is very less and wider weld feed. So that will happen here. Okay. So this process, electrode negative and electrode positive, is suitable for some of the welding process. In the arc welding, there are two groups of welding processes. One is called the consumable arc welding process. Other one is called non-consumable arc welding process. So consumable arc welding process, they use DCEP, direct current electrode positive. Okay, because the electrode, the consumable arc welding, the electrode should melt. So you need to melt the electrode, and the metal should be deposited on the joint area. So you require more heat to melt the electrode. So normally the consumable arc welding process, they use electrode as the positive. Workpiece is connected to the negative. But there are non-consumable arc welding processes are available. Those non-consumable arc welding processes, they use electrode as the tungsten electrode. Tungsten will be used as the electrode. So the tungsten electrode should not melt. So you required, if you apply very high heat, the tungsten also will melt. To avoid tungsten melting and to retain the electrode for a longer weld, so you need to connect the electrode to the negative. So this is the case. So when if you non-consumable arc welding processes, they use electrode negative polarity. And AC, so this is why they are going for AC, alternating current. So in this case, if you take DCEN, okay, DCEN, the electrode is coming from the electrode, the electron is coming from the electrode, and they are bombarding on the workpiece surface. But if you take in this case, the electrode is, the heat generation in the electrode is less. Okay, so overheating of electrode is avoided, and the electrode melting is also eliminated. But at the same time, if you take the electrode positive, what happens here? The workpiece, if you take the workpiece, from the workpiece, electrons are coming out. Because the workpiece is connected to negative, from the negative terminal only the electrons will come out. So when the electrons come out, they will break the oxide layers. What are the layers available on the material surface? The oxide layers, if you take aluminum, it has aluminum oxide. If you take titanium, titanium oxide is there on the surface. So to break those oxide layer, these electrons will help. That's called as the cathodic cleaning. So when the workpiece is connected to negative, workpiece will act as the cathode. The cathode, from the cathode, electrons will be emitted. The electrons will remove the oxide layers. That is, automatically the workpiece surface is cleaned by the emission of the electrons. So in this AC polarity, what happens? Half of the cycle, electrode is negative. Half of the cycle, when the electrode becomes negative, workpiece is positive. In the next half of the cycle, the electrode will become positive and the workpiece will become negative. So here what happens? Both will be balanced. The heat is balanced in the electrode side and the workpiece side, and also the cathodic cleaning action taking place one half of the cycle, and the next half of the cycle, electrode overheating or electrode melting is avoided in the next half of the cycle. That's why people go for the reactive materials like aluminum and the titanium alloys to break the oxide layer, to clean the surface during welding. They go for the AC polarity rather than go for the DC polarity. So this is the basic for all the welding processes. So why I spend more time is, if you understand this, it is very easy to understand all the welding processes, especially the arc welding processes. So consumable arc welding processes, we have shielded metal arc welding process, that's called as the manual metal arc welding, and gas metal arc welding process, it's also called as the MIG welding, flux core arc welding process, submerged arc welding process. And non-consumable arc welding, we have two processes. One is gas tungsten arc welding, that's the TIG welding process, and another one is plasma transfer arc welding process, plasma arc welding process. So we'll see that one by one quickly. You all aware of this process. I don't want to spend more time on these processes. The first one is shielded metal arc welding. Why it is called shielded metal arc welding? The shielded metal arc welding process, you have an electrode. The electrode is called as the stick electrode. Why it is called stick electrode? It will have a standard length of 300 mm or 350 mm or 400 mm length, and the material is at the core. Core as the material. What are the material? Whether it is a carbon steel or stainless steel, that will be at the core, and it is surrounded by a flux covering. It is surrounded by the flux covering. The flux material will have the alloying elements and also the gas forming elements. So when the flux melts, and that the flux melts, they produce a gas. That gas will expel the surrounding oxygen and nitrogen from the atmospheric air. Because whenever you do the welding, this will be a very high temperature. That's a molten region. This molten region, okay, this molten region is involved. If it is exposed to the atmosphere, easily they will react with oxygen and the nitrogen. So if they react with oxygen and nitrogen, oxides will form and nitrates will form. So if the oxides and nitrates forms on the weld metal, and they will be entrapped, and sometimes there will be oxide inclusions or nitrate inclusions. So these oxide inclusion, nitrate inclusions should be avoided, because if there is any inclusion, that will reduce the ductility of the material and the strength of the joint also. So to avoid that, the gas is formed while melting the flux, and also the slag will be deposited on the solidified metal, that will give the proper covering to the molten metal and also solidified metal. So this is happening in the shielded metal arc welding process. So this process, electrode is always connected to positive, workpiece is connected to negative, because the electrode has to melt. You require higher heat. So 2/3 of heat, 70% of heat is required on the electrode end. So you have to connect the electrode as the positive, and workpiece is connected to the negative here. But it is a manual metal arc welding process. Once the electrode, the length 300 mm or 350 mm is over, then you have to change the change the electrode after one welding after the other. Right, the next process is gas metal arc welding. The gas metal arc welding is an automatic process because to overcome the problems faced in the manual metal arc welding, this process was developed. Here, the electrode is in the form of wire. It's a wire. The wire diameter, normally we have three diameters, 0.8 millimeter, 1.2, 1.6. These are the diameters of the wire. It's a solid wire is used here in the gas metal arc welding process. So to feed the wire, you need to have a wire feeding unit. Through the wire feeding unit, there is a torch. Through the torch, the wire will be fed. And here also, it is a consumable arc welding process. So the electrode, the filler wire, should be connected to the positive terminal only, because to get the melting of wire is required. So the shielding gas, you have to supply the shielding gas externally. Okay, the filler wire will not have any flux here, so it is a solid wire, a bare wire. So that should be, when it melts, it should be completely shielded by the inert gases or the other gases. So shielding gas should be supplied externally through this nozzle torch only. So here normally in gas metal arc welding, the very widely used shielding gases are argon, and sometimes the helium also used, and sometimes the CO2, carbon dioxide, also used for the carbon steel welding, not for the other welding processes. And sometimes mixers of these shielding gases also used as the shielding element. So this is the cross-sectional view of the gas metal arc welding torch. And inside, if you see the torch, you have the wire feeding unit is there, and there is a cooling arrangement because a lot of heat will be generated. So to cool that, it's the air-cooled torches are available, water-cooled torches are available. Based on the current rating, you can go for, if it is a low current rating, you can go for the air-cooled torches. If it is a high current rating, then you can go for the water-cooled torches.
In metal.
So this is a clipping how the MIG welding, it's a gas metal arc welding process works here. It is a continuous process. No need to change the filler wire or electrode here. So as long as you can weld even 100 meters or more than that. Also, you can weld in a one pass itself. And it's a flux core arc welding. It's a variant of gas metal arc welding process. So here, in the previous case, the filler wire is solid wire. I told it's a solid wire, bare wire. But here, the tubular wire, it is a tubular wire. In the tubular wire, the core of the wire consists of the flux. So the flux will consist of alloying elements and also the gas forming elements. So it's like in the shielded metal arc welding, the flux covering is in the outer side, but in the flux core arc welding, the flux is kept in the inside. The core is the fluxes. So this is the advantages. Here the advantages, you can add the alloying element through this flux. That is one advantage. And by that you can vary the chemical composition of the weld metal. And another advantage is this will give, though there is additional shielding gas, you can send the additional supply the additional shielding gases externally, but the flux itself produce the shielding, the gases, that it will give a double protection to the molten weld core. So through the external shielding gas, one protection, and through the flux melting, there is another protection. So it's a double protection you will get here in this flux core arc welding process. So this is the clipping, how this process is used. Here also it is the automatic process, and you can do the wire will be fed continuously. There is no need to change the wire, and you can weld continuously any meter length. It can be possible here. Only thing is the slag will form. The slag should be removed between the process. So another one is submerged arc welding process. The submerged arc welding process, wire is fed separately and the flux is fed separately. So that is the advantage of the submerged arc welding process. Because making flux cored wire is somewhat challenging one than making the solid wire. So making solid wire is easy when compared to the making flux cored wire. Because for making flux cored wire, you require tubular. So the diameter is So again, it is 0.8 mm, 1.2 mm, 1.6 mm. So within the diameter, making tubular wire is highly challenging one. So to avoid this problem, these difficulties, to overcome those difficulties, the solid wire is used here and the flux is supplied separately. Okay, so this is the arrangement of the submerged arc welding process, and you can see that it is fully, the arc is completely submerged. You cannot see the arc as in the case of gas metal arc welding or flux core arc welding process. The arc is completely submerged, and once the welding is completed, you can, the slag which is formed on the surface, that can be removed. It's a very I can say it is a very pure, high pure weld you can get by this process, and also high deposition rate. And it's because high heat energy, there is no heat loss to the surrounding, like in the SMW or gas metal arc welding processes. But here, all the heat, whatever generated, that is going into the weld metal. So high deposition rate you will get, thicker plates you can weld, and it's a high quality, pure quality you can get. Only disadvantage is it can be welded only in the downhand position. You cannot weld in the vertical position, or you cannot weld in the inclined position, or you cannot weld in the overhead position. That is the only limitation of this process. And now we are going to the next, that's a non-consumable arc welding process. That is the gas tungsten arc welding process. One of the non-consumable arc welding processes, gas tungsten arc welding process, that's called as the TIG welding process. In the TIG welding process, as I told in the beginning, you have an electrode. That electrode is non-consumable. So normally, tungsten will be used as the electrode here, and it is the electrode is used only to generate the arc, generate the electric arc, and that arc, in that arc, you have to introduce the filler wire separately. Filler wire should be introduced separately, and the wire will be melted by the electric arc, and it is deposited on the weld region. So this is the setup schematic diagram. So the filler rod, the rods, it's in the form of rods you have to add, and the starch will be held in the one hand. So the welder required high skill if you are doing it by the manual welding process, because both the hands should work as it's in a synchronized way. Then only you will get the perfect weld. Suppose if the filler rod comes out of the arc region or the shielding gas region, the filler rod will get contaminated. Okay, so that's why the welder skill is very much important for this process, for the success of this process. Otherwise, it is a very good process, high quality weld you will get here, and it is best suitable for the thin sheet welding rather than the thick plate welding. It is best suited for the thin plate welding, and it's a TIG welding process. And you see that both the hands,
it must be added externally, usually manually, or with the use of some mechanical wire feed system. All of the arc and metal shielding is achieved through the use of an inner gas, which flows out of the nozzle surrounding the tungsten electrode. The deposited weld bead has no slag requiring removal because no flux is used.
So this is a flux-free process. No flux is used, only the shielding gas. Normally, argon is used as the shielding gas, and sometimes now it's for heavier, thicker plates, they go for the helium as the shielding gas, they will use it. And the plasma arc welding, it is also a non-consumable arc welding process. In the plasma arc, the difference between the TIG welding and the plasma arc is the electrode is kept inside the nozzle. That's a torch, and the electrons which is coming out from the electrode by the nozzle orifice. The nozzle orifice will constrict the arc. So when compared to the TIG welding, because if you see the setup of TIG welding and this, the electrode is in the TIG welding. If you go back to the slide, the tungsten electrode is outside the torch. It is outside the torch. But in the plasma arc welding, the tungsten electrode is within the torch. It is kept within the torch. So what happens here? The arc which is produced by the tungsten electrode, when it comes out, there is a torch body. The torch body is given the positive terminal. So it is this will constrict the arc, and that's why in the compared to TIG welding, here you will get a narrow arc. You will get The arc is very narrow here. It's a constricted arc. People used to say it is a constricted arc. The constriction is produced by the torch body. The nozzle orifice is producing that constriction. Otherwise, the all other things are similar. But in the plasma arc welding, you have different variants are there. It's called the microplasma, soft plasma, keyhole plasma. So microplasma means it's a very thin sheets, thin foils. That's based on the current level. What are the current level you are using? So the plasmas are classified. Microplasma means it's a very low current, very small current. It will be used, and also the arc, the heat is very small. It will be used for the thin sheets or thin foils. And the keyhole plasma is for the thicker plates. It's more than 6 mm. If you want to weld more than 6 mm, then people go for the keyhole plasma. And soft plasma is in between that. That's a keyhole plasma. You can see that video clipping, how it works. Yeah, so now I will go to the slightly advanced topics. So whatever I covered so far is the basic processes, basic arc welding processes. So a lot of variants have come in all these processes. We'll see some of the, I am not going to cover all the advances or all the variants of this process because it's very difficult to cover in 1 hour or 1.5 hours, all the processes. So one of the variant is called as the pulse current welding process. So this pulse current welding is applicable for TIG welding, GTAW, and gas metal arc welding. For both the process, this can be applicable. If you use the direct current, so direct current welding, in the direct current welding, electrode is, you can connect the electrode as the positive and the workpiece as negative. The current is varying from the minimum current to maximum current. So the minimum current is, this is required, the minimum current is required to maintain the arc. If the current becomes 0, arc will extinguish. To avoid the arc extinguishing, the minimum current should be supplied continuously always. So the maximum current is, the current is required to melt the electrode, melt the filler wire or filler rod. Right, it's in the consumable arc welding, you are using, whether it is consumable arc welding or non-consumable arc welding, you are using a filler wire, you are using an electrode, or you are using a filler rod. So that should be melted and that should be deposited in the joint area. So for melting, during melting, you require very high current. But that is normally in the constant current welding, what they do, suppose if you are welding some 6 mm thick aluminum sheet, okay, so the current will be fixed at 200 ampere in the constant current welding. That 200 ampere current is supplied continuously from the beginning to end. The current will be supplied at 200 ampere. There is no fluctuation in the current. But in the pulse current welding, the current will fluctuate from minimum to maximum because 200 ampere current is not required continuously for welding. Because if you see the welding process, there are various sequences are involved. The current is supplied through the electrode, the filler wire melts, and once the filler wire melts, the molten metal will grow in size, and when it grows in size, there is a forces will act on that. It's a surface tension force. If the surface tension force is that is used to detach, that is used to stick with the electrode, the droplet. Once the droplet grows in size, the gravitational force of the droplet will be higher. It will be increasing. Once the gravitational force taken over by the surface tension force, or the gravitational force is higher than the surface tension force, then the droplet will detach from the electrode tip, and then that will be transferred to the joint area. So all those things will happen in microseconds. It will not happen in minutes or something. They will taking place in microseconds. So even the metal transfer modes of metal transfer, there are many transfers are there, starting from the dip transfer, spray transfer, globular transfer. This pulse transfer is one of the type. Pulse transfer is one of the type. So the transfer means metal transfer. It's how many droplets are produced in 1 second. Okay, if you have 5 droplets per second, then it is called as the globular transfer. If it is 100 drops per second, then it is called as the spray transfer. So based on the number of the drops produced per second, the transfer, that's metal transfer, will differ. So here in the pulse transfer, the current is, the maximum current 200 ampere is supplied only to melt the filler wire or the filler rod or the electrode. Once the melting takes place, the molten droplet will take few microseconds to reach the joint area. So during that time, bring the current to a lower level. Lower level means to maintain the arc. So like that, it is the current is fluctuating from minimum to maximum. So drop by drop. So whenever current reaches the peak current, the molten droplets will form. Whenever the current reaches the background current or base current, the molten droplet will transfer. So during transfer of molten droplet from electrode tip to the weld pool, the current will be lower level. During melting time, current will be at higher level. So this is, by doing this, what happens, the heat supplied to the weld region, you can minimize or you can reduce greatly. So what are the advantages? So peak current is used to melt the electrode and detach the molten droplet. Base current is used to maintain the arc. Between pulses, heat will dissipate and gives cushioning effect. Pulse current produces fine equax grinds. So how it produces? The mechanism is, when the current fluctuates, maximum current, the peak current, during that time, the heat will be high, and the force, the magnetic force also will be high. So these things are fluctuating. Temperature is also high. Heat is high, force is high, temperature is high. But when it is the current reduced to base current, the heat is reduced, temperature is reduced, and force also reduced. So the fluctuation of forces, fluctuation of temperature, fluctuation of the heat, that causes the grain refinement in the weld region. And this is the technique normally used for the hot cracking sensitive materials. Materials that are high alloyed materials are sensitive to the cracking. So they will go for the pulse current technique for those materials. So this is how the pulse current will work. So if you see that the arc will fluctuate. Arc is not a stationary arc, it is a fluctuating arc. Because of the current is fluctuating from maximum current to minimum current, the current is fluctuating. So because of that, the arc is also fluctuating here. So this is having advantage of producing, see that you can clearly you can see the difference when you use constant current. Constant current means if you use 200 ampere continuously from starting to end. So this is the bead appearance. If you use pulse current varying from 200 ampere to 100 ampere, if you fluctuate, then the bead appearance will look like this. And also the grind refinement in the weld region, the grinds will, this is the constant current welding microstructure, right? The grinds are porous, bigger in size. If you see that in pulse current welding, this is the grinds become smaller, finer. So finer grinds have many advantages. It's always preferred to improve the strength of the joint. And another technique is magnetic arc oscillation technique. So here, the arc is oscillated by means of the external magnetic field. So if you are in the torch surrounding the electrode, they will place the 4 or 8 or even 2 magnets, because now the electric arc itself will have some magnetic field. If the magnetic field is disturbed by another magnetic field, then the arc will deflect. Arc deflection. You hear about, it's one of the defect actually. Arc glow is one of the defect, but this the defect is converted into a useful one by means of some mechanism. So that mechanism is called magnetic arc oscillation welding. So the setup is like this. So this is the actual torch body. You can see the electrode here, and that's the external magnetic field is kept here. So by the magnetic field, external magnetic field will interact with the original magnetic field surrounding the electrode. So there is arc will be deflected. We can see in the clipping. So like this, in the torch body, you have the external magnetic field. Either you can have 2 magnets or 4 magnets. It all depends on your requirement. So if you keep that, these magnets are energized sequentially. Suppose this, when this one of the magnet is energized, other magnets are it's not energized. Let's say the one of the magnet is on condition, the other magnets are kept in the off condition. So this only one magnet at a time will energize, and that will produce a magnetic field. That magnetic field will deflect the original magnetic field of the arc. So this is happening here. So you can see in the clipping, you can understand that how the magnetic deflection is taking place, arc oscillation is taking place. So you see that arc is deflecting from left to right. Okay, you can see that clearly. It is a two magnets are there. One is on the right side, other one is on the left side. So when the left side magnet is energized, right side magnet is in the off condition. When the right side magnet is in the on condition, the left side magnet is in the off condition. So based on this on and off, the magnet, the arc is deflected from one end to other end. It's not only that, you can also, if you use 4 magnets, then the arc will rotate. You can rotate the arc continuously. You can rotate the arc continuously. So these are the variant of the TIG welding. This is useful for, you can use it in the TIG welding process, gas junction arc welding process. You see that, what is the effect of this? So without arc oscillation, if you do that welding, the weld metal region will have grinds like this. Okay, these grinds are very coarse in nature. But if you use the arc oscillation, okay, the grinds will become finer grinds will get. So this is an advantage of having finer grinds. Finer grinds will have higher strength, and also you have the higher hardness, and the cracking, especially the cracking, can be avoided here. So you can combine the pulsing current with arc oscillation also. That is also possible. So constant current welding, you see the microstructure here, weld metal microstructure. It's where exactly the welding takes place, the microstructure. And it's a coarse grinds. Grinds are very big in size, bigger in size. But if you see pulsing current, so the grinds will become finer when compared to CC. If you compare PC, it is finer. And arc oscillation, again you are getting finer grinds. If you combine this pulsing current and arc oscillation, you will get very, very fine grinds here. Okay, so you can see the difference. If you this is good. This is a preferable microstructure because the strength is enhanced and the many properties are enhanced in this case. Finer grinds, mechanical properties like tensile, impact, fatigue, strength will be enhanced, and reduces the hard cracking problems. The problems, especially high alloying elements, the cracking is the problem that can be minimized here. And another process is in the variant of the TIG welding is gas tungsten constricted arc welding. So we have seen constricted arc in the plasma. Okay, as I told now, when I introduced plasma arc welding, so it's a constricted arc. So constricted arc is always preferred because now you have to keep the weld zone or weld metal region very narrow. Okay, any welding, wherever you keep the weld metal region very narrow, that has many advantages. Because if the weld metal region is narrow, the adjacent heat after zone, because heat after zone is the problematic region in all the welds, all the arc welding process, fusion welding process. Okay, it is a weaker zone. Heat after zone is a weaker zone. So to minimize the heat after zone is one of the objective of all the welding processes. Okay, the advanced welding processes, they are all focusing on minimizing the weld metal region, weld zone, and also minimizing the heat after zone. So that's why laser beam welding, electron beam welding are having greater advantage because they have very narrow weld metal region, weld zone, and subsequently they have very narrow heat after zone. But only the main problem with laser beam welding and electron beam welding is high investment is required. Very high investment is required. Expensive. Equipments are very expensive. But how you can achieve those quality, laser beam welding quality or electron beam welding quality with the conventional welding processes like TIG welding, MIG welding, or the plasma arc welding processes. So people are trying. There are many variants have come nowadays. One of the variants is constricted arc welding concept. It is also called as the interpulse TIG welding. It's popularly known as interpulse TIG welding. This is the patented process. It was patented by Vacuum and Bracing Company. It's a UK-based company. They have invented and they have patented. And this is only few machines are available in our country. And the idea is, as I told, no, it's when the current passes through the electrode. So this is a TIG welding, tungsten arc welding. So tungsten arc welding will use tungsten as the electrode. So when the current passes through the tungsten electrode, there is a magnetic field surrounding the electrode, tungsten electrode. So that magnetic field that will decide the width of the arc. Width of the arc will be decided by the current, magnitude of the current, and the current density. That's not current density, the magnetic field. So both will decide the width of the arc. Arc width can be decided. So if you are able to reduce the magnetic field, okay, if you're able to reduce the magnetic field surrounding the electrode, then automatically the arc will become constricted, arc will become very narrow, or arc will become focused. So that is, they are supplying another current. If you see this here, the arc current, and this is another current. It's called, they are calling it as a delta current. They are calling it as a delta current. A third current they are supplying here. Okay, that current is producing another magnetic field in the opposite direction. So when this opposite direction the magnetic field is produced, the original magnetic field is constricted, and that it causes the very narrow. If you see that in the clippings, you can understand how it works. So this is the left side. It is the constricted arc. This is the interpulse stick welding, IPTIC, or constricted arc welding. The right side, it is the this original constant current arc welding. You see that the difference between this and this arc width is wider in the constant current welding, but in the constricted arc welding, arc width is very narrow. It is constricted because it's a pulsing current is applied, and also the pulsing current, as I told, no, you have base current and peak current, and third current is a delta current you are applying. The delta current constricts the arc, and it produces the arc quality in the matching with laser beam welding and electron beam welding. Okay, so this is, you can understand here, a superposition of high frequency 20 kilohertz waveform, and the main current leads to narrow and stiffer arc than the conventional inverter arc. So you can have arc width is 2 mm, that's a minimum, and arc you can supply even at 0.5 ampere current, you can generate the arc. That's the advantage of this process. So inverter arc will have a very narrow arc, but sorry, the interpulse arc will have very narrow, but inverter arc means a constant current. Conventional TIG welding process will have wider arc current. So what is the advantage of constricted arc? Because here, when you constrict the arc will become stiffer and narrow. When they become stiffer and narrow, the energy, right, the energy density in that spot, in the area, will be very high. Smaller area, more energy is falling. But if you take the constant current conventional TIG welding, it's a wider arc. In the wider arc, the energy, whatever the energy that was carried by the arc, it is falling on a wider area. So wider area will take only you will get the shallow penetration. Penetration is very shallow in the case of constant current welding, but in the interpulse welding, it is the deeper penetration is possible, and it is mainly suitable for the thin sheets welding, not for the thick plate welding. It is for the thin sheet welding, less than 3 mm thickness. It is it's ideally good process. So there is a comparison between laser and interpulse stick welding. So a lot of benefits are there. You can get X-ray quality, and you will get the running cost is very low here, and it's the repeatability is also very good here, and easy to use and low risk. These are the advantages of this process. And applications, welding of similar nickel-based superalloys. Basically, this process is developed to weld titanium-based alloys and nickel-based alloys. That's the high-temperature alloys, especially on the aerospace applications, not for the other applications. But now people are using this for the other applications.
Hello, sir. It's not audible.
Hello, sir. It is not audible.
Is the slider? Yeah, sorry for the disturbance here. So here in the CMT cold metal transfer, the first stage during the arcing period, this period is called the arcing period. The filler metal is moved towards the weld pool. Wire is moving. That's the filler metal means the wire is moving towards the weld pool. And when the filler metal dips, dips in the weld pool, the arc is extinguished. Almost it is extinguished because short circuiting will occur and that will extinguish the arc, and welding current is lowered here. And then the arc, the filler wire is again it's retracted. I told you there are two motors are there. It's reverse. In the reverse direction, it is rearward movement of the wire assist droplet detachment during the short circuiting period. And again, no, the wire motion is reversed and the process begins here. So this is during arcing period, it will move forward. And once the droplet reaches the weld pool, then again it will be retracted again in the backward. And once it reaches the arc gap is reached, and again it starts melting. The wire is melting here. So the advantage is you can see that how the CMT works here. See, the right side is the conventional MIG welding. The left side is the CMT. The right side, you see that it's continuously the filler wire is melted and the droplet is formed and it is moving towards the weld pool. But here in the CMT, the filler wire is melted and it is during the forward direction and again it is retracted back. So by doing that, what will happen? Here the current also reduced. Okay, current also reduced here, but here the current is kept constant in the conventional MIG welding. So because of this, the heat supplied in the CMT process is enormously reduced when compared to the conventional MIG welding process. So it is a low current and low voltage process. Hence, it is a low heat input process. Peak temperature is very low here. Peak temperature is low. Fast cooling rate, because peak temperature is low means definitely it will cool very fast. And in the dissimilar welding, it is ideal process for joining dissimilar welding. Intermetallics is minimum due to the above said reason. And narrow heat up to zone, that is another advantage because of heat supplied. Overall heat supplied is minimum. So the weld region also narrow, and subsequently the narrow heat up to zone. It's a fast process, and the productivity is there is no reduction in productivity, and best suited for thin sheet welding. It's a spatter free. That's another advantage of this process is no spatter. Normally the MIG welding is involved with a lot of spatter, but here it is spatter free process. And the pollution, it's a less pollutant. Pollution will be there, but compared to the gas metal, it's constant current welding, conventional MIG welding, the pollution is very less here. And another variant of this gas metal arc welding is spin arc welding process. So this is also coming up in the big way now, because for welding thick plates, when you are welding thick plates, there are many challenges you have to face. So here it's a narrow gap welding process. So one type of narrow gap welding process. We will see that how it works.
Weld Revolution has created a unique welding process that allows you to perform superior welds while improving efficiency. This patented technology has an adjustable rotating welding arc, which enables welding in all positions, using both solid and metal core wires in a spray-like mode. Our rotating arc technology can be used in all welding positions.
due to the surface tension created from the high-speed rotation. Joint preparation can be drastically reduced, as a square-cut edge is sufficient for most welding applications.
You see
By
that
minimizing
the wire will
weld
rotate
stress
here.
and distortion are reduced. The high-speed revolving motion holds the puddle in the joint, and the stirring action results in a cleaner weld with enhanced properties. This revolutionary process fills the gap and ties the sidewalls together, virtually eliminating lack of fusion. The rotating welding arc is extremely versatile. By changing the diameter and speed of rotation, the weld is optimized for narrow and wide grooves. Weld Revolution uses a centrifugal arc transfer or CAT welding torch to deliver this unique technology. Whether it's a pipe welding bug, welding robot, hand torch, or custom automation, we have the right solution. When it comes to welding, choose the company whose name says it all. Weld.
Yeah, the advantage, if you see that, if you conventional MIG welding process, you have to prepare the edges. If it's a thicker plates, okay, it's more than 6 mm, or if you're welding half an inch thick, then you have to prepare a V groove like this. So the V groove preparation means you are removing the material, so loss of material there. And another thing is, and you have to deposit more amount of weld metal to fill this groove. But when you go for spin arc welding, there is no need of this V edge preparation. Only the square edge preparation is enough. And because of the square edge preparation and the number of passes, here if you require 6 passes here to fill this V groove, but here it is required only 3 passes. You can fill the entire joint area. So by that you can improve the productivity. Productivity has enhanced when the spin arc welding process. So 60% increase in productivity and 40% weld cost reduction and 60% weld metal. That's very, very important. Weld metal is reduced here, deposition of weld metal. Okay, so here it is number of passes reduces, that reduces the weld metal also. So it reduces the distortion because the heat supplied is also reduced because of number of passes. So no slag removal and no beveling is required. Edge preparation is required here. So these are the advantage of this. It's called spin arc welding or rotating arc welding or revolutionary arc welding. Different names are used. It's mainly for the thicker plates for high productivity. This process, this variant is widely used. But basically it is a MIG welding, gas metal arc welding process. Right. So maybe it's another, I think it's another half an hour. I can take the second phase, solid state welding process. So far, whatever I covered is on the fusion welding process. Heat is involved. That heat is produced by the electric arc. The electric arc is used for melting the base metal as well as the filler metal. Both will be melted, and there is a fusion takes place. By the fusion, the joining takes place. Right? So that is the heat-based processes, whatever we have covered here. So in the heat-based processes, the main thing is the weld metal area should be kept minimum. And if you keep the weld metal area minimum, then obviously the heat after zone area also will become minimum. The reason is heat after zone is the vulnerable region. That's a weak region in any joint. Okay, weld metal will be stronger because of the alloying elements and the finer grinds and all those things. But heat of the zone is the weaker region because of the coarse grind formation, and also there's loss of alloying elements from the heat of the zone. So those are the reasons that region becomes the weaker region. So the people want to keep minimum heat of the zone, and if you want to keep minimum heat of the zone, then you need to minimize the weld metal region. So these are all interrelated concepts. So to the process which gives narrow weld metal region and narrow heat of the zone is known as the best welding process, best fusion welding process. So the people are trying to, that's why these are all advances. What are the advances we told? Pulse current welding, magnetic arc oscillation welding, or interpulse TIG welding in TIG welding process. In the MIG welding process is the cold metal transfer welding or the spin arc welding. So, okay, these are the processes which are focused on surface STT. There is another process called STT, surface tension transfer process, and even the pulse current welding in MIG welding. Okay, so this is all developed to minimize the weld metal region and also minimize the heat of the zone, and also to improve the productivity. So that's the concept of fusion welding. So coming back to the solid state welding process, there are many processes out there. I am not going to cover all the processes here because the time is limited. The very important processes, I'll cover this. So solid state welding means here there is no melting at all. There is no melting of materials. Okay, without melting in the solid state itself, the bonding, the joining is taking place. So some of the processes, they will apply only pressure for joining in this solid state welding. Some of the processes will apply both heat and pressure. Both will be applied here. So we will see that one by one. First one is diffusion bonding process. There is a solid state welding process and its application of pressure at elevated temperature. So pressure is important and temperature is important and does not involve macroscopic deformation. Though the pressure is applied, there is no macroscopic level deformation. Microscopically, there is some deformation and there is no solid filler metal is inserted here. You'll see that how it happens. So it is, there are different stages in diffusion bonding. The first stage, the deformation, forming interfacial boundary. So you have top surface and bottom surface. This is the bottom one is the top surface of the bottom plate, and the other one is the top surface, the top plate. When they will kept on one over the other, though there is a surface finish is good, but there is asperities are there. Asperities means there is ups and downs are there in micron level ups and downs. So during this contact period, the contact will occur only in few points, localized points. So when you apply the pressure through this two materials, pressure is applied and also temperature also you need to apply. So these both and pressure and temperature causes the flow of elements through these contact points. Okay, the elements will flow from this side to this side and this side to this side. It's a diffusion of atoms. Atoms will occur through the contact points initially. When the pressure is applied, the deformation takes place and the contacts is getting wider. Initially, it is the point contacts. That point contacts transforms into the line contacts. That line contacts then transform into the area contact and volume contact. So through this contact only, the diffusion of atoms will taking place. Atoms will move from one location to other location. So there are many principles available for diffusion of atoms. It's based on the Fick's law. I don't want to elaborate on those Fick's law here. It's a Fick's law 1 and Fick's law 2 is there. So through that, by governing that, this diffusion of atoms will take place. Moving up, diffusion of atom means nothing but movement of atom from one location to other location. Why they move? Because the concentration. If the concentration is different from higher concentration, it will move to the lower concentration. So the solid phase bonding in solid phase is carried out in vacuum. It requires vacuum chamber, and it's required a heating source. That's the induction heating is required, and you need to apply the pressure, and you need to prepare the surfaces. Surface finish should also be met. It's a factor here. Normally, it should be kept 0.4 microns, and it should be clean as possible. So this is a small diffusion bonding machine we have in our center. It's a low temperature. We can go up to 1000 degrees centigrade. So you need to have a die like this. This is the vacuum chamber, and the bottommost vacuum chamber. It's, in that only the die assembly. This die assembly will be inserted here, and then it is closed, and the pressure is applied through this, and you can measure the pressure, how much load it's acting on the specimen, and how much temperature it is. So all those things you can measure, and you have to maintain. So we can see the clipping here. So you can stack any number of metal pieces one over the other. Not only that one piece, you can stack any number of pieces here. So load and heat are applied in a controlled atmosphere. So these are the grinds, the movement of grinds, grind boundaries. It's a very slow process, but the video is fast. It's a fast video. It will not happen in a fraction of a second. It will take a few hours to happen, all these things to happen here in this process. So it is bonded now. Right, so solid phase diffusion bonding and liquid phase diffusion bonding. Suppose if you want to join dissimilar materials, then you have to use some insert. Metal inserts will be used. Normally silver, copper, these are the inserts normally will be used, because if the temperature, melting temperature is more, the difference is more between the two materials, then you have to use these inserts. The inserts will melt and they will spread to both the surfaces. The bonding will occur through that. So this is called the liquid phase diffusion bonding. So by this you can join ceramics to metals also. Ceramics to ceramics and metals to ceramics and composite to metals. So different combinations you can join by using this liquid phase diffusion bonding method. So I just want to skip all those things. So these are the criteria that should be considered for diffusion bonding. One is surface roughness. As I told, 0.4 microns are required. And the bonding pressure. So pressure should be selected in such a way that it should not exceed the yield strength of the material. Okay, because if the pressure exceeds the yield strength of the material, then deformation will occur. If the deformation occurs, you will lose the shape, you will lose the profile, you will lose the dimensions. So it should be less than yield strength. And bonding temperature, that is also very important. It should be normally 50 to 70% of the melting point, because if you go beyond that, a recrystallization, every material will have a recrystallization temperature. You should not exceed, you should not go to that region. It's well below the recrystallization temperature. And the holding time, as I told, the diffusion will take place slowly. Okay, so how much time is required? 30 minutes or 60 minutes or 90 minutes, 120 minutes. So that's it's a very slow process. For completing one cycle, it will take minimum of 3 hours. Slow heating, and then the temperature should be maintained for quite some time, soaking period, then slow cooling. Then only the cycle will be completed. So it is a very, very slow process. But for some of the applications, some of the dissimilar material combinations, this is the ideal process. And you can see that how this diffusion bonding is
There's been a huge
a big
resurgence of interest in diffusion bonding at TWI. Indeed, it's invested in a rather unusual machine to do just that on longitudinal section. As Alec Gunner explains,
we've been diffusion bonding here at TWI for the last 41 years now. In the early days, there was obviously a lot of interest about what this technique might be.
It's a vacuum chamber, so vacuum chamber is required for the diffusion bonding. These are the two specimens or the component to be joined here that will be kept inside the furnace. The furnace will be closed and it is vacuumized, then it is heated, then the load is applied.
A particularly good joint. It's a very simple process. The equipment is really not a lot more than a hot box with a press running through it. It works on the principle that if you heat components up to the point where the atoms on the surface have enough energy to start jumping across the gap, then they will bond together. So you would take two components with a very good surface and you push them together and heat them up and wait. You can form a bond which is metallurgically perfect. If you took a section through that bond and polished it, then if you've got the conditions right, you won't be able to see where the bond line is. And if you then did tensile testing, you would expect the failure to occur in the parent rather than the joint. The new machine is a bit different. Most machines work with a vertical press. This machine has been built with side ports so that we can put extension tubes on and swing it round horizontally. And that way, we're not really limited as to how long a component we bond. So in theory, we can put longer and longer side pieces on and make longer and longer components. So
the load is
like
applied now.
rods or
Thermocouples are fixed to measure the temperature. It's an induction heating furnace. Inside the furnace, the specimens were kept stacked one over the other.
Unique advantages. So, for example,
so now he is closing the furnace.
Effectively, you can make a structure which you would want to machine out of a solid block, but simply couldn't get.
Fixing the temperature, fixing the pressure.
There's interest in heat exchangers. There's interest for various aerospace components. Aircraft brakes have been diffusion bonded.
So after 2 hours or 3 hours, open the furnace and take the specimens out. So now they are bonded together.
Which can't be manufactured in the lengths needed. And This
So
allows
surface to surface
closest
bonding
thing
is possible
to the
only in this
perfect
process.
joint. And that
So next process is explosive welding, explosive bonding. So here it's also called as welding, explosive welding or explosive cladding. Here the chemical source of energy, energy is chemical substance is used as the source of energy here. That chemical source of energy is applied in a controlled manner to get the metallurgical bond between two or similar or dissimilar materials. We'll see that. So there are normally two setups are used. One is called the parallel setup. So this is one plate, base plate, which is kept stationary, and the other one is called a flyer plate. Why it is called flyer plate? This plate will be accelerated by the explosive, and that will hit on the surface of the base plate. Okay, this is parallel means the gap between the flyer plate and the base plate is uniform. You have to maintain the uniform gap. Over the flyer plate, you have to pack the explosives. Okay, there are different types of explosives are available, and these explosives will be ignited by means of a detonator. Detonator will be kept on the side here. Then once the detonator is ignited, the explosive will explode. That explosion will cause the flyer plate to accelerate towards the base plate, and there is a collision will take place. That collision, during collision, very high pressure will act on the between the surfaces between the flyer plate and base plate, and that causes the bonding between the atomic level bonding between the flyer plate and the base plate. So this is the inclined setup also people use sometimes. It's a 15 degrees, 30 degrees, 45 degrees inclination they will keep. So this will also produce a very good bonding between the two materials. So this is the schematic diagram, how it works, explosive welding works. You can understand here. So this is the parent metal or base metal. This is the flyer plate. So it may be carbon steel, it may be aluminum alloy. So you can bond aluminum alloy over the carbon steel by explosive cladding. So detonation, initially only the detonator will be ignited. That ignition causes the explosives to explode, and that explosion will causes the flyer plate to accelerate and hit on the surface of the base plate. You will see that in a better way in this. So that while it is hitting, colliding, a pressure wave will be produced on both the metal surfaces. So that pressure wave causes the plastic deformation, microscopic level plastic deformation at the interface. So that microscopic level plastic deformation causes the metal to lock. It's interlocking between and they will form a wavy interface. I'll show you in the next slide. So what are the surface layer or oxides or impurities left on that will be removed off or washed off with a high velocity collision. So this is the how it works here. So base plate, and then you are keeping the flyer plate in the inclined position, and over that explosive is loaded, and this is the detonator, and the distance between the flyer and base plate is known as the standoff distance. Explosion, then it's a small animation how it works. And after welding, after bonding, if you cut the section, right, that's a material, if you see the cross section, in the microscopic level, the bonds will be looked like. At the interface, you will have a wavy-like structure. It's called the wavy interface. So this is a typical characteristic feature of this process. So you will get this type of wavy interface only in explosive bonding and magnetic pulse welding. So there are many parameters. Explosive, what type of explosive? Okay, there are many types of explosive, low explosive, high explosive, medium explosives are there based on the detonation velocity. And explosive loading. Explosive loading is E by M. E is the weight of the explosive and weight of the plate. So it is decided by you have to calculate. There is a relationships are there to calculate how much explosive you can use for a cladding or a bonding process. It all depends on the flyer plate mass or the flyer plate weight of the flyer plate. So for that there is a ratio. So if it is if the flyer plate weight is 1 kilogram, so there is a ratio. It will vary from 0.5 to 1. So 500 grams to 1 kg of explosive is required for 1 kg of the weight of the flyer plate. So collision point velocity, collision angle, thickness of flyer, A stand-up distance, it's a distance between flyer and base plate, and flyer velocity. So a lot of parameters are controlling this process. So as I told, no, there are a lot of explosives are there. RDX, PETN, TNT, trinitrotoluene, tetryl, lead ammonium. These two are very low explosives. Ammonium nitride and special gelatin. So these two are used in the quarries. Even if you go to the quarries, they use this two low explosives. Low explosive means the detonation velocity is around 2000 meters per second. Even 2000 meters per second means it is a 2 kilometers per second. If the detonation happens, the velocity will be the flyer plate will fly at a velocity of 2 kilometers per second. That's the detonation velocity. So these are RDX and PETN, they are all high explosives, and lead azide and tetryl, these are all TNT, they are all medium explosives. Okay, so you can use any explosive based on the availability, and the detonation velocity will decide the interface, the wavy interface, formation of wavy interface. With very low velocity, okay, so velocity is very low, 1800 meters per second, you will get a flat surface. You will not get any wavy interface. So if you use 2800 meters per second, detonation velocity is, then you will get a wavy interface, very a huge wavy interface. The amplitude is very high. In the waves, the amplitude is very high. But if you use 2100, you see that a lot of the waves formed in a unit area. So when you measure the bonding strength, this one, 2100 meters per second, this bond will give higher bonding strength because more number of locks are there, more number of wavy interwaves are there. In this, more number of amplitudes are there in this case. Here there is no waves, here it is a very high amplitude wave. So both will have, this will have better than this, but overall, if you compare all the four, this will have higher bonding strength when compared to other conditions. Many metals were joined by this process. Many combinations were joined, and it's you see that only these white regions, white areas, aluminum alloys with zirconium, nickel alloys with zirconium, copper alloys with zirconium. They are not yet investigated. And the stainless steel with molybdenum, low carbon steel with molybdenum. It's not yet investigated. Similarly, nickel alloys, and so other combinations are already investigated. Data are available for other combinations, and you can try these. These are some people want to do research. You can try these combinations: aluminum alloy with zirconium, or nickel alloy with zirconium, or stainless steel with molybdenum. So these combinations they can try. Advantages: similar and dissimilar metals can be welded. Weld area is not restricted. So there is no restriction in the weld area because we are going to do in the open area. Metals have different melting points. Melting point is not a criteria here. Any combinations, any dissimilar combinations you can join. Metals with different properties can be welded. Joint strength is higher than the weaker of the two metals, and is suited for bonding flat and cylindrical surfaces. It has one disadvantage because the reason is that the material to be joined should have some amount of ductility. Brittle materials cannot be bonded here because when the explosion takes place, brittle materials will go into pieces. So the material to be joined should have some amount of ductility. Minimum ductility is a requirement. So a lot of applications are there for this explosive welding. So you see that many components, many structures, even it is used even today it is used in the defense and the space applications. Okay, so this type of domes and everything are made using the explosive forming, explosive cladding processes are still used, and the only problem is the handling of explosives. So you need a lot of restrictions are there. The storing of explosives, storage space, and handling of explosives, and so many restrictions are there. That is the only problem. But government agencies can do. They are doing it. So they are doing a lot of work on this. So the next process is, I think, quickly I'll go through it, running out of time. Magnetic pulse welding. It's similar to explosive welding, but only the difference is there we are using chemical substance. Okay, explosives are used to generate the flare plate to move. Here also there is a flare plate. Here also there is a base plate, but here the flyer plate is accelerated by means of magnetic field. So that magnetic field causes the flyer plate to move and collide with the base plate. So that's the only difference. The source is different. You can see that here, small aneviation. So this is the top one is the flyer plate, and the center one is the base plate, and the maroon color is the magnetic coil. Through the magnetic coil, a magnetic field is generated. That magnetic field causes the flyer plate to accelerate and hit on the base plate. So the magnetic field is in pulses, not in a continuous one. Okay, one shot, so one explosion. So it's also similar to the explosive welding. So if you see that even the interface, if you see that there will be a waves formation of waves will form here, and even the inclined setup, you see that inside schematic diagram, it almost similar to the explosive welding. But only thing is there it is chemical substances are used, but here it is magnetic field is used to cause this bonding to occur. And small clipping, video clipping, how it works, you can see that very closely. So magnetic coil, the coil you have to design for each component, each joint, each component, you have to design the magnetic coil. So that is the coil normally special copper alloy will be used as the magnetic coil that you have to make for the joint requirement. You cannot use one magnetic coil for all the components or all the joints you want to make. So that's the difference here. So very quick process. Charging time is in less than 1 minute. You can actual welding time is less than 1 minute. So a lot of materials were tried already. Copper with brass, copper similar, stainless steel to stainless steel, aluminum, MS. So similar and dissimilar combinations were tried. At the interface, if the waves form, then the bonding strength will be much better. If you get the flat surface, the bonding strength will be it's a very weak bond. If you get a typical wavy interface, then bonding is good. So a lot of parameters here. Voltage, it's one of the parameter which will produce the magnetic field and which is responsible for the accelerating the flyer plate. And standoff distance between the flyer and target plate, and working length. It's nothing but the overlap length. Okay, that's a overlapping length, and flyer thickness. So advantages, it's high speed, high reliable, dissimilar metals can be possible, no need of filler, green process, no heat, no spark, no smoke, no radiation, and it's a very clean process, high quality welds you can get, no distortion, lower cost and productivity. Only problem is the equipment cost. Initial investment will be higher. A lot of applications it finds in the automobile application, drive shaft, air filter, and many of the small components they are making it now. In India, there is one industry at Bangalore, Pina. There is a MagPulse Technologies in Pina Industrial Estate. They have very good facilities for magnetic pulse welding. So finally, it is a friction stir welding process. Friction stir welding is also a solid state welding process. It was invented in 1991, and it has here also there is no need of filler metals, shielding gases, and edge preparations. Nothing is required here. This is also clean process because no smoke, no fumes, no arc glare, and it is environmentally cleaner process. And as I explained this process quickly. So there is a tool, non-consumable tool, and that tool is the heart of the process. So the tool dimensions will be decided by the plates to be joined. What are the plates you are joining? That the plate dimensions will decide the tool dimensions. So suppose they based on the plate thickness is important parameter that is required. Suppose you have a thickness of 5 millimeter thick aluminum alloy, and this thickness of the plate is 5 millimeter. Here in the tool you have two parts. It's very important. One is the pin, that's a probe part, and over that you have the shoulder. The shoulder is having these two dimensions. The pin diameter is equal to the plate thickness, and the shoulder diameter is 3 times the plate thickness. So 5 mm plate thickness, that's pin diameter is 5 mm, shoulder diameter is 15 mm. Okay, and pin length should be 0.5 millimeters shorter than the plate thickness. So you have to make a tool for each plate, that tool will be inserted in the material, that's the machine. Then you have to fix that, you have to rotate this tool at a particular speed, and then you apply the downward force, and that causes the material to flow from one end to other end, and the joining will occur here. So this is the various stages. Fix the tool in the machine, fix the rotational speed, and start the machine. The workpiece will, the tool will rotate, and bring down the tool down, and the pin, initially the pin portion, establish contact with the pin portion. So here the heat will be generated here, and that heat, through this, the pin will be plunging. Then bring down the tool further. The shoulder will establish contact. So larger area come under the shoulder, larger heat generation. Under this condition, the material will be plasticized. The plasticized material will flow from one side to other side, surrounding the pin inside the pin. So once this is established, then move the tool forward, and you will get the welding. So this is a small animation. You can understand how this process works. So this is a tool rotation, and then at the end you can retract the tool. So the shoulder is the major heat generating source than the pin. Pin is only used to stir the material, and also it's a 1/3 of heat will be generated by the pin, 2/3 of heat will be generated by the shoulder of the tool. So this is, we have two facilities here in our center. This is a manual operated friction stir welding machine, and there is a CNC controlled friction stir welding machine also we have. This is how it works. If you see the clipping, this is left side, it is aluminum alloy. The right side, it is the steels, stainless steels or carbon steels. Both by the friction stir welding. The difference is aluminum is very easy to weld. Aluminum, magnesium alloys are easy to weld by this process. But welding of steels and nickel-based alloys or the titanium alloys are very difficult, challenging, because we have to use the tools somewhat, the high expensive tools are required. So the third phase, only few slides, I quickly cover that. Right, as I told, the FSW process, there are many parameters to be considered. Process parameters, rotational speed, welding speed, axial force. These are the parameters. And tool parameters, tool pin profile, tool shoulder diameter, all will decide. And material side, tool material hardness, base material yield strength. These are the parameters that control the quality of the joint or the quality of the process. So there is many equations are there, many models are developed now. This is a very basic equation developed to calculate the heat generation. Q is heat generation, that is given by this equation, 2 pi by 3s mu P omega Rs and efficiency. So if you see that P is the normal force, that is the downward force which is acting, and omega is the rotational speed, and Rs is the shoulder radius of the shoulder. So all these parameters are in the numerator. That means they are having directly proportional relationship with heat generation. If these parameters are higher, heat generation will be higher. If these parameters are lower, heat generation will be lower. But the welding speed, S is the welding speed, that is in the denominator. It is having inversely proportional relationship. Welding speed is high, heat generation is low. Welding speed is low, heat generation will be higher here. So this is the equation normally used. There are many equations now available. You can use any equation. The point is, high heat generation is caused by these parameters: high rotational speed, low welding speed, high axial force. So if you keep higher side of these parameters, and then high heat will be generated. High heat generation also a problem. Material will flow turbulently. Grind coarsening will occur because peak temperature will be high. Precipitates will agglomerate. Flash formation will occur, and this lead to the defects like piping defect, tunnel defect, these defects. But suppose if you reduce that, you keep very low level of speed, low axial force, shoulder radius is low coefficient of friction between the tool and the workpiece, then heat generation will be lower. So lower heat generation also not preferred, because that also form some defects, pinholes, cracks, all those things. So one need to optimize these parameters to get the proper material flow, good consolidation, defect-free welds. Okay, so optimization is very, very important because for some of the established material, the parameters were optimized for this process. For newer materials, even if you change little bit of chemical composition or properties, then you have to optimize these parameters. Then only you can get the defect-free and good welding is possible. So it's suppose if you want to predict these properties, okay, tensile strength or weld metal hardness or corrosion rate. So these are all influenced by the parameters. These parameters. Okay, many parameters as I told in friction stir welding. So these are input parameters: rotation speed, welding speed, axial force, shoulder diameter, pin diameter, tool hardness. So you have to develop a model, whether it is a statistical model or it may be a numerical model. So that model should be useful to predict the mechanical properties and microstructural characteristics. So that's why once you develop a model, then you can use that model for other materials. Only you have to vary the parameters here, okay, properties here. By giving the different properties, you can predict or estimate the outcome without doing the experiments. These are these, maybe people will explain the later how to optimize. There are many techniques are available, and it's what do you call genetic algorithm, artificial neural network, or simulated annealing and colony. So many tools are available for optimization now, and hybrid tools are also available. So only thing is, all those things leads to the optimizing the parameters for a particular material. So you have to optimize all these parameters by using some method. I think this workshop, this FDP program, many topics are there. People will cover many techniques. Please try to understand those techniques, and then it is the use that techniques for your work. And also if you take another process, interpulse stick welding. Okay, as I explained there, main current, delta frequency, welding speed. That's called as cause and effect diagram. Okay, if it is lower than this problem. Higher than this is the problem. Lower than this 40 ampere, incomplete penetration. Higher current, 60 ampere more than over melting. Okay, so if you take delta frequency, welding speed, 40 mm per minute, less than that, over melting of base metal. Welding speed is greater than 80 mm per minute, incomplete penetration. So these problems will occur if you don't optimize that. So you need to optimize the parameters within the range. First, you have to identify the range, within the range, which is the optimum parameters. So by numerical methods like finite element methods, finite element analysis, you can estimate the heat distribution, and also you can measure by experimental methods. You can compare that. I don't want to elaborate. There are many lectures out there, few lectures to explain that. So by using any standard software package like ANSYS or Abacus or even Syswell softwares are available. Using that, you can predict, estimate the heat distribution, temperature distribution, stress distribution that can be predicted and estimated, and that can be correlated with the actual experimental values. So even the bead geometries also you can predict using this numerical simulation method. One of my students did recently. So this is the right side. You see that's experimental, the joints, actual joints. It's interpulse stick welded titanium alloy joints. And also this is the left side is the simulated. Okay, by using Syswell software, he has simulated that, and you can compare the bead width, whether it is matching with the experimental values or not. That you can predict and estimate. So these tools now you can use it for because now these tools will reduce number of experimental conditions, because experiments are now very, very expensive. So you try to minimize experiments by doing the simulation and optimization tools. Using that, you can minimize the number of experiments, and that you can cut down the cost of the experimentation. So finally, a few slides about my university. Those who are outsiders, I just want to spend only 5 minutes. It's a residential university, established in 1929. Recently, we celebrated 90th year. It's a state government, Tamil Nadu State Government University. We are accredited with A grade by NAC, and it's located near the east coast, near to the Pondicherry, 60 kilometers from Pondicherry. We have 10 faculties. Engineering is one among them. We have Faculty of Arts, Science, Engineering, Agriculture. So we have 49 departments, and the Department of Manufacturing Engineering is one among them. So the university is spread over 950 acres of land. So engineering college, as I told in the beginning, the inaugural function, it was established in 1945, second engineering college in the state, and it's 2005 we celebrated the Diamond Jubilee. Actually, 2020 is our Platinum Jubilee year. Due to pandemic, we are not able to celebrate that, and we have 11 departments. Each department is offering one UG program and 24 PG programs. All the UG and PG programs are approved by ASP. Regarding our department, it's manufacturing engineering. We are one of the best department in the university. We do a lot of research. We do teaching, research, extension, and other activities. These are our performance publications. We have 750 publications, national and international. Out of this 750, 550 in Scopus Index Journal. And similarly, we used to attend many conferences. Our faculty members used to present in conferences and research scholars. And so far, we have produced 125 PhD in the department. And the projects, we have completed more than 50 projects, R&D projects, 35 and infrastructure and consulting projects. And so far, we have generated more than 18 crores through the projects alone. We used to organize many programs like this periodically. And facilities are there. A lot of facilities are there, minor to mega facilities. We have normally we used to develop products, processes, procedures, and we have partnership with a few industries and academic institutions. MOUs, MOU is also there, and we are offering these courses: BE mechanical, specialization in manufacturing, because we have separate mechanical department. That is, they are offering BE mechanical engineering, but we are offering BE mechanical, specialized in manufacturing engineering, and ME manufacturing, ME welding engineering, ME nanomaterials, and PhD in manufacturing. We are also offering through full-time, part-time also, we are offering PhD. Thrust areas of research: materials joining, surface engineering, synthesis of newer materials, material processing, and manufacturing management. This is about our Center for Material Joining and Research. We have 10 laboratories in our center. So these are the various labs: fusion welding lab, solid state welding lab, plasma processing lab, physical metallurgy, mechanical testing, corrosion testing, and tribology, and modeling simulation, thermal spray, high temperature lab. Center has completed 40 R&D projects worth of 10 crores, and 5 ongoing projects are there. So these are the list of sponsored R&D projects completed. Various funding agencies, not only AST and UGC and DST, DRDO, many agencies are supporting us. We have done so far more than 40 projects. Finally, it's facilities and welding. We have almost all the facilities are there except electron beam welding facility, pulse current TIG, pulse current MIG, friction welding, diffusion bonding, spot welding, and the laser welding, linear friction welding, CMT, ultrasonic welding, plasma arc welding. All these facilities are there. This is the photograph of the welding machines, what we have in our center, major facilities. And then surface engineering is another area we are working. A lot of work is going on in this area. We have facilities for this also, like plasma spraying, HO spraying, and CVD, PVD, tribology instruments are there, corrosion instruments are there. And these are the photograph of various instruments, what we have for the surface engineering field. And newer materials, this also we are working. We recently started working on this newer materials, developing, synthesizing newer materials. For that, we have tubeless sintering furnace, strip casting furnace, tap melting furnace, EBPVD, sputtering machine, high energy ball mill, dilatometer. These are the facilities. And the general facilities we have for testing and characterization. We have the universal testing machine and fatigue testing machine, SCM, and these are the general facilities we have in our department. And with this, I'll close. Of course, I exceeded time because I started at 9:45. I want to complete by 11:15. Exceeded by 10 minutes. Any clarifications? I'm ready to answer. Are you? Please. ask your questions.
Thank you, sir. That was a very informative session on various advanced welding processes, optimization techniques, and simulation analysis. I request the participants to clarify their doubts by unmuting their microphone or by sending a text message.
Chat box.
Sir, let me read out a question in chat box by Ritraj Tamuli. Can we design rotating tool with stationary pin in FSW technique?
Repeat the question.
He's asking, can we design a rotating tool with stationary pin in FSW technique? That's the question.
Yeah, it is possible, but what purpose? It's the pin is no, it's pin has to rotate, then only the steering will take place. Okay, we have pinless tools are there, only shoulder they are using for processing and other things. But whenever you use the pin, then pin has to rotate. If the pin doesn't rotate, the purpose of steering action will not take place. Okay, so that is it's very, very difficult to make, and also it will not give any advantage over that.
Sir, next question again by Ritraj Tamuli. What does Taylor welded blank mean?
So it is the Taylor welded blanks means it's what do you call it? In the automobile industries, if you take the car frame and all, so they have a standard size and standard dimensions. So that will be made by these welding processes. It's at exactly no. It's if you want to make in multiple numbers, they have fixers and other things to make those numbers, and they have a routine welding procedures, and welding specifications are defined, and it will be used for the best example is car doors, and the car the many frames in the cars, structural frames are made by the Taylor welded blanks. So they do it's they do forming as well as welding and machining in all combined together to get a final component in that. That is called the Taylor welded blank.
So the next is friction stir processing is a welding or severe plastic deformation technique?
Yeah, it is a severe deformation. Actually, friction stir welding is a metal forming process, combination of two metal forming processes. It is a combination of extrusion and forging. Okay, it's extrusion means the surrounding the pin, the material is extruded, and forging means between the shoulder and the bottom of the plate, the material is pressed. It's a forging. So it's a combination of two metal forming process, but it is used for joining purpose. That's all. Basically, it is a severe plastic deformation process.
So next is 3 questions asked by Mr. Nachiappan Ramasamy. I will ask one by one. Why in DC there are 2 different classifications and analysis made as DCEN, DCEP? Why not in AC? Here also main is there and neutral is there.
No, it's the AC current, the polarity is changing from negative to changing from negative to positive every half of the cycle. It's a sinusoidal wave. So in the AC current, it is not a constant current. The polarity will not will change every half of the cycle. But in DC current, the polarity will not change. So that is the reason we don't have in the AC current. AC current, there is one, already it is a combination of negative and positive. AC is one half of the cycle, electrode is negative, EN. Other half of the cycle, when the electrode is positive. It is a changing one, that's alternating one. That's why they don't have separate EN and EP in the AC. Because every half of the cycle, electrode will become negative and positive. One half of the cycle it is negative, other half of the cycle it is positive. It is automatically it is changing in the AC. But DC, its polarity is constant, so there is no change in the. That's why they are going for EN and EP there. Yeah.
So the next is DCEN is better, whether it is because of depth of penetration or depth of joining. Generally, this is required by customers.
No. Yeah, electrode negative is better when you use the non-consumable electrode process, non-consumable arc welding process. Because the electrode is negative, heat will be less in the electrode side. The electrode, you want to maintain the electrode life, to extend the electrode life and to avoid the melting of electrode. So you require less heat in the electrode side. So that is the reason they are going for the non-consumable process like TIG welding in plasma arc welding, they go for electrode negative. All other consumable arc welding, they go for the electrode positive because they have to melt the filler rod. They have to melt the electrode. They have to melt the filler wire. So they go for the positive polarity, electrode positive. So that's the reason.
Sir, how diffusion bonding is differ from conventional adhesive or pasting system?
No, adhesive is different because now in the adhesive you are using like now it's adhesive materials you are using, but there is no temperature involved in the adhesive bonding. But in diffusion bonding, we are not applying any paste like things. It is we are applying the temperature and also pressure we are applying. Because of the temperature, the atoms are excited and they are started moving from one location to other location. Transfer of atoms, mass transfer is taking place. Because of transfer of atoms, the metallurgical bonding takes place. But in adhesive bonding, there is no metallurgical bonding. It is only a mechanical bonding that takes place. There is no metallurgical bonding in the adhesive bonding. And also adhesive bonding is low temperature process, but diffusion bonding is high temperature process. So that's a basic difference.
Sir, one clarification by Tejaswini Shekhar. Sir, is it allowed for outsiders to use a facility in your research lab now?
Yeah, we are allowing. So that's why I showed these slides. No, these are the facilities available. It's open to all. If anybody wants to use this facility, you can contact us, and we will charge minimum because the nominal charges are levied. Because now we need to maintain these equipments and machines. So we on charge basis, we allow all the people. People are using it now from outside. It is open to all. Anybody is want to use any facility, you can contact us either through email or by phone. You can contact us, and we'll give. You can use this facility, but we'll charge. Charging is mandatory. It is charged. Each machines, equipments, they have different charges.
Sir, next by Manivannan Ravindran. Sir, do you have friction surfacing machine or any other modified machine to do friction surfacing method?
No, we don't have any friction surfacing method. We don't have friction surfacing machine. We have only friction stir welding machine. Friction surfacing, you required a separate arrangement is required. And I think IIT Madras is the only place where you have friction surfacing facility. Or otherwise, you can contact the RV Machine Tools Coimbatore. So they have the machines because it requires different setup.
Sir, can we do FSW for polymer composite materials?
Polymer, yes, people have tried, but we have not worked on that, the polymer composites. But only problem is the reinforcements and other things will be disturbed, and it's somewhat difficult by doing that in the polymer.
Sir, question by John Rajkumar. In research, how can we use optimization and simulation? In what extent we rely on simulations and which one is the first one to use? Sir, in research, how can we use optimization and simulation? In what extent we rely on simulations and which one is the first one to use?
See, it all depends on your problem. Okay, so first thing is whether you have knowledge on simulation. Simulation means it's a finite element simulation. So if you have finite element knowledge on finite element analysis, then you can go for it. So there are two things. One is 75% experimental work, 25% the simulation work. Okay, if you have facilities, experimental work facilities, then you can 75% you do that and do a minimum of simulation, and compare these two values. But suppose if you don't have experimental facilities for doing experimental work, do the extensive simulation studies using any one commercial software. A lot of softwares are there, as I told, ANSYS, Abacus, Syswell. For welding, you have Syswell or COMSOL. Many softwares are there. Use those softwares and do extensive simulation studies, 75%. So to compare, to validate those the simulation results, do minimum experiments. Okay, for that you can approach where the facility is available and go there and do few samples, few joints, and compare these your results. So it all depends on the availability of expertise and the availability of your the equipments and facilities. You have to decide based on that one.
So can we use an interlayer for solid state diffusion bonding for joining dissimilar metals? Can
Yeah,
we
it is.
use?
It is. You can use it. No, that will improve the bonding strength. But normally, the interlayers will be used when you have two different materials, and the melting point is the difference between the melting point of two alloys are large. Okay, for example, aluminum with stainless steel. So aluminum melting point is 650 degrees centigrade. Stainless steel melting point is 1550 degrees centigrade. So the difference is 900 degrees centigrade. Okay, so if you keep 600 degrees centigrade for bonding temperature, so aluminum will go to the melting condition. It is not a solid condition. So in that condition, in that case, you can go for the interlayers, either silver interlayer or low melting interlayers you can keep, and that will melt and diffuse on both the surface, aluminum side also and stainless steel side also. But generally, if you the melting point is close, for example, stainless steel and copper, it is only 500 degrees centigrade. So no need to go for interlayers. So you have to decide which combination of material. But if it is a solid state diffusion bonding, no interlayer. Interlayer is not required. The liquid phase diffusion bonding, you require the interlayers. If you say solid state diffusion bonding, it is not. You no need to use the diffusion layer.
Sir, could you tell where the IP TIG welding facility available in India?
It is available. IPTIC is available in Welding Research Institute, WRI, Trichy, PHL Trichy. It is available. We also had, but it was transferred to GTRE Bangalore, Gas Turbine Research Establishment. They have one facility. And in Hyderabad, it's a DRDL, Defense Research Lab, Defense Research Development Lab, DRDL, Hyderabad, they have this facility.
Sir, that's all messages in chat box, sir.
Right. Yeah, any other questions, you can contact me. Anybody want to ask directly? Yeah, if there is no questions, thank you for your passion listening. Of course, there was initial technical hiccups. It was delayed by 15 minutes. Please enjoy the other lectures, interact with the speakers, and enhance your knowledge. Thank you. Thank you very much.
Thank you, sir. Thank you for your very elaborative session within a short period of time. Now we'll switch on to the second session by Dr. Pankaj Biswas, Professor IIT Guwahati. The session is on thermomechanical FA analysis on fusion welding process. I will take this opportunity to introduce Professor Biswas. He did his BE from IAEST Shibpur in mechanical engineering. He did his MTech and PhD from IIT Kharagpur. He has 3 patents, 22 book chapters, 75 journal papers, and 65 conference papers. He guided 2 postdoctorate fellows and 12 PhD scholars, 6 completed and 6 ongoing. 32 MTech students and 34 BTech students. He got different awards and honors. He got IEI Young Engineers Award in 2013-14 in mechanical engineering discipline. I would request to Professor Biswas sir for taking over the session.
Thank you so much for giving me opportunity to deliver a invited talk in your this forum. Am I visible? My slide is visible?
No, sir.
Sir, your voice is not clear, sir.
Am I audible?
Now you're audible, sir.
So audio is not clear.
You're audible.
Yeah, no.
Okay, fine.
Yes,
I'm
sir,
just
please
sharing
proceed.
my slide now. Okay.
Yeah. Sir,
Yes, I am sharing.
yeah. Slide. Sir, go to slide share.
Yes.
Slide show, sir.
Is it visible?
Yeah, it's good.
Okay, thank you.
Yeah, you had to hide the. Yeah, stop sharing.
Okay.
Okay, sir.
Stop sending. Okay, no problem. No.
Yes.
problem. Oh no, this is stop sharing.
No, sir.
No. I am doing again. No problem.
Minimize the.
Yes. Allow. It is visible, correct?
Yes.
Okay, thank you. So today I am going to deliver a talk. Actually, this is a very interesting talk, you can say, as this topic is on simulation of welds and optimization technique. That's why I think these topics will be very much interesting to you people, because here I am going to discuss about the detailed methodology, you can say. It's a hands-on training types of session, you can say, because here I'll show you how to do thermomechanical analysis of fusion welding process. Thermomechanical analysis means here I'll show you how to do thermal analysis and how to do thermal analysis for finding out the temperature distribution due to welding throughout the entire weld specimen. After that, I will show you how to do mechanical analysis, or you can say structural analysis, to find out the what it's called residual stress distribution, then what it's called distortion, all the things related to fusion welding process. Here I will show you because just before sometimes Professor Balasubramanian sir already explained a lot of things. He is a very famous person in the field of welding. All of we are very aware about his research work. So he already explained actually to do generally if you don't have experimental facility mass, then what happens, you can go for doing thermomechanical simulation by using some finite element techniques. So here I will show you how to do thermomechanical analysis of fusion welding process by using some commercially available software package like ANSYS, Abacus, or any other software package. Generally, once you learn one of the software packages, then you will get the test, you will get the fundamental, you can say, you will get the fundamental things, what are the things required to do in any other finite element packages, because all the packages have more or less same steps. What I'm telling, understand? That's why here I will show you a step by step how to do thermomechanical analysis of fusion welding process. Now you are well aware that this welding is such a phenomenon. It's a very complex phenomenon. So welding is such a subject where you will get every science related subject, fundamental concept, as well as engineering related subject, fundamental things is required in welding. Like in welding, you will get the test of physics, chemistry, mathematics. In engineering subject, like you will get the here for understanding the welding phenomena, engineering subject like thermodynamics, then heat transfer, then what it's called for structural analysis, here it's required strength of material. So you see design. So most of the things, so welding is such a topics. Here you will get the flavor of all mechanical engineering branches. Like here you will get the generally idea about thermal science. That means then what it's called designs subject. Then you will get the idea about what it's called manufacturing subject. Now I am going to discuss about the detailed procedure how to do thermomechanical analysis of fusion welding process. Now what I have told you, welding is a very complex phenomena. You see, here just first of all, I'm just showing briefly about the flow chart of thermomechanical analysis. Generally, first of all, what we did in welding process, we generally moving a heat source along the weld line. So this heat source contains sometimes what is called molten droplet. Sometimes it does not. Or that is very well familiar to us. That is sometimes it is
No, sir. No,
autogenous.
sir.
Hello.
No, sir. No,
Am
sir.
I-
No, sir. No, sir.
Am I audible? Hello. Hello, Professor Rajkumar.
You are audible, sir. You are audible.
Okay, fine. Thank you. So you see, now I'm going to show you what are the flow chart generally we follow to do thermomechanical analysis. Here you see a step by step here I am showing, then it will be very clear to you. So you see, 1 minute. So first of all, for doing generally thermomechanical analysis, what are the things required to do? So before going to discuss about flowchart about the thermomechanical analysis, first of all, I should tell you what is a welding process. What are the things are there in a welding process? So you see, first of all, we are moving a heat source which may contain only heat source or which may contain sometimes this consumable also. Consumable means the droplet is formed and it's continuously deposited along the weld line, correct? So you see it may contain only heat source, that is autogenous types of welding process, or it can contain separate filler wire also. What I am telling, understand? So you see, depending upon this heat source, what happens and this movement of the heat source, you can say. So welding is generally a transient types of phenomena. Transient phenomena in the sense, here throughout the entire line, generally load is continuously varying from a starting to end. That you can say. How it is varying? Because at a particular location, if you consider at that location, when you apply the load, at that times here the temperature rise drastically. Once the means heat source move away from that point, generally at that location the temperature gradually decreases. So at a particular location, if you consider, there generally your loading, that means temperature distribution, is continuously varying with time. So once something, generally something in the sense on something like load, any types of load in a structure varying with time, that types of structural problem is called generally transient problem. What I'm telling, understand? That means here with time, temperature is varying. Here in case of welding, generally what are the load generally we applied? The load we applied in welding is temperature. So here one thing you should keep it in mind. So as the load here varying throughout the entire time, that means sometime it is heating, then it is cooling. So load is not constant over a time. What I'm telling, understand? That's why this types of phenomena is called transient phenomena. So first of all, we got the idea welding, for doing welding analysis, first things required to apply the concept of transient thermal analysis, correct? So second things, for structural analysis, what we are doing, we are generally applying this time varying load in a structural problem, correct? A structural problem. In that problem, generally what in a structural problem also, you see this temperature we are applying, which is varying with time. So you can say this structural problem is also a transient types of problem. What I am telling, understand? Because here we are applying the load in to get the distortion or residual stress is dependent on time varying load. What I am telling, understand? That things you should keep in. So a structural analysis also is a transient problem. That's why, and here one thing you should keep it in mind, in case of welding process, generally the temperature rise beyond its melting point, because today I am going to discuss about fusion welding process. Fusion welding process means here the parent metal temperature goes beyond its melting point temperature. So here generally whatever the problem we are solving, that problem is based on what it's called, you see what are the structural change first occur due to melting and all. Here you see, due to melting, its plasticized types of phenomena, such plastic phenomena has taken place. Once it cool down, there is a combination phenomena is occurring. That means some portion is contract, that means return back to its original position, some portion does not. What I'm telling, understand? So you see, after welding, generally this welding structure does not return back to its original shape or sizes. Some sort of deformation and other thing is taken place. That means some sort of permanent thing is taken place. So permanent deformation means plastic types of deformation. So in welding, both plastic and due to contraction, that means some contraction is also taken place. That means it's try to return back to its original position. So some sort of elastic types of phenomena is also taken place. So you can say welding is such a phenomena in which you will get in a structural problem both elastic and plastic types of phenomena. That's why welding structural analysis is called thermomechanical elastoplastic. What it's called? Elastoplastic thermomechanical analysis. What I'm telling, understand? Why it is called elastoplastic thermomechanical analysis? Because here both elastic phenomena as well as plastic phenomena is taken place. That's why it is called elastoplastic thermomechanical analysis. Why it is called thermomechanical analysis? Because here the load which we are applying, it's a thermal load. And due to this thermal load, whatever the mechanical changes means like a structure, means a strength, then what it's called hardness, on all the things, whatever the changes occur. What I'm telling, understand? So this is generally called mechanical changes. Now you got the idea that, okay, what is a welding process? So welding process actually is a transient. First of all, it's a transient phenomena. That's why you can in one sentence you can write welding is a transient elastoplastic thermomechanical problem. What I'm telling, understand? So once you go for doing welding analysis, so you can, within a short form, you can write welding is a transient elastoplastic, both elastic and plastic phenomena is taken place. Thermal and mechanical changes is occur. That's why it's called transient elastoplastic thermomechanical analysis. Okay. Now here I am. Now I will just discuss in details how to do this welding elastoplastic thermomechanical analysis. What are the things required to do the simulation? So you know, you can write your code by your own, no problem. By using this following flow chart, you can write your own code, no problem. But what happens to write a code? Generally, it can take a lot of times because already these types of code and its implementation is available in finite element packages. So if you just know the procedure, detailed procedure, how to do it by using some commercially available software packages, then what happens? I think your time will save and your things will be also good. Your outcome also will be good. Because there you can employ, because already a standard means software packages is there. Inside these software packages, all the related things of means welding is generally embedded in a particular types of software packages. If you just can learn how to implement all this formulation used in this embedded software, then what happens? You can save your time. You can improve a lot of things in this field also. Because this software is such a software like ANSYS or Abacus, here you can write your own subroutine, own program, and you can generally implement you can develop new techniques over this platform. What I'm telling, understand? Already existing platform is there. Over this, you can apply your knowledge and you can do lot of things. So you can write your code definitely, but what happens? That code outcome may not be better than this existing one also. What I'm telling, understand? That's why I'm just telling, if you just want to write code, no issue. You can develop some other thing. But what happens? Already existing one is there. There, if you can apply your knowledge and apply your means further interest, then we can get further more and more things. What I'm telling, that's why I am going to show you how to do thermomechanical analysis by using some finite element package like ANSYS or Abacus. So you see, so you know this in first of all, in a thermomechanical analysis by using any types of software packages, first of all, you have to do the modeling. Modeling means like plate dimension, then what it's called well bit shape, everything I will show you. So modeling, first of all, you have to design your detail geometry. That means you have to make your detailed geometry. It can be 3-dimensional, it can be 2-dimensional. Depending upon your choice of what it's called analysis, you should decide. Then after modeling, second part is required to do meshing. Mesh, you know, which is very well familiar terminology in case of finite element analysis, or you can say FE means finite element discretization. Discretization means, now in case of finite element method, means what is finite element method? First of all, you should know little bit. I am just, because I am not going in details about finite element related things. By basic concept of finite, but then also I am just giving you some brief idea so that it should be very clear to you. So finite element discretization means, generally in finite element method, first of all you have to make the model. After that, generally you have to discretize, or you can say you have to divide the model into finite number of division. What I'm telling, understand? That's why this each and every division has a name that is called element. So that's why you can say, so this as you are discretizing, or you can say meshing, or dividing the model into number of small division, that's why it is, and that division number is not infinite number, it has a finite value. What I'm telling, understand? That means you are dividing your model into finite number of division. That's why it is called finite element method. That means, so each and every element have some corner point. What I'm telling, understand? So every element connected with another element. So node to node, you can say this corner point to corner point of every element is connected together. What I'm telling, understand? So if you apply in any particular node a load, so that load will transfer in every node. What I'm telling, understand? So you can detect the response of that nodal output to any other load. What I am telling, understand? Little bit I am just showing here. This is a plate. This is a plate. This is your well line. You see. Now let's you make this plate into finite number of division. I'm just here very roughly I am showing, because here I am just using this paint. So you see. So now you see this, like this is a element, this is a element, this is a element. Now you see this element have a corner point. This is a corner point, this is another corner point, this is another corner point. Now this corner point, this middle corner point is further connected with this element. So if you apply a load, let's say any load at a particular location, at a particular node, you are applying a load here. So what should be the response of this load P with any other node? Here, whatever it is. So you can get the response by using some connectivity types of programming is there. So by using some connectivity types of matrix, you can get the response of that load in any other node. What I'm telling, understand? So that's why this is called finite element method. So in case of welding, how we do this finite element analysis, that I am just going to show you. So first things we have to do the thermal analysis. So for doing thermal analysis, what are the things required to do? So for generally you know in case of welding process, generally we use a heat source. Correct? In case of welding process, we generally use a heat source. Correct? 1 minute. 1 minute. It is better to have. Okay, no problem. We generally use a heat source. This heat source generally moving along the weld line, correct? This heat source generally moving along the welding direction. So that's why this heat source generally you see coming out from a electrode, correct? So this heat source coming out from a electrode, correct? This is the heat source. So this heat source is a, you say it's a distributed types of heat source. What I'm telling you, a distributed heat source. That's why you see sometimes this is distributed heat source. Whatever the heat source model we generally use, that heat source model can be either Gaussian distribution heat source or it can be gold arc double ellipsoidal types of heat source, or you can develop your own heat source model. So that's why you see this heat source, Gaussian distribution heat source means this intensity of heat source varying from center to outer side exponentially. What I'm telling, understand? Like these types of heat source that you already well familiar about Gaussian distribution of arc and all the things. What I'm telling, understand? So it is varying like this. So Gaussian distribution heat source, that's why here I have written already. First of all, you have to choose your means what types of heat source you are going to use. Generally, here one thing you should keep it in mind. In case of thin types or two-dimensional types of simulation, what you can use? You can use Gaussian distribution of heat source. What I am telling, understand? But in case of three-dimensional types of problem, it is better to use a three-dimensional types of heat source model. That can be gold arc double ellipsoidal types of heat source, or that can be different types. Nowadays different types of other heat sources also available. Volumetric types of different heat sources available. What I'm telling, understand? So first of all, you have to decide your heat source model depending upon your type of problem. That means whether it is a two-dimensional case or three-dimensional case. After that, you have to apply your material property. Material property means here you see during welding process, the temperature is varying with time. What I'm telling, understand? It's rise and it's decrease. So it start from room temperature and it's go to melting point temperature, and it's again return back to room temperature. So if you use a constant temperature property here, then what happens? Your result will be erroneous. That's why it is better to use temperature dependent material property. That means throughout the entire melting point temperature, from room temperature to entire melting point temperature, how the temperature is varying. What I'm telling, understand? That thing is better to use. So in case of any types of analysis, you should require some boundary condition. So here also we should use some boundary condition. One is called initial condition, another one is called boundary condition. So in thermal analysis, generally initial condition is when the heat is not applied in this plate. That means when time t equal to 0 in this plate, once the heat is not applied, that means when the time t equal to 0, at that time generally you can say t equal to 0. For t equal to 0, you can write t equal to 0, your whole plate surface temperature, that means plate surface temperature will be how much? Let's say your 25 degrees centigrade. That means room temperature, or you can say atmospheric temperature. What I'm telling, understand? So that is called generally initial boundary condition. Now this initial boundary condition can be different. Let's you apply some preheating in your plate, preheating technique. So at this times, your initial temperature will be preheating temperature. What I'm telling, understand? And let's you apply some furnace heating in your plate. After that, you are doing welding. So in that plate, then your temperature will be whatever the temperature you generally raised in a furnace, that temperature will be your initial temperature. So that temperature or that boundary condition is called initial condition. Now other boundary condition in thermal analysis, generally what are the things we use? So other thermal boundary condition, like here we use generally convection types of heat source, heat loss is taken place, as well as here generally occur some radiation types of losses in case of fusion welding process generally. So that's why the boundary condition here you should apply, that is called convection heat loss boundary condition and radiation heat loss boundary condition. So after doing this, all the things, what are the things required to do? You have to do transient thermal analysis. How the transient thermal analysis is required to do? This heat source is starting from t equal to 0 and it's gradually moving along this well line. So this, how you can model these things, everything I will discuss in subsequent slide in details. How to do transient thermal analysis, I will show you. Okay. Now once you do this thermal analysis, then from here, what are the outcome you will get? You will get the temperature distribution throughout the entire well plate. So once you get the temperature distribution over the entire well plate, how it is? This temperature distribution will be taken place due to this conduction phenomena. So what are the basis of this conduction phenomena? That is also very well familiar to you. In case of welding, generally the basic governing equation used to do transient thermal analysis is called Fourier transient heat conduction formulation. That is very well. So that things generally, that Fourier heat conduction equation generally you can say use to write this transient thermal analysis things in finite element method. What I am telling, understand? So once you get the temperature distribution over the entire weld plate, that temperature distribution generally you have to take as a load in structural analysis. So in a structural analysis, again, in a structural analysis also, to do a structural analysis, you know that a structural analysis again, so before going to discuss in details, first of all, we should know what are the different material property required. So in next slide, it will be better. In next slide itself, I'll show. So again, for a structural analysis, you have to apply the material property, which should be temperature dependent material property, because in a structural analysis, we are applying the load, which is temperature. This temperature generally varying with time. That's why, as this temperature is not constant, that's why here also we should use temperature dependent material property. So in thermal analysis, to get temperature distribution, we use heat. This thing you should keep it in mind. But for a structural analysis, we are not applying heat. Here, whatever the outcome we get from temperature, the temperature analysis or thermal analysis, so by using heat, we get the temperature. So in a structural analysis, we are using input as a temperature. This you should keep it in mind. Okay. Now here also you have to use initial condition, then boundary condition, and we have to do what types of analysis? Elastoplastic analysis. I have already told you why it is called elastoplastic analysis. And here the boundary condition means how you are putting your weld sample, whether it is a just putting over a plate which is simply supported types of condition, or you are generally fixing one end, another end free. So what are the condition you are using? That is called boundary condition in a structural problem. Whether you are rigidly clamped, whether it is a free condition, whether it is a hinge condition, depending upon your situation of plate, you should apply the boundary condition here also. What I am telling, understand? After that, generally you have to apply the load, which is temperature distribution, which you are getting from this thermal analysis. I have already shown here, getting from thermal analysis. So this temperature distribution you have to apply as a thermal load. So once you apply this thermal load in a structural problem, after that, if you just solve it, then you will get a strain, residual deformation, residual stress, everything actually due to the effect of temperature distribution. Now I will explain what are the material property required for thermal analysis, what are the material property required for a structural analysis in detail. Now, generally for doing thermomechanical analysis by using ANSYS, here I am going to show you how to do thermomechanical analysis by using ANSYS finite element package. This similar concept you can apply in Abacus or a deform software, any other software or COMSOL software. There are different types of what is called finite element packages there. You can use the same concept. So first of all, you have to choose your element in the sense for doing thermal analysis, you have to choose one types of element. So this element for a structural analysis, you have to choose another types of element. What I am telling, understand? So thermal analysis, first of all, you should know what is the element. So element, finite element method, generally we will get different types of element. Generally in a finite element package, you see for a particular types of problem, all the formulation generally programmed in a particular location. For thermal analysis, generally for thermal analysis, all the thermal related formulation generally programmed in a particular location, and that location generally gives a name that has different types of name. Like here for thermal analysis in case of welding, this solid 70 is such a element where generally most of the welding related thermal issue, you can say thermal formulation, welding related thermal formulation generally programmed inside this location. What I am telling and that's inside this location. So once you choose this element, then what happens? Whatever the different means program you want to means call during your simulation, that things you can get from this location. That's why first of all, for doing thermal analysis, you have to choose this element, that location from where you will get all the means input programmed. What I'm telling and to do the thermal analysis. Now, once you do this thermal, choose this thermal means solid 70, and you have to do what? You have to do all the basic procedure. That also I will show you in subsequent slide in details. So basic procedure means first of all, you have to choose this element. In this element, generally all the Fourier tangent heat conduction related means formulation is programmed. Then all the boundary condition like conduction, convection, radiation, every boundary condition is formulated inside this solid 70 location. So once you choose this element, you will get all the detail. You need not to means get disruption during your simulation for welding thermal analysis. It is a very well standard and compatible element to do tangent welding thermal analysis. What I am telling, understand? Now this thermal analysis result, you have to shift to another location where you will get a structural related formulation programmed. What I am telling, understand? So that location also generally give a name that is called generally either solid 45 types of element, or nowadays generally for higher version of ANSYS software you will get a element whose this element name is solid 185. So this element generally very much compatible with this solid 70 element. What I am telling, understand? That means once we switch your thermal analysis to a structural analysis, what I am telling, understand? Then generally automatically this compatible element will be chosen. So in this compatible element, again all the structural related formulation is given. A structural related formulation is given in the sense here generally you will get, we know that governing equation for thermal analysis I will show, then a governing equation for a structural analysis also I will show. From here there you will get the idea what are the different formulation is available. So here once you just apply the load in this solids 185 as a thermal load, whatever the response generally you should get from thermal effect, that formulation generally given inside this element you can say. What I am telling, understand? Now just I am just going to show you in case of in case of welding thermomechanical analysis. So before going to these things, my God, where is the thing? 1 minute. Take. Okay, so first of all, for doing welding thermomechanical analysis, first of all, actually you should know what is the governing equation. Here I am just writing the governing equation little bit for thermal analysis. You see, as I am using paint and writing, it may not be good. So you know, for thermal analysis, Fourier heat conduction equation in 3-dimensional case, I am writing here. Let del x square, I am writing del x square. Okay. So plus del 2t by del y squared dot 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 dot. You can say here I am writing directly rho c divided by k del t by del t, small t. So you see, so for isotopic material, generally you see this this K, then rho and C, this is not varying with direction. So here we are doing the welding in a isotopic material like steel. So these are not XYZ bearing. That's why I am just writing right side itself. So here in case of this governing equation, first of all, what should be the material property you should use in your thermal analysis as well as structural analysis. So in thermal analysis, you see, you are generally solving this governing equation to get this temperature. So here your outcome is temperature. What is temperature? Or this temperature you are going to find out. To find out this thing, what are the things required here? The thing required here is, first is this, you see, what are the input is required? You have to apply the XYZ coordinate. That is your model. Okay. Then another things, material property, what are the things required here? Here you have to use rho. Rho is the density. C is the specific heat, so you have to use a specific heat, and K is the thermal conductivity. So during thermal analysis, what are the things required to apply as a input? So the input parameter in thermal analysis is, you are getting the information from this, what is called governing equation. So first of all, you have to use temperature dependent density, then you have to use temperature dependent specific heat, and you have to use temperature dependent thermal conductivity. And how you are applying time here? Here time is generally your heat source is moving with time. That means you are heating and cooling. So heating time you have to apply, and cooling time also you have to apply. So that's why this is, so everything is generally input you are providing like this. So input time, then coordinate, then this material property, everything you are getting from this, what it's called, governing equation itself. So to do any types of analysis, what should be the input material property is required, that idea you can get from governing equation. That you should keep it in mind. Now you are doing some thermal analysis, you have applied thermal conductivity, but you did not apply the specific heat or the density. Then you will not get the result correctly. What I am telling, understand? So to get an output, first of all, you should know what are the input material property you should use. The input material property you can get, what should be the material property you should apply, that idea you can get from this governing equation. This you should keep it in mind. Okay. So this is the input parameter for thermal analysis, as well as for structural analysis. The main governing equation is generally sigma is equal to, that means simple relation I am just showing here. That means stress-strain relationship. So stress-strain relationship is generally sigma is equal to Hooke's law. I am putting here Hooke's law, E into epsilon, correct? Sigma is equal to E into epsilon. So again, this is epsilon is depend on what? Here epsilon is dependent on thermal expansion coefficient, and alpha into you can say delta T. You can say, I am writing like this. So alpha into delta T, correct? So this is the generally, so as I am using this what it's called paint and hand, that's why it is coming like that. I am not writing here. Okay. So you see this so for structural analysis, what are the basic boundary, basic governing equation is there, stress-strain relationship. So here, from here also you will get the idea what should be the input parameter in structural analysis. So in for structural analysis, the main input parameter is Young modulus E. Then for strain, temperature you are putting as a input. This is generally input parameter as a load you are putting. So this is known to you. And another input parameter, material property is required, that is called alpha. Alpha is called thermal expansion coefficient, correct? So these two material properties mainly required in structural analysis. Apart from this thing, here one thing you should keep it in mind, as it is a three-dimensional problem. So here you will get, you have to put your Poisson's ratio. So three-dimensional, because what happens, this epsilon generally will have different component in epsilon x, epsilon y, epsilon z. So you have to apply, you have to put your Poisson's ratio. What is Poisson's ratio? This is your another input. So for a structural analysis, main input parameter is Young modulus, thermal expansion coefficient, and Poisson's ratio. Now you have to see welding is what types of analysis. Welding is elastoplastic thermomechanical analysis. So here there is occurs some permanent deformation. That means here the material goes beyond its yield point limit. So once something goes beyond its yield point limit, then here you have to specify the yield criteria. So yield criteria generally for welding thermomechanical analysis, the main yield criteria for isotopic material is von Mises yield criteria. So once you go for putting the yield criteria, there generally another material property is required, that is called sigma. You have to define your yield stress, correct? You have to define your yield stress value. So you see, so you have to, so what are the material property you have to put in your structural analysis? First thing is your Young modulus, second thing is your alpha, third thing is your Poisson's ratio, and fourth thing is your what it's called yield stage, because here generally permanent deformation types of phenomena is taken place. What I am telling, understand? So these things you should keep it in mind. So for doing thermal analysis, what should be the material property? That idea you are getting from governing equation, that is Fourier heat conduction equation, tangent Fourier heat conduction equation. Then from stress-strain relationship, you are getting the structural input material property. This concept you should keep it in mind. For any types of analysis, first of all, you should know what types of governing equation you are going to use. So based on this governing equation, you have to decide your element, you have to decide your material property. If you miss any of this material property, your result will be erroneous. This you should keep it in mind. Now, for thermal analysis, you know, thermal analysis you are using what? You are using generally what it's called Newton convection cooling. Then you are using Stephen-Boltzmann radiation types of phenomena, correct? So for boundary condition also, you know, some input material property is required. So what is this input material property? Like for convection types of boundary condition, their temperature is there. Generally convection loss, how it is put? Like this is the convection heat loss. Let's QC. QC generally is given as H into T minus T0. Temperature T minus T initial temperature, correct? T 0. So here you see, so this convection types of heat loss, this temperature you are already putting as a load. So what are the input parameter is required for convection loss? This H. So this H is called generally film coefficient or convection coefficient. So this convection film coefficient also you should put in your as a input parameter. Similarly for radiation, you know, sigma into epsilon into T to the power 4 minus T to the power T0 to the power 4 Stephen-Boltzmann radiation types of heat loss. So there also you should put your sigma value, that means Stephen-Boltzmann constant value. Epsilon means emissivity, you have to put your emissivity value. So you see, these are the generally different types of material property required in your analysis. So what are the material property required? That idea how you are getting? That idea you are getting from the basic governing equation as well as boundary condition. This you should keep it in mind. Okay. Now here I am just showing you how to do all the analysis. So first of all, generally in case of thermomechanical analysis, okay, time is there. Thermomechanical analysis, first of all, you have to, in thermal analysis, you have to design your heat source model. So what I have told you, in case of two-dimensional problem, you can use directly Gaussian distribution of work. That is a very well-known formula. For three-dimensional case, you can use what it's called Goldach double ellipsoidal formula. Apart from this thing, you can develop your own what it's called volumetric heat source. Like here you see, this is a well-bit geometry. This is a well-bit geometry. So what happens? Generally, what we used to do, we generally make the well line into multiple number of division. What I'm telling, understand? Like here you see, this is the well line division. You can see here. This is the different small well line division. So this is the well bit cross section. So this is the geometry generally. This is the model we did. This is the model we did where we considered both this this two plate, and inside this, in between these two plate, there is a well bit geometry. Now this well bit geometry we have divided into finite number of division. So each and every division we consider as a what is called constant volumetric heat source. What I am telling you is constant volumetric heat source. So each and every small division we are taking, in that location we are putting the load, which is generally calculated by using this following formula. Following formula in the sense how the formula is coming, little bit I am explaining. This Q is equal to this small volume, in this small volume how much heat is there, that I am going to find out. That in this small volume how the heat per unit volume is there, that I am showing. So you see Q equal to your eta, W is the watt, means W you can write as V into I, voltage into current. So eta VI divided by this small v is generally represent the volume of this a small division of this well bit, you can say. So in this volume generally we are getting the heat input, this you see Q, that is generally heat input per this unit volume. So in this small volume, here we are putting this heat, and after that we generally move this heat source from first element to next element. So there again we are putting the same amount of heat, what I am telling, understand, and we are deleting the heat from this first volume. Again we are putting the third element this amount of heat, and we are generally deleting the rest of the heat from another two volume, what I am telling, understand. So gradually we are putting the load throughout the entire well bit, and we are putting with time how this heat source location is positioned, that we can easily find, what I am telling, understand. That means first we are putting the load in first volume of what it's called a small volume of well bit. There we know the time, that means this time how we are calculating, time we are calculating depending upon the speed of the torch. This time we can easily find out. That means in first location generally time let's time is 0.1 second. So second volume, once the heat source will put there, the time will be let's 0.2 second. So third volume, generally third location, once you put the well, so there the time will be let's 0.3. This way generally gradually your heat source will move, and you are putting the time with increasing order. Then what happens, your load generally you gradually you can apply throughout the entire well bit like this way, what I am telling, understood, the entire well bit. So this is called generally very straightforward technique. For that generally what are the things required to do? Here generally you are putting the consumable heat, consumable types of filler wire. Due to this how much material is melted. So in this molten region generally we are considering throughout the entire molten region we are considering the constant heat is applied. So that much of heat we are applying a small volume, and we are putting time, and gradually we are moving our heat source along the well line, what I am telling, understand. This way generally you can do your heat application along the well line. Okay, so this way you can apply as a heat load in thermal analysis, what I am telling, understand. So once you do this means apply this heat, how the temperature distribution and residual stress distribution is taken place, little bit I am showing. After that I will directly go to how to do it in ANSYS. Okay, so you see, so the thermal property which are required for this analysis, generally I have already told you thermomechanical property. This is generally mechanical property, or you can say structural property. Here they generally required Young modulus, air required Poisson's ratio, then thermal expansion coefficient, and I have already told you yield stress is also required. For a structural analysis, and density generally required in what is called thermal analysis itself, you are putting density. Okay, so in a structural analysis, what are the things required? Specific heat, thermal conductivity, and thermal expansion coefficient. So these are all temperature dependent. Here you see with temperature how it is varying. Okay, so these types of data is already available for a standard types of material. You can get it from published literature. Okay, now you see Here I am showing, this is your heat source. So this heat source, once it start from this location, and it's gradually moving along this line. So once on this heat source moving along this line, how the temperature distribution conducted, you see how the temperature distribution conducted, everything you can get from this. This is the temperature distribution during welding time itself, how the temperature is distributing over the entire weld plate. So after cooling, how it is look like, so due to conduction and other things. Okay, after cooling, how the temperature is look like, here it is showing. So here you see, this is the generally temperature distribution, and how the temperature curve, generally transient temperature curve you can get in case of transient thermal analysis that I am showing. I have already told you, generally here this first black line, this line represents the temperature at weld line, that means center of weld line. Here the temperature is generally higher than the melting point temperature. What I am telling, understand? It's for SS304. Here we did the simulation. We are getting a temperature around 22 to 2400 degrees centigrade temperature. So here you see, so how the temperature is varying, that you can see from here. Initially, generally temperature is rise drastically. After that, it's cool, gradually cooling. What I am telling, and with time, once the heat source moving from that location generally temperature is gradually decreased. So the peak, peak temperature here you can say this peak temperature is maximum at weld center line, and it's gradually decreased away once we away from the weld to away from the weld center line. What I'm telling, and that means 10 millimeter away, 4 millimeter away from weld center line, you will get lower temperature. That I am showing here red color. You see. Again, for 8 millimeter away, how the temperature is distribution, 10, 15, 20, how the temperature is distributing. So you see, this temperature distribution we validated with actual experimental data. At a low, we have measured this temperature data by using thermocouple located at a distance 30 millimeter away from weld center line. And we generally take both experimental, record this experiment data, and we take the data from our numerical simulation, and we compare this data. You see how closely matching with each other. That means this variation within 5 to 10% only. So you see, you can get a very similar types of distribution actually. That means your model which you are predicting by simulation. So whatever the outcome here from here you can get that variation with actual one within a range of only 10 to 5 to 10%. What I am telling, and so that this is a comparison I am showing. So after that, this structural temperature data we take in a structural analysis, a structural model. After that, we generally find out the residual stress distribution. Here you see how the residual stress distribution. Here I am showing the longitudinal residual stress distribution over the plate. So here one thing you can see this. This green color generally represents the tensile types of residual stress, maximum residual stress distribution for SS304. Generally, we know along weld line, this residual stress is tensile in nature. Just away from the weld line, here you see away from the weld line, it is compressive. Compressive means here you see, here you can see this color, that means blue color. So away from the weld line, generally it's become compressive. So maximum tensile stress is near the weld region. It's gradually decreased and it's come to 0. After that, it's generally become negative size of residual stress. Here you see, and gradually it's going to further 0 level. What I'm telling, understand? This you should keep it in mind. So welding residual stress, generally in a welding plate, it's a balanced types of residual stress. That means whatever the proportion of tensile residual stress will be there, the same proportion of compressible types of stress should be there, because it's a balanced types of stress. This you should keep it in mind. Now, how this longitudinal residual stress and transverse residual stress distribution for different types of heat input, here I am showing. Here you can see generally the magnitude of longitudinal types of residual stress is higher than the transverse residual stress. What is longitudinal residual stress distribution? Longitudinal residual stress distribution means the weld line, the direction is called longitudinal direction. This you should keep it in mind. So weld line direction is called longitudinal direction, and perpendicular to the weld line direction is called transverse direction. This you should keep it in mind. So along well line, well line direction is x direction. So along x direction, whatever the sigma x you will get, that is called longitudinal residual stress. Let's y coordinate is transverse direction. So whatever the sigma y you will get after cooling and all, that is called transverse residual stress. This you should keep it in mind. Now here I am just showing a tangent thermal analysis animation that will be very interesting to you, because you see to show this animation things I am just showing here. 1 minute. Oh. It is not. Okay. Okay, it is not moving. I'm just showing here, then it will be more clear to you. Here you can see this is a generally moving temperature distribution. You see, due to welding, this we did by using this ANSYS software only. How this moving heat source is moving and how the temperature distribution is taken place over the entire weld plate, that you can see. So it's a very interesting phenomenon actually, and a very interesting thing. By using this simulation software, that means finite element software, you can get everything related to welding. So this is a very this we did by using ANSYS only, that you can see from here. Okay, now come to the presentation. Here you see, now I am going to discuss how to do the simulation by using ANSYS software to get both this temperature distribution as well as to get the residual stress distribution. Okay, to show in details, first of all you should know little bit what is I am giving you some brief overview of ANSYS software. So you see, in ANSYS software, what is the ANSYS full form? ANSYS means AN represent analysis, SYS represents system. So ANSYS actually is an analysis system. What I am telling, understand? Here generally what are the things we used to do? We generally first of all used to do the modeling part first. We are going to do some beam analysis. So I have, first of all you have to make the model by using modeling techniques, that also I will show you. After that, what are the things required to do? You have to mesh it. You have to divide this beam. This is a beam. You have to divide this beam into a small number of division, and which is finite number of division here it should be, that is called meshing. So this is and every small division here I am showing. This is generally called element. This element corner point generally is called node. So this is node and element concept you can get. Some element you can get the node in between this corner point also. Okay, so there can be middle length of this corner length, generally there can be some element. There are different types of elements are there, finite element method, that once you will do it, once you will practice it on this, you will get every idea. Now in finite element analysis, first and foremost thing is to do convergence analysis. Convergence analysis means that is called mesh sensitivity analysis. To establish, generally you see a little bit idea I am giving. You have a circle. So this circle cross-sectional area, this circle cross-sectional area generally you know, which is a standard formula, that is pi r square. So if you know the r value, or if you know the pi value, your this is generally constant actually by using this analytical formulation, correct? This pi r square. But this area you can calculate by using by putting the generally this corner periphery by finite number of division and make a small triangular element, what I am telling, understand? And finding out the individual triangular area and sum it, and by this also you can get the approximate area of this circle, correct? So this division you can do either from inside of this circle, or you can do by using outside of this circle itself. What I am telling, understand? So here you can see If you just make more and more number of this triangular element, then you can get closer to this actual what it's called, actual pi r square value. So after sometimes, if you further increase this number of division, you will get the very minor deviation with previous pi r, means previous area. What I'm telling, understand? So that area at which you are getting closer to pi r square value, if you do further and further division, your number of element increase, but your this closeness to this pi r square value is not that much extent. What I'm telling, understand? So you can consider that limit at which you are getting closer to pi r square value. That number of division you can consider your optimum number of division. What I'm telling, understand? So for doing any types of analysis, first of all, you should do these types of. So you have to start from bigger types of division to very small division. Once your result will matching with the actual result very close to each other, then you can consider that element number is your optimum element number. What I'm telling, understand? So this is a very interesting formula, phenomena in finite element analysis. Now you can think, sir, if we make more and more division, we can get very closer result to each other. But here one thing you should keep it in mind: if you do more and more division, your computational time, your solution times, your cost and other things will increase drastically. This you should keep it in mind. So that's why you should first do mesh sensitivity analysis, or you can say convergence analysis, at which your result is closer to actual one. At that location, you should choose your number of element division, or you can say size of your element division. That size of element division you should use for further any types of analysis. Okay. Now I have already told you that ANSYS means analysis system. Okay. AN represent analysis, SYS represent system. Now how to do thermomechanical analysis, just I am going to show you in details here. Now this is a black your computer screen. In this computer screen, generally once you install ANSYS software, then there you will get a shortcut of ANSYS software. Okay, that is generally configure ANSYS product, or nowadays it is written APDL ANSYS, something is generally it is written nowadays. So once you double click in this shortcut window, you will get your ANSYS will start. What I'm telling you, you will get another window. So in this window, generally, you have to generally configure your software, you can say. That means, first of all, in launch, here you have to choose what types of analysis you are going to do, and what are the, you can say, what are the license version is with you in ANSYS. So here, generally, there you see this license version, generally, ANSYS Multiphysics is such a license version where you can do most of the types of analysis. That means thermal, structural, dynamic, electrical, magnetic, most of the fluid. So most of the analysis you can do by using ANSYS Multiphysics. So apart from LS Dyna, the mechanical, multiphysics, LS Dyna, a lot of other license version is there also. But what happens here, I am going to choose ANSYS Multiphysics because for welding thermomechanical analysis, ANSYS Multiphysics license version is sufficient. So after that, we have to define our location where we want to save our all data. That is called file management. So once you just go for file management, here you see, I am interested to save all my data. That is working directory, which is C, document and setting, Pankaj. Okay. So in this folder, generally everything will be, that means C, in C, C drive, Pankaj folder, everything will be saved. Okay, that is called file management. So here we are doing, structural thermomechanical analysis. So here you can write your job name, thermomechanical analysis. Okay. Now after that, what are the things required to do? So you see, so see this, let's say here I have written C user. So here working directory I have changed. Here I have written welding simulation 2020, and here job name I have written welding analysis. Okay. So in this welding simulation 2020, everything will be saved. Okay. Now you have to click on run. Here you see, once you click on run, then your ANSYS will start. Okay, so you see this ANSYS software is started here. So now here you see in ANSYS software, this first 5 main menu ANSYS main menu topics is very much essential. This first 5 steps. First one is called preferences. Second one is called preprocessor. Third one is called solution. Fourth one is called general postprocessor, and fifth one is called time history postprocessor. Generally, these steps is given sequentially. You should always keep this thing in mind. You should do you should do your work also sequentially. You should not jump one step to another, after that return back to previous step. That will not helpful. What I'm telling you, that will not generally solve your problem. Okay, that will be erroneous. So first of all, you have to preferences. You have to complete all the steps in preferences. Once it completed, then you have to shift to preprocessor. So in preprocessor, you have to do all the things. After that, you have to go solution. Here, one thing you should keep it in mind. After solution, preprocessor, you will go, it will give you erroneous results. So every steps you should do sequentially. This you should keep it in mind. Okay. Now preprocessor, what are the things here it is required to do? In preprocessor preferences, here you see in preferences, what are the things we used to do? Here you see, once you click preferences here, at that time generally we will get a window like this. Okay. We will get a window like this. So in this window, generally here you see there are different types of option is there. Structural analysis, thermal analysis, fluid float run, so a lot of different things is there. So if we will say here actually in case of thermal welding analysis, we are doing this two, that means a structural thermal analysis. So we have to take this structural and thermal analysis. So if we will not choose this thing, then what happens? It will take all the things together. What I'm telling, understand? So there can be little bit complex types of things in your solution. That's why you should be very specified. You should choose first what types of analysis you are going to do. So after selecting this thing, you have to put OK. Here you see I have chosen a structural thermal and I have put OK. Okay. So after that, in preprocessor generally we have to put all the things. We have to choose our element type. Then we have to use what types of unit we are going to use, or whether it is FPS unit, whether it is a SI unit. Okay, so that unit we have to put. Okay, so after that, generally we have to put our material property in preprocessor. Then we have to do our modeling, and after that we have to put meshing. We have to do meshing. Here, one thing you should keep it in mind. Generally, this modeling and meshing part, modeling and material property, everything should put before meshing. What I'm telling, understand? Let's you put some material property before meshing, and after meshing again you put some material property. So after meshing, whatever the material property you will use, that will not be counted in your analysis. So your result will be erroneous. So always keep this thing in your mind. Before meshing, you should put your material property and modeling details. Everything you should put. Okay. And here unit is a very important phenomena. So in dimension, whatever the unit you should use, that means in modeling, you should use same unit in your material property. Like let's your unit in your dimension as a millimeter. So in your material property, every material property should in terms of millimeter only. In your modeling, if you put it in meter, then what happens? In your material property also, you should put everything is in a meter related things. What I am telling, understand? These things you should keep it in mind. Most of the student, most of the researcher makes wrong here. So putting unit in modeling one types millimeter, but putting material property in another unit, FPS unit, SI unit, meter, or something else. So the result is to come wrong way. What I'm telling, understand? So here I am just showing. So if you click how to do all these things, here I am just showing step by step. Professor Rajkumar, am I going actually out of time? Because I have, hello?
Sorry, nice, sir. Please continue, sir.
Okay, fine. Okay, I'm just doing. Thank you. So you see, so in preprocessor, generally, first of all, you have to decide your element type. I have already told you, generally element type means for thermal analysis, generally, there is some standard location where you will get all the formulation related to thermal analysis. If you will not choose that location, that element, if you choose another element, then what happens? Your analysis you will not get, your result you will not get. That's why here you see, in preprocessor, first of all you have to choose your element type. So in element types, if you click add, edit, delete, you will get a window like this. In this window, if you click on add, you will get another window like this. Here you see, as I choose in initial preferences thermal analysis and structural analysis, that's why you are getting here thermal related element and structural related element. So thermal element here, once you click thermal elements, solid types of element, because we are generally we are going to do welding simulation, which is a generally solid types of element. Generally we choose brick element or cubic element or triangular element. These are all solid. So, and as it is a three-dimensional problem, that's why here I choose solid. So in solid, here you see so many different types of element are there. But it is observed that this 8-noded, which is a brick element, 8-noded solid 70 is more preferable element for thermal analysis. That's why I choose here these things. Okay. After that, we have to put OK. So once we put OK, my element will be choose. Okay. Now we have to put what? We have to define our temperature unit. Here you see. Then thus material property here, first of all material I choose. Now I am putting material property. So in material property, first of all, I have to choose what types of temperature unit we are going to get from this analysis. It can be Kelvin, it can be Celsius. So by default, generally it takes Kelvin. Once you choose here, actually once you click here in this arrow, you will get Kelvin, Fahrenheit, then Celsius. This types of option is there. So here I choose Celsius. After that I have to put OK. Okay. Now unit I choose, SI unit I choose. Now I have to apply material property. Here you see. So use in material property, just step by step I am doing. First of all, I did temperature unit. After that I am putting material model. So if you go material model, here you will get a window, this window, where you can put your all the input parameter. All the input parameter, what are the different types of input parameter? I have already told you. In thermal analysis, generally from the what it's called governing equation itself, you can get density, specific heat, and what it's called thermal conductivity. But similarly for a structural analysis, generally isotopic material property, that means Young modulus, Poisson's ratio is there, thermal expansion coefficient is there, and here we use yield criteria, that is called von Mises bilinear isotopic yield criteria here we use. So all the option is available in this input property. Here you have to define all the input property by using material model. How it is? Like here you thermal. Once you click material property, you will get a window right side like this. So in this, if we click thermal, inside thermal, all the material property you can get. So here you see, first of all, you have to put your conductivity. So if you click conductivity, a window will appear like this. So in this window, generally here only one column window you will get. But here we want to put temperature dependent material property. That means T1, T2, T3. That means 100 degree, 200 degree, 300 degree, 400 degree centigrade, like this we want to put. So how to put all these things? If you click in this button, add temperature, you will get another column. So depending upon your number of temperature versus material property, you can create number of column like this. Okay, there you can put both temperature and Kxx means thermal conductivity. So if you put it and if you just click OK, you will get, it will deposit it and it will show left side. What I'm telling, understand? After that, you have to put a specific it. If you click a specific it, you will get another window like this. There also you have to put add temperature, and at temperature you can put your temperature dependent material property. Then you have to put density. Then you have to put emissivity. Then you have to put convection film coefficient. What I have told you already. Emissivity for required for what is called radiation types of boundary condition. Convection film coefficient required for what it's called convection types of boundary condition. What I'm telling you, so you can put all the things here as a input. After that, if you just generally here itself, you can put your structural material property. Otherwise, during structural analysis, there also you can put your structural material property, no problem. Okay. So here also, if you click structural, you will get all the structural material property list. There you have to click Young modulus. Once you click Young modulus, you will get a table like this. There you have to put your data, and automatically left side it will be whatever the material property will be put, then everything will be represented left side. Okay. Now after that, after putting all the material property, so material, you see everything I am doing step by step. Element type, material property. Now I am doing modeling. So modeling generally you have to here I am just showing how to do modeling. So modeling you can do directly. You can make some volume, okay, or you can start from the scratch. Corner location coordinate you can define every corner location. After that you have to join this corner location as a line, then line to area, area to volume. This way also you can do. So I am showing from the scratch how to do any types of modeling that I am showing. So for generally instead of making a volume directly here, I am just showing step by step. So in modeling, first of all, you have to create the corner point of this of your plate. This is the corner location 1. This location key point here I am just writing in. If we generally click key point, there a window will come that is in active coordinate system. If you click in active coordinate system, another window will come. So here generally key point number here you have to put 1. So if you put 1 here, there you have to put 0, 0. 2 is let's 0, point on. 0, point on is 2. Okay. 3 is let's point on. Let's 100 millimeter by 100 millimeter plate we want to make. Okay. So corner point you can define like this. But here one thing you should keep it in mind. Every time you should change your key point number. Because if you just put your key point number as 1, after that you are just putting the coordinate. So the 0, 0, 0, 1, 0, 2. So is just key point number in same location, this will change. Okay. So you have to change this here. You have to change your key point number every time. This you should keep it in mind. Like here, key point number 1, this is 2, this is 3, this is 4. So depending upon this number, you have to put the coordinate here and here. This you should keep it in mind. After that, you have to draw the line. So after that, how to draw line? So key point is completed. Then I have to draw the lines. Here I am making a straight line. I mean cubic types of plate. That's why you see rectangle types of plate. That's why I am directly generally joining the line. Here is a line, a straight line I am making. So a straight line, once you click a straight line, just you have to select this point, one line will create 2, 3, another line, 3, 4, another line, 4, 5. If we click, automatically the line will generate. After that, you have to make area. So you see line I created. Next step is area. So area I have to make by line. So here you see, if you select area by line, if you choose, just select this 4 line, then okay. If you put, automatically this area will develop. So now you get the area. Why I am showing all these things? You can generate any arbitrary shape by using this generating key point, joining line, arc, or anything. Okay. And you can develop your own geometry. What I'm telling, understand? That's why I am showing how to create a 3-dimensional model from scratch. Okay. Now, now after that, this area is created. Now you have to put thickness. So how you can put thickness? So now for putting thickness, you have to go operate. So I am going operate. Here you see in operate, generally there is the option extrude this area. So if you click extrude area, this area I want to extrude, let's 5 millimeter thickness. Okay. This and this area should be normal. This thickness is normal to this area. That's why I have choose here along normal. Okay. So if I choose here along normal, generally your thickness will be developed. Let's say I have a window will come here. I put this thickness value, and if I just click OK, if I click OK, automatically this volume is created. What I'm telling, understand? This volume is created. So after that, this way generally I made every volume, and I make this 3 different zone of weld plate. So this is one weld plate, this is another weld plate, and this is the welding region. What I'm telling, understand? Generally, after that we have to do meshing. So meshing generally you can do by using this mesh tool. Here you see meshing. A mesh tool, generally there is you can choose your meshing as per your requirement. What I'm telling, understand? What we did generally in welding zone, we generally we did very fine mesh, and away from the welding zone, generally we make very gradually coarse mesh. That mesh generally you can do by using this what is called mesh tool. So I am directly showing this how to get. So this is the our meshing geometry of this weld plate. Okay. I am quickly just showing all the things because I have already missed initially 10 to 15 minutes. No problem. I'll quickly finish it. So this is the meshing view. So once meshing is done, then we have to go to what it's called solution. So in solution, we have to choose the analysis type. So I have gone to a solution. Here I have to choose the analysis type. Here there can be different types of analysis option. It can be steady state, it can be tangent, it can be substructure. So as our analysis is tangent, that's why I choose tangent analysis. Okay. So after that, we have to apply the boundary condition. So here you see define load. Okay, apply. Then boundary condition here I put as convection as boundary condition. So convection I put generally apart from welding location, I put every surface. I choose every surface which is subjected to convection types of heat loss. So after that, if you just put OK, then what happens? Your what is called convection boundary condition will be applied. Then you can put here the radiation boundary condition also. What I'm telling, understand? So after that, we have to apply the load from heat source. So in this, generally you can directly write a subroutine or that is APDL code. ANSYS parametric generally language code is there. So there you can directly write by using concept of Fortran or C coding. There you can provide a loop. Gradually you can move your heat source model from starting point to end point by using these things. So, but here all the detailed step manually I have shown. So once you go through these things, because I will provide you all these detailed things to you, you can get how to do, how to put thermal loading. So you see, first of all, you have to apply the heat flux value. After that, generally here you have to apply the time value. Here you see time value. Then what is the time sub step? Everything you have to put. So after that, generally you have to put the what is called. You have to write your load as a load step file. So in this load step file, generally for one load you have to write one load step, second load steps. So depending upon your number of division, you have to create n number of load file. Okay. So once your n number of load file will be created. After that, once your loading is done, then generally you have to solve your problem. So how to solve your problem? So that things generally for explanation of this loading heat source model loading generally it takes little bit time, but everything is written over there. You can get it from my slide itself. So just I am directly showing. So after that, generally we have to solve the load step file. So we divide our model into 100 number of what it's called 100 number of division. So 100 load we apply. So 100 load step file we generally created in our folder. So this 100 load step file now we have to solve. So how to solve these things? Here you have to go solve from load step file. So this load step file number varying from 1 to 100. So 100 load step we put gradually first position one load, second position another load, third position another load. Gradually we generally complete the entire well line loading deposition, correct? Or you can say material deposition. So after that we have to solve this thing by generally using this option solve from load step file. Here I am solving from load step number 1 to let's 100 number of load step we put, so 100. After that if you just put OK, a solution will start like that. After that, generally in general post processor you have to go. In general post processor you can generally get the pictorial view or graphical representation of your load. And how you can get generally, let's what happens, this is after Sanush solution, this is general post processor. So in general post processor, generally let's I want to read the data by peak. Here you see general post processor read result by peak. Let's I want to get a temperature distribution at a time 15 second or at a load step 15. So at a load step 15, how should be the temperature distribution that you can get here? So at a load step 15, how the temperature distribution is there, you can see. Now here on things you can see this is a very interesting phenomena. Here you see this is here generally we use element death and birth technique to simulate the well material deposition. Simulate the well material deposition means
So audio is not there, sir. So Pankaj sir, your audio is not.
Yes, sir.
Pankaj sir,
You
you
are
are
not
not
audible.
audible.
Might be a technical issue. I think.
Hello? Hello?
Yes, sir.
Session over, sir? Hello?
No, sir. Session is not yet over. Please wait, sir.
Okay.
Speaker is having some technical problems.
Okay. Thank you.
Hello. Actually, in between, somehow I am disconnected. Okay. Now, if you have any queries, anything in your mind, you can ask. Otherwise, actually, yes, yes. Purnami.
So,
Yes.
I'm Giridharan speaking.
Yes, yes.
So I also tried this online,
Yes.
but this thermal simulation,
Yes.
and we had a problem when we go for a multi-pass.
Yes.
When you go to multi-pass, the existing first root pass will do. When you go for second pass, then how this first element and the first row and second row of weld we are making it one, merging
Yes,
that one.
I'm just telling on. It is very, you know, you have to make different bit, bit geometry. So you know, in ANSYS there is an option depending upon your required location you can choose. What I'm telling, understand? So let's fast bit. So during fast bit application, so first of all you have to model your every bit. What I'm telling, understand? Every bit you have to model. Let's first bit, then second bit, third bit, whatever the bit geometry you got, or whatever the bit geometry apply. So every bit you have to model together. After that, you have to choose first your first pass bit. That option is there. So there you have to apply simultaneously load. What I'm telling, understand? And do the analysis. Then for this second pass, you have to choose your second location, all the geometry. What I'm telling, understand?
Okay.
So then second bit shape, you have to apply all the load again further. What I'm telling, understand? So gradually, whatever the location you want, whatever the pass you want to do simultaneously, that pass only you have to choose. There you have to load. But here, one thing you should keep it in mind. That means first, let's for doing fast pass, you are applying 10 number of load. But for second pass, your load step will start from 11 to 20. What I'm telling, understand? So it should not start from 1 to 10 again. Otherwise, what happens? Your result will be erroneous. That means it will mix with previous load step.
And another thing also the temperature, also first pass temperature. When you go for second pass temperature, initially that first pass temperature maybe instead of 2000, now it have come down to nearly 100 or 200, 300. So when you lay above that one, how will you input that temperature in the second pass?
Automatically it will come. Continuously you have to do together, continuously. At the end you have to select all. What I'm telling, understand? At the end you have to select all. You do it for a very small length. Let it be 10 millimeter length plate. There multi-pass geometry you create. Do it for for 10 number of load step is required for one pass. Means one pass. So let's 10 pass you made. So 100 load step will be required. Okay. So what you can do, in between interpass, second pass, interpass time you have to put as a cooling time. What I'm telling, understand? Cooling time, let's for fast run, after that you want to give 10-second cooling time. Cool it. At that time your load will be 0, but that should be counted. That will be a separate load step in between. Let's continuously put 10 load step, 10 load. After that, you want to cool sometimes. So at that time, your load will be 0, but time will be there. What I'm telling, understand? Clear? Then third, again second layer, first step, second step, third step, like. But first step in second layer should start from 11. That means 11 number is over there. So 12 to 21. What I'm telling, understand? Again, you have to put interpass. This way you just do for a small length, you will definitely get. We did it actually for multipass also, we did it.
Then second thing is, what is a welding speed role? How we can inquire welding speed?
Yes, welding speed generally is a very important role. Welding speed you can say decide your time step size. Time step size means generally you see, let's your welding speed 10 millimeter per minute. You are doing 10 millimeter length plate. Okay, 10 millimeter length of weld plate. What I'm telling, understand?
Yes.
So you see, and so to complete your simulation of this 10 millimeter length, how much time it will be required if your welding speed is 10 millimeter per second or 10 millimeter per minute? It will require 60 seconds.
Yes.
Now let's your welding speed is 5 millimeter per what is called 5 millimeter per minute. So now for this same 10 millimeter will require how much time? 30 seconds only.
Okay.
What I'm telling, understand?
Yes.
So in previous case, when your welding speed was 10 millimeter per minute, that times your weld plate was heated for 60 seconds. Full weld plate. But once its speed is increased, what it's called 5 millimeter per minute, then your weld plate will be heated for how much time? Your weld plate will be heated for 120 second, correct?
Yes.
What I'm telling,
So
understand?
yes, you are divide accordingly to timing.
Yes, according to your time, you have to
Divide
put your division, means put your time step during simulation.
And another thing also I want to say about that when you're calculating heat input.
Yes, yes.
But we know the formula, standard formula for heat input calculation.
Yes.
But when you are entering the value in heat input into the model, we have to consider the normal efficiency of the heat transfer, and almost even some part of the radiation also loss will be there. No? Radiation heat transfer also will be there.
Yes.
No?
Yes.
That anything radiation will not consider at all in this process.
Yes, we have to consider. No? We have to consider. That's why you have to put your Boltzmann constant and what is called emissivity. For a particular types of material, Boltzmann constant is very well defined. For a particular types of material, there is different types of emissivity. Emissivity you can get as temperature dependent also. What I'm telling, understand? And for convection also, this film coefficient, for convection coefficient also you can get temperature dependent convection coefficient. But here one thing you should keep it in mind, in case of ANSYS or Abacus, generally simultaneously heat loss and heat input you can give at a time. Otherwise your result will be erroneous. That's why in your welding region, generally, once the heat source move away, at that time, generally in that location, you have to put your convection. But away from the weld region, your heat convection you can put all the times. But in welding region, generally at a time, that means let's you put the convection in all weld region. After that, you are putting the load. Then your result will be erroneous. What you have to do? You have to move your heat source from a particular location. At that location, generally simultaneously you can put convection. But what happens at the convection loss along well line is very minimum. That the very minimum types of thing. That's why along well line, and it's a very small zone. That's why what happens along well line, you can even eliminate the convection heat loss. You just have to put the convection heat loss apart from the well bit zone. What I'm telling, understand?
Yes.
And it is observed that the result is quite good agreement with experiment result within a variation of 10% only. So because I am doing this welding simulation around from 2002-3 onwards. So that's why what happens, I have seen different things. I play different way. And it is observed that different parameter of different effect. Okay. Yeah, tell again. Yeah.
Why this was asking is because if I know completely the answers properly, then I can able to play with that. But since I don't know answers, I have to depend on the other person who knows answers, but he doesn't know about welding.
Okay.
So when you want to communicate, then these problems are coming. When you asking question, you're not able to answer. With options, what options there to do choose means.
You can directly contact with me. You can send your student if they have any problem. What I'm telling, understand? They are always most welcome.
Yes, because you are one of the colleague. You are Sendil Veran.
Yes.
Composite materials.
Yes,
He's also he's also my LA colleague also in Amrita University. So even other one more person is there. So he also from Trinelveri also you could know it. So as you say that one, because why this question came is I had one project in Cameron. Cameron, the inconel alloy when you want to weld it.
Yes.
Multi-pass welding, they are given data regarding sensor data. Multiple locations, they given sensor temperature from different locations from center of the weld. And they asked to make a model and give a prediction as per this output of the sensor value.
Good.
So that when I'm doing this, the sister came, so many like killing, applying return birth elements, and then all the things. We tried everything. We came close to that point, but some of the things were not able to get the results properly. So one of the thing is this, as I
boundary
mentioned,
condition and all the things.
Boundary condition and also the conduction convection part.
Yes.
These all things are not properly.
It has significant effect. I'm just telling you. Let's see what your temperature distribution curve. Somewhere it is very cooling is very rapid. Somewhere cooling is very slow. So everything depends on only one parameter, that is called film coefficient. Convection.
Yes.
You
Convection.
play with this convection film coefficient, you will get exact result with these things. What I'm telling, understand?
Yes.
And let's somewhere you are getting higher temperature, then you reduce the what it's called efficiency, because what happens, whatever the efficiency we generally consider, that efficiency is generally approximate efficiency. You just do some means approximate method, you will definitely get it. Because you are very closer to your result, because as you are getting already. Okay.
But I'm getting the result when I have almost 15-20%. Of course, I only brought it. But I think fine tuning has been required. That's not a problem.
If you want any help, you are always welcome. Actually.
Yes, I am. Okay, still thank you. I'm Dr. Giridharan from professor from mechanical department in Amrita University, Chennai campus.
Okay.
Thank you. Thanks.
Very nice to talking.
Amrita University.
Thank you. Amrita University. Thank you.
Any question? Any other audience?
Good
If you
afternoon,
have
sir.
any, yes.
Sir, this is Dr. Vijay Kumar.
Yes.
Mechanical engineering, Good Institute of Technology, Victoria.
Yes.
Sir.
Yes.
Sir, but today, nice session, sir. I learned a lot, but I have one more doubt, sir. My area is in the friction servicing, but I have not attempted the analysis and the thermal analysis and material flow analysis.
Okay.
So is it possible to apply in the flow analysis,
yes,
metal flow? Because the spreading is taken care of. When the rod consumes, when apply the thrust force, it will be spreading like onion rings.
Actually, it is very much possible. Actually, we are doing here. You can see our publication. We have done lot of things related to friction stir surfacing, friction stir welding, related simulation where we shown how to do material flow model, how to do material flow model, both similar material, both dissimilar material. If you want any help actually regarding these things, you are most welcome to us.
Thank you, sir. Excellent session, sir. I am very much delighted and
actually,
happy.
at the end, I don't know. At the end, actually, I lost my connection. No problem.
I understood, sir. But I learned, sir. It's a beautiful presentation, sir.
Thank you.
Everyone can understand. So please share your contact and mail address, sir.
Everything I will provide you. Already it is with Professor Rajkumar and IIT Guwahati. I will send my details to you.
So I request Professor Rajkumar, sir, it is an excellent session, sir. Please share all the PPTs of the program, sir. Nice session, sir. Huh?
Thank you so much. Thank you so much for your appreciation. Any question?
Sir, we will take quickly one or two questions, sir.
Yes.
Because there are a lot of questions.
Okay. They can ask me by my mail actually. They can send me.
Yes, sir.
Yes.
Sir, one question from John Rajkumar. Sir, how we can use these heat sources in case of pulse current heating, sir?
Yes. You actually, Professor Rajkumar is calling you, Anil.
Manikandan.
Yes, sir.
Sir, heard my voice?
Yes, sir. You are audible, sir.
Yeah. Okay. You can close it this session because almost time is 1:30, about 1:30. We have to start the next session at 2 o'clock.
Okay, sir. We will close this session by answering this question alone, sir.
The next session maybe you can start 2:30, right? So you can give some time because the participants are taking lunch, right?
Yes, sir.
So we will start at 2:30. Anyhow, thank you, Professor, for your very good lecture. So maybe definitely we will contact in future. Thank you for.
Thank you, sir. Thank you, Professor Rajkumar.
Thank you, sir. Thank you. Thank
So
you.
can I leave now?
Yeah, sir. You can leave, sir. Thank you. Mani?
Yes, sir.
Manikandan?
Yes, sir.
Render Maniki. Yeah, you can inform to all the participants. So the next session will start at 2:30 p.m. today.
Okay, sir.
Okay, right. Thank you.
Mani sir, can you share the Pankaj Biswas sir contact details?
Sir, we will share it by the end of the session, sir.
Okay, please.
By
Sir.
afternoon.
Okay.
Yes.
Good.
be your answer? Just write me in comment, okay? I want to see what is your understanding of sampling. Moving ahead, let's say you have one sample. One sample meaning we have 3 columns here, right? Let us consider we have to do some analysis on this particular column, general column. So what kind of analysis can we do on this one column I'm talking about, one sample, okay? Means one column. So we can do a, percentage distribution analysis, for example.
Good afternoon to one and all. The next speaker is Dr. Nachiappan. I take this opportunity to introduce Sir. He has completed his bachelor's degree in mechanical engineering in the year 1997 from Bharatiyar University and BBA in the year 1997 from Engineering College. And he has completed his master's from industrial engineering in the year 1999 from Madurai Kamarajar University. Operation management and MBA operations from Indira Gandhi University. He has completed his PhD in the Department of Manufacturing Engineering in the year 2018 from Annamalai University. For this, he has received his best PhD award, which is Biswanathan Iyer Award in Manufacturing Engineering for the year 2007 and 2008. His research work he carried out in collaboration with the Confederation of Indian Industry and implemented in TTK LIG Limited, Chennai as a part of Industrial Institute Interaction. About his career details, he has worked in so many companies, TVS Rubber, Sundaram Industry, and Prompt Datacom Bangalore. Apart from that, now he is working as a government assistant professor in mechanical engineering department in Tanjavur Government College of Engineering. He has to his record, he has 10 international journals, 35 national journals, 25 international presentation he has completed, and 50 national presentation he has completed. He has received first prize from Best Technical Paper Presentation in the National Conference QQ Quest 2007, and he has received Best Paper Award given by Quality World New Delhi for the title Achieving World Class Status Reducing Variability in a CLMS-A case study paper, and he has a Best Paper Presentation Award given by IISc Bangalore. He has a he has completed best. He has another award for the best participant, best student in the reference course on manufacturing engineering management organized during 2004 by Annamalai University. With this brief note, I welcome Dr. Nachiappan sir to take over the session. Thank you, sir.
Thanks for nice introduction. I think the participants are after lunch to execute in a basic statistics part. It's really a tough job, but what I want to say is please take a paper and a pen and a calculator, because there is a calculation part is there. Unless or otherwise you are not worked out it is very difficult for you to recollect. As my guides and gurus says, I am following the same principles or the things. If you work out with the paper and you can understand the concept behind in it. So as of now, this lecture has been planned towards understanding the basic fundamental concepts. So during the time of June 10th, Dr. Rajkumar inquired about giving fundamentals for this particular FDP. In that aspects, it is basic and fundamental aspects only. I never touch the computer's role into the statistics, how the computer can play or how the computer can work, the background in it, because I practiced, I am sharing what I learn it through the pen and paper. So with that only I am sharing it, because unless or else if you are not strong in the fundamental, it is very difficult for you to survey or you to present what it is and what is the background present in it. It may be simple For example, if I am saying that average, for some people, because of systems are introduced in there, so people feel that it is may not be necessary. Those who are completed doctorates may have well-versed, but those who are doing PhD or doing the research, please be, these are all the areas you need to be understand before you are publishing papers or you are presenting in the conference, where this is the fundamentals. Why I am putting this background of the slide, that you can understand it at the end. So earlier part, the title is given as statistics and analysis. Now adding the new part of, because most of the lectures are oriented towards experiments in the welding, but I never speak about regarding with the weldings. I am purely speaking how, what are all the parameters to be considered during the time of conducting the experiments, and with respect to statistics point of view, what are all the things you need to be caution in executing the experiments. Once you carried out the experiments, you can concentrate on analysis part. If you are not started the experiments, kindly go into these angles before carry out the experiments, because experiments plays a major role that you can understand after go through it in depth. So this is the basic part of me. Without these peoples, I am not here. These are all the peoples molded me to this. And Professor Maiti is the man who is guiding me related with the aspect of the statistics and its fundamentals. And Professor S.M. Kannan is my ME guide. And because of him, I am getting basic knowledge about the DOE. And further application part, I get it from Professor Anantaraman from this Annamalai University, is my PhD guide. So with these three peoples giving the inputs, the problems, what they are given to me, I am sharing it to you. I am not created anything. Whatever they teach to me in the class are making me to give me a solved problem to me to work out. I am preparing from that and I am delivering to you. It is not the mean that I am not the learn it. I am just sharing the part which is learned by others. I am sharing it to you, because my Professor Anantaraman says nothing is perfect and nothing is permanent. In that aspects, in that period, what I learn it, I am sharing it to you. Maybe with respect to application of these current softwares and all, you are using it, you may well versed on these particular aspects. But what I learn it, I am just sharing it to you. Now, coming into the part. This is the content of this today's presentation. Mostly statistics part, then in that descriptive part, inferential part. So even for the people, not only from engineering, may be attended in this particular program, because the title is related to optimization technique. So the optimization comes, then it not mean that only with respect to experiments, where in case of arts and science also, where they are carried out the experiments. For example, Mahamallapuram, where they are studying about the features or comparing one framing of this one particular god and the other god, how they were preparation in the case of stone, how the difference is there. Is there any difference between one particular god and the other god? How it is there? These are all the studies are carried out by the ILO college peoples. So it not mean that application of these only related to our engineering part, they are applied for the arts people also. Before going for the statistics, I am saying that one particular simple example, because you should not sleep it. That's why I am saying this. There is one particular experiment in which a frog is jump. So first case, a man says that cut the first leg and ask to jump. Then the frog jumps. The second leg cut and asking the frog to jump, the frog jumps. And cut the third leg, asking the frog to jump, the frog jumps. Then fourth leg cut, asking the frog to jump, the frog is not jump. Then he made the conclusion that the ear is not working, the ear is connected with the fourth leg. So the data are there, but how you are using the data, how you are interpret the data, that is very, very important in the statistics. Statistics is act as a tool and it will make you to present or the justification for you to present your analysis or approach. How you are using the tool is very, very important. If using the tool, maybe in other vice versa also, I don't want to explain about the other part. How you are using the tools effectively for your validation of your conductation or what your prediction. That is the fundamental. So use the statistics, after learn it fully, then adapt it. Rather than different designs are there, people are suggesting and the paper publication, because of that, don't take it and use that particular tool. Really, why you are using this particular analysis or optimization analysis, why you are using that particular optimization algorithm, what is the need, what is the specialty of it, that is very important before executing this. So then you can select it, right? So now in this presentation, we can see the basics of statistics, the terminology involved, the branches, descriptive, inferential, analysis part, optimization part, then application and the tools and software. I'm not going in depth with respect to the application part and tools and software because these areas which are discussed by many experts in the forthcoming programs. So I am concentrate only with respect to the statistics, experiments and analysis part. So the statistics process of collecting, processing, summarizing, presenting, analyzing and interpretation of the data in order to study and describe the given problem. So it is having three parameters. One is population, variation and how we can reduce the variation. These is the way in which the engineers or managers are using the statistics towards application of it. So what is the importance of it? Condensation of the data, simple, a single line. Maybe you can do many of more than 300 days you are executing it, you are presenting it 180 minutes in the presentation. That's the meaning is that the data, collection of the data, consolidation of the data and removing the data which are not required or we consider as a error, presenting only the data which is required. So this is useful for the viewers or the experts to understand the way you are executing or you are conducting the experiment. It facilitates where the central tendency dispersion and all, I will explain it further. Then limitation part earlier itself I have clearly given. Statistics deal only with respect to quantitative items. It does not study the qualitative phenomena based on the numbers. If the number is there, we can say that it is the best. So they maybe the number alone may be better or the number alone may be the worst case. Based on the decision has been taken. Normally we call it as a type 1 error or type 2 error. That will come under in case of testing of that we can see in your videos. Then statistics is labeled responsible misused by the peoples. The main terminology which are used in the statistics, the data, facts, conclusions made at the drawn, then statistical data which are having you can measure a qualitative data or quantitative data. Qualitative data for the colors, a language, nationalities, or sometimes people say that it is good or the bad. These are all the data also it is there. For example, if you are going and studying about the service of the banks and you go, the service is good or bad, then we can put it or in terms of scales, Likert scales, they are putting 1, 2, 3, 5 ratings. Then they say that it is excellent or medium, good. Like that they are categorized and then they can further studies. Then the population and sample. These two things you need to be clear and basic things need to be understand. Sample is the things what you are going to do the experiments. Based on the samples you are giving a solution or you are suggesting the solution for others towards the population. It is very difficult to study the total population. It means census. It is very, very difficult. The time period taken is more. But the sample, you have to taken something and you can study with respect to that. Then you are estimating or predicting about the population. So the sample drawn and executing the experiment on the samples are very important. So when you are conducting experiments is only for 10 samples or 20 samples, 30 samples. Based on that, you are writing the expression. For example, today morning, Professor VB sir giving the expression about the heat estimation. That equation has been estimated from the sample studied, then validated. That now it is used as a generalized equation. It is from the samples it has been taken. But there is a chance of error is there if the sample is having error. So the sample is how far the sample is there is based on how you are conducting the experiment. What are all the sample? Sample size, it means that number of items you are taken for investigation. How many number of readings you are taking, or how many number of, for example, 12 experiment, 13, that is the sample size. If the sample size is increases, it is very good. You are estimating the population, reality is there. But what is the problem? If the number of experiment is more, then time taken is more, cost is more. So right trials of experiments in right number of places at right ways, it is very important. That's why I am stressing on it. The method of conducting experiment is very, very important. Then the branches in the statistics. First we see about the descriptive statistics. In the descriptive statistics, it is the first part of the statistics. Without attempting or conclude anything that goes beyond the data, we are speaking only with respect to the data what we are having. If we are having 4 data, we must speak only with respect to 4 of these data. We are never coming to the conclusion about the further. Based on the data, inferences has been made related with respect to the data alone. So here you can see there are different cases of the graph is there. It will shows how much correlation is there between these 2 variables. If the correlation is 0, then it means that is the center part. The correlation is 0 where it is scattered. There is no relationship between X and Y. X is horizontal axis and Y is the vertical axis. If there is no relationship based on the data, I am saying that there is no correlation between X and Y. Then if you come under the extreme case of this case, there is a perfect correlation. It means if I am varying the X one particular level, correspondingly the Y is vary. If I am vary the X in terms of 2, then Y is also vary in terms of 2. It means a perfect correlation between X and Y. This here also I am saying this is based on the number of data which is taken for consideration. There is other case where the negative correlation is there. That's the last graph where I am changing the X one part, then instead of increasing, it will be reducing 1. So that is a negative correlation. So now I am came into the conclusion of Y, that what we want, that X what we are giving or what is the input. So that I am using this X, I am saying that what is the status of the Y. Or is there any correlation between X and Y? Yes, correlation is there. If the correlation is there, how much correlation is there? That we are the correlation coefficient, that is all basic fundamental. So I don't want to go into further about the mathematics about finding the correlation coefficient. But only thing, R is equal to 0, it means there is no correlation between these 2. Now, still I am in the descriptive part where basic data I am presenting part, where histogram is there. Even if you are conducting the experiment, you are putting these. This graph you can highlight maybe in the experiment part for industrial engineering, where this is the major aspects people will visualizing, where the majority of the data lies. For that, the people will put it. For example, in the class, we can put it how many number of people are getting how many number of marks. 20 to 30, how many number of people? 30 to 40, how many number of people? 40 to 50. It means majority of the peoples in the class are getting the mark in between 30 to 40. That is the graph we can understand using the histogram. Then this histogram plotting, for that we need to have the data. The data you can see the first part 14, 17, 10, 19. These are all the data, test score of the individuals. After collecting these data, then you have to arrange it in the order. Then for the data, each thing, how many numbers are present. This is the basic things towards it, towards establishing the histogram. So now I can identify where the range is lies between highest and the smallest. So the range is 11. So this is the range, the spread is having 11. From the starting to end, this having spread like this. Now comes into the next part of continuous data. Earlier we are giving individual data. If the data is continuous, then it is not able to prepare an individual graph. Then we can form with respect to class width. That's what we are seeing in the earlier part, where from the range we are fixing from which range to which range. What is the class decide in it? How many number of groups we want it? If based on the number of groups we are preparing it, then we can forming this. So once you frame it, then the lower part is the lower class limit and the upper part is the upper class limit. Then we can say what is the midpoint is the in that particular class, what is the mark. So now using these we are preparing the frequency distribution, how the data has been spreaded. The basic point is the unit of measure what we are taken into, because if you are taking 3 variables or 2 variables, if the unit of measure is differ, one is in terms of hour, in terms of seconds, then the distribution if you are comparing is meaningless. So that's why I'm putting the fundamental part is the unit of measure between the variables must be as of. Only you are comparing based on this particular polygon or the median or the frequency distribution. We want to take a judgment. All the things are taken in terms of, for example, 100 marks. If you put in terms of marks of 100, then we are convert all the things into hundreds. One thing in terms of 20 marks and other subject in terms of 30 marks, another subject in terms of 50 marks, then comparison is not possible, or it is having no meaningless while you are putting this particular frequency distribution. So determine the number of class and finding the width of this particular each graph. What is the width of it? What is the lower and what is the higher level? How many number of observations falling into each class? For that, a simple working examples. Data has been classified. Now these 11 to 15 or 16 to 20 is decided by the researchers, those who are doing the experiment. They can categorize these 11 to 15, 16 to 20, then identified how many number of people. So you may see that this may not be applicable for you to related with, but what I want to say is the people, those who are taking the data in the industrial engineering, for example, if they are preparing how many number of vehicles crossing the toll gate, they want to fix it. What is the charges for the jeep or for the car? For what they are doing is they will prepare a chart from 1 to 2. What are all the number of vehicles moving? From 2 to 3, how many number of vehicles moving? This is one particular type of data. Then other type of data, jeep. How many number of jeep in a day? How many number of car it's in a day? If they put it as a car, or they can categorize it low LCV or HCV. So because this is the data input for them to understand how many number of vehicles are moving in this particular category. So using these data, they are fixing how much charge as the toll gate charges to be fixed up. So this is the fundamental in order to arrive that. So once you are having this data, Then the unit of measure is 1 in terms of 1. So the lower class limits, it is 11, 16, 21, 26, 31, 36. And then upper class limit is 15, 20, 25, 30, 35, and then 40. So the class marks we are preparing. So 11 plus 15 by 2. That way we are getting 13. Similarly, we are doing it for others. So 13, 18, 23, 28. It is for the class marks, individual classes. Then the lower class boundary, we are obtained it. The difference of 11 minus 0.5. So we are getting as 10.5, 15.5. So upper class limit is 15 plus 0.5, so 15.5. So the class width each particular part, the width is 5. So now we are plotting the graph or the histogram. So this is the way the peoples are framing the part of the frequency distribution. I am starting from the fundamental, so I am moving with slow by slow into the core areas. So if you are aware well about it, leave it. If you are, those who are needed can use of it. The next, relative frequency distribution or cumulative frequency distribution or relative cumulative frequency distribution. In case of relative frequency distribution, the table presenting the ratio of frequency of each class to the total frequency of the class. In case of the, now we can see in case of example, the test score is there, 37.5 to 47.5. That is the class interval. We are fixing this is a class. Then we are fixing the frequency. How many number of things is 4. This we can obtain in the earlier. Now we are going into relative frequency. That is relation with respect to previous. And that's what now we are saying in terms of percentile or the NEET or JE or the peoples are preparing the marks based on the percentile system. It means relative with respect to your class students, how many marks you are getting it. If all are written bad, it not mean that 40 marks is bad. Begins here among the 40, who is best? So 37, that will become as a yardstick. For 37, how you are stand or how many number of students you are backing with respect to the topper. So that is called a relative frequency. So in that aspects, the 4 divided by 40, 8 divided by 40, there we are fixing these relative frequency distribution. So the last part is nothing but a simply percentage. This relative frequency distribution can be useful to identify where the majority of the people's lies, 57.5 to 67.5 with respect to relative frequency, it is way more. It means 32.5% of the data are lies in here. Then next comes the cumulative frequency distribution. Earlier we are saying relative frequency. Now we are seeing the cumulative frequency. Here there are two parties there. One is the center of the axis lower part and the center of the axis higher part. For less than 37.5, here you can see the 37.5 to 47.5. I am seeing the data less than 37.5 is 0. Then from 37.5 to 47.5, it is 4. So this is cumulative data. Then from 47.5 to 57.5, that's why I'm putting the, it is one tail. What is that? Only left hand side I'm saying less than part. Less than, it is 37.5, how many number of data? Then 47.5, less than how many number of data? So this is the fundamental for doing the one tail or two tail test. So please be concentrate on these. These 4 and 12, these are all with respect to left side part, less than part. Then there is other part is there, more than part, where more than 37.5, the same data, less than 37.5 is 0. But more than 37.5, all the 40 variables are having more than 37.5. Then from 47.5 to more than 47.5, it means eliminating the 4, then 36. So this is called a cumulative frequency distribution. So the next, earlier we see relative, then cumulative, then comes relative cumulative frequency distribution. Same aspects for the left side and right side attached with the cumulatives.
0 by totals 40, then 40. So each things I am preparing. 4 by 40, 12 by 40, I am preparing it. Then we are seeing what is LRCF and what is MRCF. Next, stages in the statistical investigation. These are all the stages while you are going for statistics data. First part is data collection. The data are the basic fundamental input in order to execute this statistical investigation. The data may be primary or the data may be secondary. The primary data in the sense that you are going to do the experiment, you are physically present and you observe the data from the reading, whatever the equipment, measuring device, you are measuring it. Whereas secondary data from the literature survey or there is an Indian Statistical Institute is there, the data which is there, where we can go and then collect the data. For example, rainfall in 2020, rainfall in 2010, April month, how many number of people are child are born. These are all the data. It is very difficult for you to go and then collect it. The centralized data is there. You can go it and then get it. But these are all called the secondary data. There is a chance of error. It is more in the secondary data because the application or the purpose where they are collected is based on their own convenience. The primary data collected, the time taken is more, cost is more, but your accuracy will be more. That accuracy and all we will see next. Then organizing the data, editing, classification, editing and all, people say that inconsistent. It means morning 3 o'clock you are taking the data, then next day taking the data 3 o'clock, third day, fourth day, fifth day, among these 20 observations, all these data among the 20 observations, only one particular observation is getting exaggerated values, then it means that is inconsistent. It is because of there is a chance of what we call it is in case of quality, there is a called as chance cause and assignable cause. It is because of the assignable cause. It means there is some known function happen. There is an oil leak or the pressure in the oil is deteriorated or the operator has been slept. This is a sporadic loss. It is not a chronic loss. It is a sporadic loss. That losses need to be arrested. But that reading should not be taken into account because the source or the problem or the occurrence of that error has been known to us. If you take it into the consideration, then it will be loss. So you should not taken that into this for consideration. So you have to edit these data. Then classifying the data with respect to the period in which you are taken or the time in which you are taken or the equipment in which you are taken. The classification is very important. So once you are carried out the experiment, it is very good for you to classify it. After collecting the data, if you are classified, then it is difficult. Before going to collect the data, prepare a table, go to that particular machine, then collect the data. Going to that particular machine and collecting the data, you may miss some aspects of the measurement aspect. Then it means you are preparing for previous reading 20, this reading is 22. So it may be in between these. Then there is a chance of conducting experiment becomes useless because you are doing sample. Based on the sample, you are giving estimation about the population. Sample itself, you are making some data, introducing on your own or predicting something introduced, then the chance of error in your final prediction is there. Then next, how you are presenting the data, what is in terms of chart or the diagrams or for the graphs for easy to understand, not for others, for you after some time. Then after that, you can go for analyzing the data with respect to statistics. Then interpret the data, what is the meaning of it? Because many times we are conduct the experiments, but writing the inference is a greater aspect. So why it has been occurred earlier, in the starting part itself, I am giving some inferences, example, joke. So inference writing is very important. For that, practical experience is much needed. That's why I am not taken the example related to welding, because welding aspect, the genius are there in the department of C major, where they are put a lot of literature analyzed by experience. They are preparing their inferences. Why the graph is like this? Why the microstructure like this? Based on their experience of putting their knowledge into this particular aspect. But if it is not, then writing the inference is a great skill. The next comes for analysis of the data, where these three things are very important: central, dispersion, then kurtosis. I mean, where it is dispersed or skewed. So this is the way the histogram has been plotted. Thickness of the output. For example, same what you are saying about the workpiece. How the thickness, what are all the thickness it has been obtained. How many number of pieces has been in this particular thickness. From this we can say majority of the products are having thickness of 3 mm. So it means 60 pieces are in this particular category. By adding these, or we can say the lower limit is 2, that spread has been from 2 to 10 mm. This is the way in which the workpiece has been obtained. So now you can see, before going into this, because earlier itself I used the word accuracy. So before we are going that, this is very important. Normally my Professor Anantaraman says that reliability is very important. For that reliability, this accuracy plays a role, where the shooting point, where we are targeted, and each time where it has been hinted. You can see this. You are hinting it, the target is there, where it has been keep on, you are making any number of times you are doing that particular rifling. But it means that you are never touch the target. You are making many number of rifles. Assume there is 20 set of readings. So 20 set of way, but you are not clearly pinpoint the target. You are focused, but you are not catching it. It means it is inaccurate and you are imprecise. It means your variable taken or the way in which you are conducting the experiment may not finding the real parameter or what you want to say about the material removal rate or the strength that has not been measured in this. The next case, it is accurate, but it is imprecise. It means I can be closer to the point, but all the points are at the different. It means there is no, the gap between the first point and the second point is more. It is not repetitive. First time, second time, third time, it will not hit the target. It is around the target, but it is not exact to the target. So it is accurate but imprecise. Then you can see here it is precise, but it is inaccurate. Deviating from the target. So this is very easy in the industry in order to execute it. It is nothing but shifting. It means the lathe is there. If you putting a tool and we are making a product, the component thick can keep on increasing. The people can easily identify. The supervisor quality engineer clearly identified that. In the night shift, normally this kind of problem will be occur. The operator has been slept out. So continuously it is moving to one particular area. So all the products, you are taking the piece as a sample and inspected, all the pieces are shifted. It means because of tool wear, the operator has not identified the problem. So what we want is always hit the target. So that is accurate and precise. So now, in order to get accurate and these precise quality data, we need these statistics as a role. So for that, the central tendency plays a role. So the central tendency has been measured in terms of mean, median, and mode. Normally, you are conducted the experiments, your research work, and you are saying the output as single value. But single value, it may be occur, maybe a random. So you have to conduct many number of trials and you are preparing where the central tendency lies. So that is the next part. That's the part of reliability is there. You have to, the data is reliable or not. It is one time occurrence. It is repetitive or not. That is very important. So that's why we need to study this mean, median, and mode. So now mean is nothing but the arithmetic mean, adding, or nothing but we can call it as a average. Simply adding of all and how many number of data it is there, mating it. So in the mean itself, different ways the people are doing arithmetic mean, geometric mean, harmonic mean, quadratic mean, then trimmed mean, weighted mean. Based on the applications people are using any techniques, each thing is having its own advantage and disadvantage. Arithmetic mean is simply adding of these variables and divided by the number of the data what we have. But it is very easy to calculate, but consider all the data what we are obtained is having equal weightages. But if the problem is here, extreme values may be there. For example, one data is 2 and another data is 10 and the other data is 11. So 2 plus 10 plus 11. So 22, 24. So divided by 3. The average is comes around 8. The problem is the mean has been towards one extreme. 2 is in one extreme. Other two data 10 and 11 is the other extreme. So it means the center line has been deviated in one particular area, that is towards, because two data are there in the upper area. So the center line has been shifted. So this is the problem to go of conventional arithmetic mean. Now, for that we are doing that geometric mean. So here, in case of geometric mean, we are assigning individual retirement account earned towards annual interest rate. This is the example for you to understand well. It is not average of 5 plus 10 plus 15. It means we are 23.5 is there. So please be understand. Suppose you are having individual retirement account which earn annual interest rate of 5%, 10% and 25%. So if you put the average, then we are getting 1.05, 1.10, 1.25. If you take the average, it means we are getting it 1.13. It means 13%. So it is not a general average of 15 plus 10 plus 25. That way, if you add 5 plus 10 plus 25 divided by 3, then what you are getting is 23.5. So instead of that, here you are putting in terms of percentage and we are evaluating it so that we are reducing the mean towards one particular area, shifting it. The next comes harmonic means. Here, harmonic, because why I am saying different example with respect to your application, you are saying take it. Suppose a boy is riding in a bicycle. Due to topography, because the speed at the initial time period of riding the cycle, the speed is more. After 2 kilometers or 3 kilometers, your speed getting deteriorated. While you are calculating the arithmetic mean, 2 plus 3 plus 4 divided by 3, then it becomes, for example, here you can see, first mile, he can cross is 2 miles per hour. First 1 kilometer or first mile, crossed by 2 meters per hour. Then second, 3 meters per hour. Then final, he can average speed of 4 meters per hour. Then if you take average 2 plus 3 plus 4 divided by 3, then 3, which is incorrect. This would imply that 1 hour it will take to correct. So break it into respect to each component. First split and second split and third split. So first things cover in terms of 20 minutes plus 15 minutes, then walk of 65 minutes. Then we can formulate it 3 miles 1 by 2, 1 by 3 plus 1 by 4. Then we can prepare. The difference is very simple, 3 and here 2.77. But here comes the accuracy plays a role. Yes, simply what we are doing is simply arithmetic average. But while you are conducting experiment, starting part experiment, heat temperature is different. At the end of the stage, the heat will be more. If you take average, the problem is there. Because if time increases, the heat generation will be fast. So it will give the result at the last experiment, the result is different. So if you take average, the problem is there. Then if you go for the quadratic mean, suppose the measurement is 120 minus 150 and 75 volt. So if you take the average 120 plus minus 150 plus 75, if you get the average, the problem is dumped. So for this case and all, we are going for, in the case of electronics, people normally use root mean square values. Among this, taking in terms of squared of each things, then they can take in the average. Not taking the individual's means, and then we are proceeding it. Then next, mean, where the peoples go with respect to arithmetic of top 10%, bottom 10%, taking the center, trimmed these data, and they are doing it. The trim is based on the researchers to handle. Because, for example, night shift, there are people taking the data, day shift, night shift, they can cut down the after 8 o'clock. Morning 8 o'clock, the data has been, you can trim down. So these are all the individuals, those who are collecting the data, has been planned what is the way to trim it. The next is weighted mean. In case of weighted mean, the people assigned weight to each variable and then calculating the mean. That weight allocation is based on the researches towards each variables. For example, in the industry, there are different parameters. Productivity, quality, cost, delivery. These are all the different variables. If I am taking these all the variables equal weightage, then the company will not consider it. If it is related to cost, they will give more weightage. If it is related to morale, then they are giving less weightage. I'm sorry to say this is the reality. For example, if it is related to quality, then they are giving second weightage. So anything is cost. This is what the current industry is visualizing. If you are reducing the cost of 1 rupee, you are taking the project, you are giving more weightage. So there, if you doing the mean, then you should not take equal weightage to all, assigning the weightage to each values, then you are using this particular. But the problem is the weightage allocation, it is a pure subjective factor. For that, there are theories are there, different techniques are there towards allocation of this weightage. For that, our expert professor Dr. C. Muralidharan is there. He is strong in arithmetic and AHP process, where he has learned from Deshmukh from IIT Delhi, where he is introduced this particular technique in Annamalai University. Majority of the qualitative type of research are carried out in case of AHP towards allocation of these weightage. The next part is the mode, where each particular, here I am not doing any calculation, very simple. Which one is repetitive more? That's all. By seeing the data, 23, 22, 12, 14, which one is repeating? 22 is repeating more and 18 is repeating more. Then I am saying that 18 and 22. This is bimodal or multi-modal. If it is single value, I say that where the mean lies. If it is more, then it is bimodal. Then we can analyze where the center lies. Here there is no calculation. By visualizing, making it. But the problem is, many number of times we may not, if the data is not repeated, then we cannot go for the mode aspects. Then go for the median. In case of median, the data you are arranging in terms of the sequence, then making the center values, add it, and they can prepare, that is eliminating the lower part and higher part, making the center in between the value. If it is one value, we can take it. If it is not, adding it, and we can write down to what is the center values. So now this is median, where it is easy compared with that. The next comes dispersion part. So the dispersion is scattering of the data. So in case of central tendency, we are speaking about accuracy. Now we are in case of precision. That dispersion is very important. How the data are spreaded. Precision means how again and again the data are comes into the same level. So measuring the same value again. Precision describes the consistency of the process. This is very important if you take a quality product, because only one time if you achieved, they cannot accept this as a quality, because it's a random chance. You must have to get the same thing again and again for many number of things. That's what industry people says. Normally we say, sir, we achieved 0 accidents. Then the Japanese consultant says it is a random. How many number of days or how many number of periods you are having a 0 accident is there? That is very important. For that, the range will tell what is the difference between lowest and the highest, and the standard deviation mentioned, where the mean lies, it is there. Then standard deviation is more reliable method in order to estimate this dispersion. Before going into the standard deviation, we must know the range, what is the minimum value and what is the maximum value. So the range specifies where the data are lies, but it is very easy to calculate maximum minus minimum. But here the problem is extreme values we are seeing, ignore about all other variables. So for that purpose, we go for the standard deviation, where how far the individual values has been deviated from the arithmetic mean, that is called as variance. So now we are going for this simple calculation for you to understand. The 10, 20, we are calculating the square of it. Then using these, we are estimated what is the mean of it. Then we are estimated the variance. Basics and fundamental, which is required for you to learn the basics. So the variance, you can estimate it using these data, or square root of this, we can estimate the how much dispersion is there. Variance is an efficient estimator. It can be added and averaged. Then comes coefficient of variation. How much the standard deviation divided by the total number of data it is there divided, then we can say as how much coefficient is there. Magnitude of the variation is more or less, that we can identify using this coefficient of variation. So here also this advantage is there. It is very simple for you to understand. Next comes the quartiles, where it is distributed, is the left side or right side, that is quarter part is there. It is basically depend on median part. So the quartile preparation, there are 15 number of data is there. So out of 15 number of data, I'm preparing these. Now next you can see this Boxman plot. For that, this is the fundamental. So the Q1, where the first quarter lies, where the second quarter lies, where the third quarter lies. You are categorizing this data and you are formulating it. So the first quartile is 11. Second quartile is 40. Third quartile is 61. These are all the ways it has been arrived. So this interquartile, the difference between the Q3 and Q1, 61 and 40, this difference is called interquartile, because based on that only the box plot has been plotted. Now you can say how many number of data is available into that particular. That's why I mean not a percentage, it is a percentile. In this, how much amount of, because based on the data it is there. So here now comes the skewness. Skewness comes, the deviation is one direction, either left or right. Here you can see the symmetric or the normal part, the left side and the right side part. Next comes the kurtosis, where it is a positive or negative distribution. Now comes your interesting part, where the Boxman plot is there, where we have peoples are using it. Here you can see the 5 data are there. That's why we call it as a 5 number summary. What is the smallest values? What is the largest values? Where comes the first quartile? Where comes the medians? Where comes the largest part? The data it is there. That is the basic inferences prepared. Once you are preparing this box plot, then there is no need of mean and mode. So this one box plot is enough for you to understand where the center lies, where the extreme data lies, how it has been shifted to lower end or it has been shifted to upper end. Using these, we can understand. That's the purpose of this Boxman plot, or we call it as a 5 number summary. So in previous chart, the histogram is there. The histogram, you can see the trend. But here, in case of this Boxman plot, we can understand where this total line is shifted. Median of this total distribution is shifted into lower end or into the upper end. From which data to which data it is splitted, easy for the visualized people to understand. Next comes engineering, how these statistics plays around. Now only we are coming into the basic part of this program. So engineers can either refining or existing product or the process, or designing a new products. People are doing design of experiments or the experiment is there. Existing product, if you are modifying the process, if it is anything new, then you have conducting these experiments where you can to adapt the statistical thinkings. So now, if we go into the statistics, this is the basic part: hypothesis, t-test, and p-values, and selection of which test. So now, instead of I'm saying I'm collecting from the common open source, so that you can understand with respect to real examples. So before that, I'm saying that null hypothesis, whatever you want, you can write as alternate hypothesis. If there is no, for example, if you are say that variation between two product is there, or if I am doing some method, because of this method, it is better, you can write it as alternate hypothesis. In case of null hypothesis, there is no variation. There is no difference between this method. Your aiming of this hypothesis testing is to prove or aim to reject the null hypothesis. For that only you are working. If you are proved to reject the null hypothesis, it means automatically the alternate hypothesis is accepted. If the bulb is working for 1000 hours, that is the null hypothesis. If then you are doing the testing, if you are statistically tested, if it is not, you are not able to prove, then it means it is working for 1000 hours. Then the null hypothesis will be accepted. If you prove, then whatever is written as null alternate hypothesis, it has been accepted. So for that, now there is a trial is there. Now there are different testing equipments. People are using COVID and all. We are using that injection and the testing is there. For that, there is a video is there. Just you can see it, how they are preparing this testing of hypothesis, application of it, how they are framing it.
Had two drugs we could use to treat it. So we give drug A to 3 people and measure how long it takes each person to recover from the virus. The first thing we notice is that not everyone recovered in the exact same amount of time. Person number 1 recovered the fastest. Person number 2 recovered the slowest. It's possible that person number 1 eats healthy food and exercises and already has a strong immune system, and that helped them recover quickly. And maybe person number 2 doesn't get as much exercise. Or maybe person number 2 has a stressful job or lives where there is a lot of air pollution. The point is that even though all 3 people had the same virus and took the same drug, they did not all recover in the exact same amount of time. And that might be due to a lot of random things like exercise or job stress that we cannot control. Now let's give drug B to 3 different people that have the virus and measure how long it takes them to recover. Again, we see that even though 3 people had the same virus and took the same drug, they did not all recover in the exact same amount of time. And this is probably due to random stuff that we can't control, like how much exercise each person gets, or how much candy they eat. Overall, it looks like people taking drug A took less time to recover than people taking drug B. And when we calculate the mean, or average, value for drug A, and the mean value for drug B, we see that, on average, there is a 15-hour difference between drug A and drug B. So, after seeing this preliminary data, it might seem reasonable to form the following hypothesis. People taking drug A need, on average, 15 fewer hours to recover than people taking drug B. And now that we have this hypothesis, we can test it by repeating the experiment. Now when we calculate the means, we see that, on average, people taking drug A need 35 more hours than people taking drug B. Compared to our preliminary data, this result is very unexpected. In fact, it is the opposite of the original hypothesis. But it is also possible that all three people that took drug A in the second experiment have super stressful jobs and unhealthy lifestyles. And maybe that's why it took them so long to recover. And maybe everyone taking drug B was well rested and super healthy to begin with. And maybe that's why they recovered so quickly. But it is also possible that we mislabeled drug A and drug B and did the wrong experiment. So we repeat the experiment, and again, the results are totally backwards from the preliminary experiment and totally backwards from the hypothesis that we made. So, again, just to make sure we didn't mislabel things, we redo the experiment. And again, these results are the opposite of the original hypothesis. So we just keep repeating the experiment, each time double-checking every little detail. And every time we do the experiment, we get the opposite result of the original hypothesis. So, after doing all of these repeated experiments, where we double-checked every little step, we can confidently
Participants? So we will adjourn for a tea break for 5 minutes. 5 to 10 minutes, we will join back.
Can we start now? Okay. Now, is it possible for you to see the screen?
Yes, sir.
Okay, thank you. Now, in the earlier part, we are seeing in case of videos where the testing of hypothesis is there, we are testing the drug, how far that particular injection or whatever be the thing we are putting it, how far it will prevent. That is required. Normally, people putting injection and don't recover from the disease. It is because of the injection or because of the individual bodies that we want to test it. That you can frame the null hypothesis that there is no role of injection in making the body to recover. Then you can write the alternate hypothesis because of this injection alone, he has improved 30%, he has improved 40%. That you can prepare it. That's why I'm saying whatever you want, you can prepare as an alternate hypothesis. Next video is related with respect to t-test. Please understand the t-test is very explained in a very classical manner, easy for you to understand. Once you are grouping of the data is there, same paired data or unpaired data, for that purpose we are go for the t-test. So here selection of the test, if your data is related with respect to this application, then you can go for the t-test. So before going the test, you can identify how or what application the peoples are executing it. That is very important. So now you can just see these particular videos about the t-test, then we can go out further.
Also known as a t-test for short. What is a t-test? We don't need to get too far into the background, but it was first invented in 1908 by a gentleman named William C. Lee Gozet. He worked for the Guinness Company in Ireland, and they were testing different varieties of barley, and he wanted to know, was there a significant difference in their experiments? And to eliminate bias, he created the t-test. Because he wasn't allowed to use his real name when he published it, he used a pen name and called himself Student. And to this day, we call it Student's t-test rather than Gozet's t-test. But enough of that. What is the purpose of a t-test? It actually has one simple purpose. It looks for significant difference between two sets of data. And that's all it does. It eliminates our bias. When we write a conclusion, it tells us, is the data significant or not significant? For example, I have my class grade book, and if we were to look at it, one of my classes has an 80% average, but another one of my classes has an 83% average. Some people may say that that is a significant difference, and some people may say it's not very significant. The problem is, in science, we want to be objective. We want to eliminate our bias, and we want one mathematical number that'll tell us, is the 83% significantly larger than the 80%? And it helps us get rid of that bias. Now, there's no question that the 83% is larger, but when we look at all the students, it could be just because there's a couple outliers in the other class dragging down the average, and thus not rendering the other class significantly worse. So that's why we do the t-test, is it allows us to get rid of this middle schooler mentality that you just look at the mean to see if something is larger or not. We, in the greater, I would say the more advanced sciences, we don't just look at the mean anymore. You want to get rid of doing that. You want to look at t-testing to see is there a significant difference. What a t-test is going to do is it's going to give us a critical value. It's going to give us a probability. We call this a p-value. Now, what we're looking for is the data significantly different, or is it just random and it's not really much different after all? What we want is a critical value, what we want is a value that is smaller than the critical value of 0.05%. What this means here, or I should say just 5% of 0.05. What this critical value indicates here is that there is a less than 5% chance that the data is random, but greater than 95% chance that the data is significant. What if you had a p-value that was greater than 0.05? Well, what this is saying is that you have a greater than 5% chance that the data is just random and less than 95% confidence that the data is truly significant. So when you calculate your t-test, you're looking to see is it greater or less than the critical value, because this indicates the probability that the data is just random and that there's no significance. So we want as much confidence as possible on a very small p-value to tell us it's not random, it's actually significantly different. Let's take a look at an example here. Let's say you did a calculation and you found, say you did a p-value of 0.52. Is that significantly different or not? And the answer is, it is not significant. This means there is a 52% chance that the data you have is random and only a 48% confidence that the data is significant. Now, it is possible that there is a significant difference, but 48% is not an acceptable standard in science. We want a 95% confidence interval when you look at scientific studies. We want greater than 95% confidence. So how do we look into this a little further? Make sure you understand what a bell curve is. It is a normal distribution of data, and you can see there's usually a mean right around the peak, and there are the outliers on the outside. Standard deviation is nothing more than the normal spread or the normal volume of data that occupies from the mean. So most people, when you look at data, they fall within this range, 68%. And 95% of your data would fall within this range here. Anything outside of that is actually our, call it outlier. So I'll put this down here. You don't need to worry about these numbers, but just be aware that anything in these ranges is usually considered normal. Let's say you were to look at the average height of people in a classroom. Find most people fall within 2 standard deviations from the mean height. But of course, there are always some outliers that are there as well. And this encompasses 99.9% of the entire class because there are even greater outliers out there. What a t-test does is it looks at not only the mean, but the spread of our standard deviation. And we ask ourselves, 2 fundamental questions before we do a t-test. Are you conducting a 1 or 2-tailed t-test? And is the data paired or unpaired? Let's look at that first question. Is the test 1 or 2-tailed? What we mean by that is really how open-ended is our hypothesis or our question that we're asking. Let's say I was looking at a height difference between girls and boys. If I asked the question, is there a significant difference between the height of girls and the height of boys? I'm making it a very open-ended question, and I can look for an answer in either direction, that girls or boys could be taller. But let's say I rephrase that same question, saying boys are significantly taller than girls, or are boys significantly taller than girls? Now I've opened the question, or I've closed the question in one direction, and that means that we are doing a 1-tailed t-test. So likewise, if I was looking at my grade book, if I asked the question of, does second block have higher grades or more significantly higher grades than first block does. That's a one-tailed question because I'm asking it in relation to second block. On the other hand, if I rephrase the question and said, is there a significant difference between first and second block? Well, now, again, we can look in either direction, and our hypothesis or our question is more open-ended than it was initially. So that would become a two-tailed t-test. So make sure you ask yourself, are you conducting one or two-tailed test? And then the next one, is the data paired or unpaired? To prepare this, I have two separate tables here, and let's look at the data. Suppose a class went out and they sampled their heights from the students, and you got boys' heights right there and girls' heights right there. What pairing means is that these two sets of data would be linked in each row. And in this case, there is no linkage here. This is actually going to be unpaired. And I'll show you what I mean by pairing here in this table. Let's say we looked at boys' heights, but we're looking at the same boy at age 5 and at age 15. Well, if you think about it, these are paired. This data corresponds to the same individual. Let's say his name is Jonah. Let's say this boy's name is Zach, and this boy's name is Elliot, and this boy's name is Sam. As you can see, it's paired data. You wouldn't want to switch the table around at all because the numbers need to be lined up with each other. This is what we call paired data. So again, unpaired data doesn't correspond to anything. The numbers can be swapped or arranged largest to smallest even. For instance, I'll do this here, arrange it largest to smallest. And you can see I just made the girls' data largest to smallest, and it doesn't really matter because it's not linked with any of the boys. But if you can't do that with the other table, because they're paired, and it would affect your results or the meaning of it if you were to arrange these differently, then it would be paired. And that's really just something that takes some getting used to, but it's really quite a simple concept. So again, ask yourself, is it one or two-tailed? And is your data paired or unpaired? Let's look at some examples of this here. This is test scores I gave at the beginning of my class, and I call it a pre-test. I later give the exact same test to the same students, and we call this the post-test. So if you take a look, this student got a 32%, which is pretty bad, but he got it at the beginning of the year before he learned anything. Later, he got a 96%, which is obviously really good. So ask yourself those questions. Is the data paired or unpaired? And the answer is this is paired because this belongs to one student here. And again, I could put a name here. Let's say this is Josh. Let's say this belongs to a girl named Sally, and this belongs to a girl named Sarah. Just pick names up on the spot. But if that's the case, and they belong to their respective sample here, this is paired. So we answer that question. The next part we want to ask is, you want to ask yourself, are we doing a one or two-tailed t-test? And here's my question I'm asking. Is there a significant difference between the test scores beginning and end of the year? Because I'm just asking, is there a significant difference? This is going to be actually a two-tailed t-test. On the other hand, if I was to ask the question, did the end of the year perform significantly better than at the beginning, then we are doing a one-tailed t-test because we would be just looking at the end of the year test. But because we asked it open-ended like this, it's going to be a two-tailed t-test. And again, that means we are looking, as a two-tailed t-test, we can look in either direction for the answer. So let's go ahead and do a t-test. I'm going to click on an open cell. You can click anywhere you want. I already filled this p-value in there a while ago. And click up here on function. You're going to have to come under here and look up statistical tests. But because it's under my most frequently used, I just come here and go to t-test or t.test. I'm on Microsoft Excel 2013, by the way. Do your t-test. You want your two sets of data. Array 1 will be our preset, and array 2 will be our post set of data. We said this is going to be a two-tailed t-test, and we said this is going to be a paired test as well, because value is 1.6975 times 10 to the negative 24th power. I'm not going to, well, I guess I can do this real quick. I don't know if that's the exact number of zeros, but if you take a look at it, this is a really small number. And ask yourself, is our p-value significant or is it not? And the answer is, this is very significant. We have an extremely low probability that the data is just randomly like this. And we have an extremely high confidence, greater than 99.99999% confidence that the data is significantly different, which is good because it means my students actually learn something throughout the year. Let's look at another set of data here. These are some grasshoppers. We did some measurements. We weighed the grasshoppers, and we're asking ourselves, is there a significant difference between the mass of the male and the mass of the female grasshoppers? And this is what we got on our distribution. They look about the same. And one person may say, well, the males were higher on average, but again, we don't care so much about the mean. We want the t-test to tell us were the results significantly different or not. So again, to do this, click on a cell anywhere you want. I just happen to put the P equals there just for demonstration purpose. And again, you go here to your statistical test, or it will already be under your most recently used t.test, and you highlight your two sets of data. I'm going to highlight all my males. Make sure you do not highlight your mean or standard deviation if you have that in there, just the raw data. Then you go to agree to, and you highlight that. And the question is saying, is there a significant difference between them? That is a two-tailed question. Again, if we were to reword it and say, are the males significantly larger, that would be a one-tailed question. But we're not. We're just asking an open-ended question like that. And then as far as the type, we're asking, are they paired or unpaired? And if you take a look here, would we put a name or something specific over there? Can we rearrange the numbers and would it affect the meaning of our results? And the answer is no. These are not paired together. We just went out and got a random, I think 20 samples from each male and female, and it doesn't matter what order they're in. They really don't correspond at all to each other. This is unpaired. Look here at our key. Unpaired is going to be 3. And therefore, our p-value is 0.08. Roughly. Ask yourself, is that a significant difference? Are the males or females significantly different than the other? And the answer is no. There is no significant difference. There is a probability of about an 8.3% chance that the data is random, but an almost 93-94% chance that the data is significant. But in science, we want that 95% confidence interval. This here is simply not to the threshold. Let's look at another set of data. Oh, and by the way,
right now you are understand this test. You may use this test for application where you are doing some improvements in the existing things, whether the improvement is occurred is significant or not, because earlier the temperature is this or the strength is this. By doing this action, the strength has been increased. This is by means of random or really the difference is there. For that we can use this t-test. There's a p-value is there in that we are used them, but p-value it means that how far it is significant. But p-value is based on how you are. If you want 95% confidence, then you can say. If you want 90% confidence, you can say, because based on the samples you are telling about the resolution or making the statement about the final population. So here this is up to the researchers how much confidence you are say that. For that the p-value is there. But anyhow, for understanding further, I'm showing this p-value also. I mean how this p-value has been obtained by means of this video.
Hello all, my name is Krishna and welcome to my YouTube channel. So guys, today what exactly p-value actually tells us. Now let's take this particular example guys. Here, this is nothing but it is a space key in your keyboard, right? let's consider an experiment, and you will be knowing that most of the time when we are typing anything in this specific keyword, in this keyboard, most of the times we press the space keys over here at this specific location, right? Yes, there are some people who likes to just press on the sideways, on this side, but most of the time, for most of the people, they just try to press or touch the space key over here, right? Similarly, less number of times are getting touched at this side, at this side, right? Now let's do one thing. Based on this, we can definitely come up with something like this kind of bell curve. This bell curve represents one very important thing. Where there are maximum number of touches, you can see that that is the bulged part. This is how a bell curve in a normal distribution looks like. Where there are less number of touches, that is basically your tail part. And in this kind of experiment, we basically say it as two-tailed test. Okay? Because any statistical analysis we'll be considering a two-tailed test, which will actually provide you two specific regions on the sideways. Right? Now let me just consider that. Suppose if I touch it over here, and suppose for this particular touch, the p-value is 0.01. Now what does this basically indicate? That we are going to understand. This p is equal to 0.01 indicates that if we repeat this experiment, if we repeat this 100 times, then the number of times we will be touching this particular area will be 1. Very simple, guys. If we repeat this experiment, which experiment? Basically touching the space key. If we repeat this experiment 100 times, the number of times we will be touching this particular area will be 0.01, which is nothing but 1 time. 1 time. This is what p-value basically specifies. Suppose if I say that my p-value over here is 0.8, right? So what does this p is equal to 0.8 actually specify? It specifies that if we repeat this experiment 100 times, the number of times we'll be touching in this particular area will be somewhere around 80 times. Right? That is what is the issue that is basically given. Right? Now let's understand and let's define what is this p-value. Okay? If I really want to define what is p-value, theoretically, I can say that it is the probability for the null hypothesis to be Yeah, you have heard this definition, guys. It is a probability for the null hypothesis to be true. Now you may be thinking, what is null hypothesis? Let me define null hypothesis also for you. So I'm just going to write over here null hypothesis. Sorry for my bad handwriting, but I am just trying to explain you the best possible way that I can. Okay. So when we talk about null hypothesis, it treats everything same or equal. That's it. It treats everything same or equal. Now let's take a very good example. A very simple example I'm going to take. Consider that I have a coin. Okay, and this is a fair coin. This is a fair coin. Fair coin basically means that if I'm performing this specific toss experiment 100 times, then based on this fair nature, at least 50 times head should be there, right? 50 times head should be there, or 50 times tail should be coming out, right? So this is a toss experiment. Now in this particular case, if I consider the null hypothesis, I'll be saying that, okay, it is a fair coin. Okay, so I may define my null hypothesis by S0. I may say that the coin is fair. The coin is fair. Okay. Now see over here, guys. It says, what is this null hypothesis? It treats everything same or equal, right? So the coin is fair. In my alternate hypothesis, it will be opposite of this. The coin is not fair. Right? So I have this two information. Now what I do is that I perform some kind of experiment. Now in this experiment, we know that my mean value is 50, right? Because 50 times I'll be either getting head or tail. Now let me perform this particular experiment. Now once I perform this experiment, 100 times I do it. Now out of that, I achieve that I have got somewhere around 60 times I've got head. Now what is 60 times over here? 60 will come somewhere over here, consider over here. 60. Now if I go and try to see this specific region, obviously I'll be able to understand that how much standard deviation away it will be from here, right? And based on my p-value, and always remember guys, based on this particular experiment, it is always good that we should be able to get this particular output or this particular experiment nearer to your mean. Okay, if you get extreme to the mean, extreme right towards the mean at this specific region, suppose, or at this specific region, because remember, this both are symmetrical, right? This region are both symmetrical, right? When this both regions are symmetrical, obviously you can consider that this is my tail end, right? As we are doing a two-tail test. So this tail end will probably have your, suppose this has my 95% of the data, this region, and this probably remaining 5% will be divided as 2.5% and 2.5. So understand, based on this particular experiment, we should always try to get, if I need to make this null hypothesis as true, I really need to get all those values or whatever experiment I'm doing in this specific region, right? In this specific region. And suppose if I consider my p-value as 0.05, we also say this p-value as significance value. Significance value. Now what does this p-value say? Now see, with respect to 0.05, that basically means says 2.5% of data at this side and 2.5% of data at this side. If my experiment comes up with a value, and if that particular value falls in this region, then I am definitely going to reject the null hypothesis, saying that over here you can see that the coin is not fair, the coin toss is not fair, because I'm getting a value which is very, very much far away from the mean value. Now suppose guys, I perform an experiment over here, and suppose my domain expert person has told that, okay, I have to take this p-value as 0.05. Okay, this is basically our tail region which I'm actually dividing based on 2.5% and 2.5. They have told it, okay, and usually this significance, we also say this as a significance value, right? And this significance values are derived by the domain expertise person. Yes, you can take it as 0.10, 0.20, you can take out any values. Now suppose if I perform an experiment where I have now got 67 times head, okay, now I'll just try to, put this particular value, probably plot this particular value with respect to 67, it will come somewhere here. And we know that our region of 2.5% is from here. Now you can definitely see that it is falling at this specific region. Now when we see that, okay, it is falling in this tail region, in short, we can definitely say that our p-value is less than 0.05, right? That basically means our new experiment data that is falling, it is falling away from the mean, and it is so much extreme, I really need to reject the null hypothesis, and we cannot treat everything as same or equal, right? So in this particular case, null hypothesis will be that which is fair coin will get rejected, and we will come to a conclusion that this is not a fair coin. Similarly, if I perform an experiment, suppose I get somewhere around, if I just take an example of 40 times head.
Right. Now, this is the way in which you have to do the test or statistical thinkings in order to execute the experiments. You are getting the readings, but it doesn't mean that always it is better. You must do some statistical test, and you can prove some justification evidence that it is not because of the random. It is really, there is a significance before and after is there. You have to prove it. Then for that, you can write it as a null hypothesis, as there is no difference. and you can write this alternative hypothesis because of this doing injection or because of this treatment, there is an improvement is there. Doing this test and you are saying that the improvement is there. That you can do it t-test or Z test or paired or unpaired. This is very simple, but you have to do this kind of testing. This is the basics that you are doing it for the engineering part. Then comes into the next part of the steps to be carried out, the basic steps to be executed. The first part is develop a clear concise about the problem, then identify the important parameters, then propose the model towards it, then conduct the experiments. Then there I can mention the conclusion steps 2 and 3 again and again. Then you can refine the model, then manipulate the model, then conduct an experiments, then draw the conclusion from it. So now comes the measurement part, because I'm not interested about it, because these are all the procedures where you are already done the experiment. There is a sequence in which executed it. For that procedure purpose, I'm explaining this. Then comes into the measurement part, because these are all the errors where we are not concentrated in our regular part. That's why I'm highlighting this. Measurement is basic fundamental for us to get the data, but how far the variation plays a role in this measurement is there. Either the instrument is having some error, or the person is doing some error, or after the person doing something, doing data entry purpose, the error may be occur. So how we can measuring these particular thing is very important, because these are all the sources of error where the variables have been present. Testing method or the process or the means of parallax error, all these things have been occurred. So how you can quantify this measurement error? There is a real value is there. Adding some error, we are getting the final measurement is there. So as much as possible, if the error is less, then you are picking the real measurement. But if the error makes a major role, then the problem of measurement becomes useless. So that has been identified using the parameter called accuracy or repeatability and reproducibility. So now you can see this has been evaluated using the part of discrimination, where round of time there is a chances of error is there, and this is where the range, normally when you are plotting the graph, people chasing the scale values as much as possible becomes wider, so that you can identify the minute changes. Here you can see the precise and accurate, and it is biased where we are seeing already. So how much it is biased, it is shifted to one particular areas. If it is shifted or biased, then the accuracy becomes reduced. So always I am saying, already I mentioned about the consistent, again and again, repetitive data is there. So the causes of bias is maybe, it is not because of the person, it is maybe because of the burnout instruments or inconsistent in the readings displayed. So here, if you make it repetitive, then taking a total more amount of the data, that's why now the quality people will seek about 6 sigma, where the variation reduction is there. Any number of times, if you're giving an order, first piece, second piece, third piece, any number of pieces manufactured in that particular company, having repetitive the same measurement, any number of pieces if you order. That's what we call it as a repeatability. Same thing in the experiment also. For that, we have to do same appraiser, same part, same instrument. We have to do more number of readings in order to do this repeatability process. There is a linearity error is there. For that, linearity is there. For example, linear measurement length, if you want to measure, there's a chance of linearity towards keep on increasing by means of more number of trials is there. So for that, instead of repeatability, people will go for reproducibility. It means making more number of people doing the same experiment. That is why we call it as an appraiser. So appraiser A and appraiser B and appraiser B is the inspector number 1, inspector number 2, inspector number 3. Measuring the same parameter using the same instrument different times, where reproducibility is there. That we can measure. Here you can see that this is the product. For this product, I am measuring using the appraiser 1, I am measuring 3 readings. I am taking the values. Then appraiser 2, I am taking the readings. Then I am calculating the range, how far, this is the R. R is nothing but the range between maximum and the minimum values. Then I am calculating how the repeatability comes. That is 5.15 times of the sigma. Where the 7.5 is the repeatability. Then I am calculating the reproducibility of R naught, where we can calculate it with respect to the people variance. That is 216.9 minus 216.9 between 216.9 minus 216.3, where I am calculating the variance. It is 0.6. That is based on, this is appraiser 1, the variation is there. This is appraiser 2. So that variation has been verified by reproducibility. So this reproducibility has been measured and tested. We can see the equipment variation and operator variation. Both the variation has been accounted in order to finding the total variation. The total variation is where we can see about repeatability and reproducibility. That's why we call it as a R&R study. If it is under that 10%, fine, it is acceptable. If it is more than 30%, if it is R&R is more than 30%, then we need to be improve the measurement method, or we can change the operator, or we can train the operators. Then come around inferential statistics, where we are used in the experiment part. From this data, we are predicting about the population. Reasonable estimating about the population using the sample. So the data are spreaded, we are extended, called as a trend analysis. Like that, we can trend it and we can extend it. So now this first part is the descriptive part. Now we are seeing about the inferential part, where we are conducting the experiment, or we are doing further experiment, we are doing ANOVA test, and then we are doing the optimization, then we can doing the process. For that, the first part is the experiment part. For that, it is a book where we are excellent and fundamental book is written by the Montgomery. This is the wrapper of it for you. If you want, you can purchase it. Anybody, those who are interested in doing this DOE, this is the fundamental books. Go through it. Each part, it's very, very essential book or Bible for the people doing experiment. Where the basic part of doing experiment is randomization, replication, or local control. Randomization, it is not because of one time, it is repetitive. And if doing that return, doing the experiment, if you are obtaining some data, this is again repetitive if you do any number of times. So that it is having not local optimal, you are going for global optimal. So now if you come for the DOE, where many people are carried out, these parameters are required. What I am saying is the factors. We call it as a controllable variables or not controllable variables. Levels, how much variation you are carried out with respect to each factors. Then what you want to estimate, that we call it as a response variables. Then interaction between the variables is also possible to study. For example, coffee is there, milk and a sugar. These are all the variables. There is a interaction between a milk and a water what you are added. So how much amount of water, how much amount of milk, how much amount of sugar. These three combination you can take the taste of the coffee. If vary of these, then the effect will be vary. Now we can say what is the best combination in order to get the best tea. So now this interaction may be two-way or three-way. It is based on the number of factors involved in it. But the basic important thing is you need to do repetitive test, and replica of the same model is very important. So next, there are co-founding is there, that you cannot hear this particular word in your you can vary one, you can vary the other, but these are having an indirect relationship between these two variables, that we can call this a confounding. So here there is a three phases there: planning phase, execution phase, and analysis phase. This is a basic model. There are controllable factors which are uncontrollable factors. Uncontrollable factors, there are, for example, environment is there, atmosphere is there, humidity is there, that we cannot change it. But even these uncontrollable factors are plays a role in order to convert the input into the output. But you can controllable factors. But this uncontrollable factor increases, the error rate increases. If the error rate increases, you cannot predict the output what it is. So you can formulate the mathematical model, or you can formulate the model using these controllable factors and uncontrollable factors, and you, as much as possible, you are minimizing the error. You cannot make it a zero, but it is possible to predict the output using the input. For that, we are framing these equations or the models. Three things which are most important in order to understand. One is process characterization, another one is process control, another part is the process optimization. The process characterization is because this is a process, theoretically you are framing the model. So now in that model, there are some variables. Using the combinations of the variables, you are formulating the y, the result y, using these x as the input. So this input and output, you are using this equation, you are using this dummy box or the black box, you are formulating it. So now this is called a process characterization. Linking, these are all the input variables. So these input variables are contribution towards the output variable. Now I am changing the input variables, whereas that I am predicting the output variable. Then I can say the process is in control. It means I can control the uncontrollable factors. I can make it the process input variable controllable factors in my mind or in my control. The other part is the process optimization, where I am changing the input variable in which what is the output variable, what we want. That is the next stage. So once you are framing the characterization and control, then we have to go for the next stage of optimization. If you are not clear about the process characterization, then don't go for the controlling system. Final, once you are characterization, then we go to the next levels. So these are all the comparative. This objective is what you are framing with respect to initial stage, screening stage, final stage. But the objective is how the researchers, those who are framing it. So this is a simple example for a soldering machine of your board, in which people may not clear about what are all the controllable factors, what are all the uncontrollable factors. If you want to do the soldering and all, the soldering temperature, the speed in which is all controlled. But you cannot control the thickness of the printed circuit board. The circuit board is there, component you are making a soldering and you are making this. But these are all uncontrollable. Then the type of component used. Sometimes you are using resistors, sometimes you are using compositor, transducers, or their transformers. Each thing you are using it, or driver transformer, where the thickness of the leg will not be same. So these are all uncontrollable factors. The layout of the component, sometimes one resistor, other resistors close together. So here and all you cannot control these. So soldering machines, this process controllable factors is your flux speed, your solder wire. These are all the controllable factors. So there may be other one thing is there. Here also a diameter of the cylinders. Once a new pump you want to design, and then the pump design the diameter where there is a relationship between the input variable itself. For example, diameter of the cylinder, length of the cylinder, even though these are all controllable factors, but there is a relationship between these two also. So that also need to be considered. When you are, there is a next example is there, where we are putting an injection to a person, where the person is having different kind of blood. So a same injection has to be fed to the different people. So in that study, there are the parameters of biological materials, chemical reagents, and other substances are plays a role in order to diagnose which medicine is suitable for this particular person. The same medicine will not be applicable for the other person because the blood group different. So for that purpose, we have to identify which combination. So we have to identify these three variables towards predicting the which product is suitable for this particular person. Human blood, we cannot in control. This is common. So when you are designing the product, this need to be considered. Then now comes a experiment part where please we listen these particular experiments little bit carefulness is there because based on this only I am explaining the analysis part in depth. A engineer want to study the target of the radar space. Two parameters is taken into account. One is ground cutter, other one is the filter they are using. So here he used three different types of cutters and two different type of filters. And he is measuring the response. What is the intensity? It is falling on the radars. So as of now, in the first stage, at the initial stages of this, what we call it as a complete block design. So here I am seeing only with respect to the ground cutter. So there are three different categories I want to conduct the experiment. So I am conducting these ground cutter, low, medium and high. I am taking different observations. For say for example, here 8 readings are taken with respect to each category. This is with respect to 1. Now using these data, I am plotting the box plot. So I am putting this is for the first category, low and medium and high categories. So now I am estimating where the median lies. Here majority of the data for the third category of this. At the third category, high composition of the ground cutter. Here majority of the data where the response will be, target hitting part will be major. Whereas here in case of low grade, the majority of the part here will be lesser. So this is the inference from the box plot we are plotted. Now comes next step. Adding the filter. So same data, this is for the low, medium and high. Then for the first 4 set of reading is for the filter number 1. Second set of reading is for the filter number 2. So now using these, I am again plotted for the filter number 1. How comes these cutter? This is for the cutter 1 and this is for cutter 2 and this is for cutter 3. Where comes the intensity lies? Then similarly for the filter number 2, where the intensity lies. So now using the single line graph converted into plotting of the 2-axis graph, where I am seeing the cutter part lower, then the filter type is 1 type, what this intensity level. Then same this cutter part is at lower category, then filter type 2, where this cutter type category. Now using these I can understand these are all the estimation from these particular data. Now comes next level, where 2 categories earlier we are seeing. Now the third parameter plays, that is the operator. Which operator taking the readings? Now we are taking 4 operators. Operator number 1, operator number 2, operator 3, operator 4. So this is with respect to operator number 1 and this reading is with respect to operator 2, operator 3 and operator 4. Because it's also a place role, but I am not, for your understanding, I am putting these 8 readings, but 8 readings are same reading. I am just remodifying with respect to for you to understand in a different colors. Now you can understand this with respect to filter type. One is for one filter type and other is for the other filter type. So now I am doing this analysis of variance. Earlier we are considered about the block design about the experiment. Now comes into the next part of variance analysis. How far the variance has to be measured, how it has been spreaded, whether these data, what we are spreaded these data, this spread of the data is really there is a difference is there, or the difference is by means of a error in the sample. If there is a difference in the filter type, or the difference is there in the ground cutter, or the difference is there with respect to the operator, how far the difference is there, is the difference is significant or not. For that purpose, we can go for this ANOVA.
So in case of ANOVA, here also we are visualizing with respect to one factor or two factor or combination of these three factors at a time. I am not explaining in detail about this explanation, but please, because these are all the equations what we are doing in that period, we memorize and repeat for the examination purpose. But now the software is there, you can learn it. But before that, how these values are estimated are very important. So for easy understanding, the first part is one-way ANOVA, where there are A, B, C, D. There are 4 different fabrics are there. These 4 different fabrics are cloth wear testing machines are used. So here in one fabrics, this is a data which is obtained. Manufacture cloth wear testing machine to measure the resistance to abrasion of the different fabrics. For A fabric, B fabric, C fabric and D fabric. This is the data has been obtained. So now I am just calculating the mean of each fabric type, then and I am calculating the total. Then first stage in order to estimate is that null hypothesis, there is no difference or there is no weight loss between the different fabrics. So now I am calculating the total number of readings what I am taking is 16 and I am calculating the y square, that is 38.41. This has been obtained by means of adding of 8 plus 10 plus 9 plus 9. So the total will be 38.41. So this square divided by 16, I am getting 92.06, the correction factor. Keep this correction factor now. Then next stage, I am calculating the sum of squares of the total. So this is obtained from, here it is 1.93. So 1.93 squared. Then 2.38 squared. Like that, each individual component, there are total of 16 components. That is ending with 2.25. All these components are squared and added minus this correction factor. So now I am getting this sum of squares of total as 0.76. Now I am going into the individual factor. Here it is only one factor, that is fabric A, fabric B, fabric C and fabric A. So all these things are related to only fabric type. So for each factor, that is 8.76, that is total of this. That is with respect to fabric A and fabric B, fabric C and fabric D. So now fabric A, fabric B, fabric C and fabric D minus this correction factor. Now I am getting at sum of squares. Now the sum of squares of error is this total minus of these factor, because here it is the factors we know, total we know. If anything is in between these, it is because of the error. So now comes into the next part of this table. So in the table, first we are looking about between the factors A, B, C, D, the variation is there. We want to see the sum of squares. How the sum of squares 0.52 is obtained, we are already calculated 0.5212, which is the factors. Now with respect to the error, that we can calculate it here 0.244. Then the total we already calculated 0.76. Now this column is clear. Then next comes the degree of freedom. Degree of freedom is how much freedom is there for variation has been possible to obtain. Here the number of factors is 4, so the variation is possible. Keeping one as constant, we can vary maximum as 3. That is that is 1, 2 or 1, 3 or 1, 4. Like various, keeping one as a constant. So that's why it is here degree of freedom is 3, and that total error, the degree of freedom is total number of, that is A, where we are putting as number of trials, and N we are putting as number of samples. Number of trial is nothing but this: first trial, second trial, third trial and fourth trial. So now N into A minus 1, where we are getting as 12. So now this 0.52 divided by 3, we are getting the mean sum of square. Then 0.24 divided by 12, we are getting is 0.023. Then 0.17 divided by 0.023, you are getting 8.538. That's what I am giving it here earlier. That's here. So now this is a calculated values. If calculated value is less than, here calculated value is 8.5 and the table value with respect to 10%. Here the p value is 0.01. That's what the significance level. 99% confidence. 99% confidence, 1% I am tolerating the error. So, and 3 and 12 is the degree of freedom. Then I am saying the book value is 5.95. So now, if calculated value is greater than the book value, then simply we can reject the null hypothesis. It means null hypothesis, I am saying that there is no difference in the weight loss. So automatically it indicates that there is a variation is there, significant loss is there. So now the question rises, which A is better or B is better, where the significant is there. For that, we can go for the Newman-Lewis test. In that Newman-Lewis test, we are preparing for A, what is the mean? This 2.19 we have obtained here. 2.19 mean, 2.68, 2.415, 2.3. That we are using these as A mean, B I am ascending, I mean increasing order. So B is more. So how far the B is better? It is significant or not? Using the mean, we can easily say B is better. But whether the significant is there or not, for that we can go for this Newman-Lewis test, where I am preparing this mean sum of error. Earlier preparing the mean sum of error, it is calculated, where here it is 0.0203 that you use. Degree of freedom is 12. Now here calculating the standard error with respect to the mean error based on the number of observations. So now this 0.0712 is the mean standard error. Now calculating this p value with respect to 234, it is from the range table from the minimum and maximum with respect to the degree of freedom. It is 3.08, 3.77 and 4.20. So now dividing these with respect to, multiplying these 0.0712 into 3.08, we are getting 3 different values. So now the B and A, that is 2.68 minus 2.19. 2.68 is this minus 2.42. This difference is really significant compared with the 0.49. This is 0.49 with respect to 0.3. Then this is really significant. But 0.236, 0.27, the gap you can measure, it is 0.11. Here it is 0.19. So now what you can infer is B is differ significantly. Whereas here and all, it is the C and A, the variation is 0.04. The significance is, difference is there, but the difference of significance is not significant. Now comes equality of the variance. Earlier we see with respect to mean. Now we are seeing with respect to Barley test, we are using it for the variance difference. But the procedure here, variation I am saying with respect to where we have intensity part, where we can say the difference is significance is there. Then if it is significance is there, then we can accept the null hypothesis. Otherwise, we can reject it. So now, because of time lag, as mentioned by the coordinator, I am just skipping this. Then we are parting with respect to one factor. Now we go into the two factor, where there is a filter is there. This is for one filter. This is for the other filter. Then I am calculating the same sum of squares of the total. Then for the cutter, that is with respect to ground cutter. Then for the filter type. Then I am calculating. Then I am measuring for the ground cutter, filter type, and interaction between these two. This interaction factor, he can visualize with respect to each part. Now I am saying that whether the significance is there or not based on the values, I am saying interaction effect is very minimum, so it is not significant, but the ground and filter type is a significant. Then comes the three factor. What is the third factor? It is the operator. So now this is the next level. There is a B and C. So A, B, C comes means there is an interaction between AB, AC and BC. One more thing is ABC, interaction between these three factors. So for that, there is a different levels, different factors in the same conducting the experiments. So now just please be understand if it is complexity is there. Here there are one particular factor is there, 10, 12 and 13. That is a percentage carbon. Then line speed 200 and 250. This is with respect to one pressure. Then other pressure, same line speed. It means I am taking 1, 2, 3, 4, and then 4, then 8 readings. It's because I am taking 2 replicas. That is 2 times the same readings in order to getting repeatability. Then for this set, I am 2 readings, this set 2 readings, and here 2 readings. Then I am calculating that with respect to AB, AC, and this is for the BC. Then calculated individual sum of squares of the total treatment. This is obtained 571 is nothing but 3 squared, 1 squared, 1 squared plus 1 squared, like that for all. Total 571. So this is for the total. Then for the each individual carbonization. Then for the pressure. Then for the speed. Here I can saying the pressure, it means B factor. I am omitting the B. So A, C and N. It means A, that is A is 3 and C I am calculating is for 2 and N is 2 times replica, that is trials, number of trials 2. So that is 3 into 2 into 2, 6. So it is 2 factor. So it is, that is, here it is 3 into 2, 6, 6 into 2, 12. So like that, I am doing it for all, then preparing this particular chart of the ANOVA. Next comes the special designs where you are, I am not going here in depth, but please be understand the basic part. While you are doing the factors, lower and higher, you are preparing this. While you are having a 3 factors, it is cuboid. So while you are reducing the number of experiment, please be very careful. You are converting the 8 experiment instead of 8 aspect, you are going for 4 aspect. Now you are visualizing from the top or from the visualizing from the side views. Here only 4 factors, here 4 factors, but reality it is 8 factors. So it means if you taken here, then it comes A and B plays a role. While it comes here, it comes B and C plays a role. So reducing the number of experiment is very, very important in choosing it. For that, people go for central composite design. That are all advanced stages. Normally, you cannot go in for central composite design and all during the initial part or the screening experiments. So there are some special design is there, the latent square design, where combination of these aspects, individual threat is there, operators plays or method is plays a major role. Here also I am visualizing these with respect to parameters. Then robust design, people using L4 orthogonal array, or this is with respect to levels and this is with respect to the parameters. So here these are all standard data. You have to use which one, where if you are L8, whether the number of experiment in order to execute this. These all the standard arrays, this is available. Use these, but the order in which the conducting experiment is very important. This is the first experiment you are conducted. All the
Nachi, Dr. Nachiappan. Hello. Dr. Nachiappan.
yes, Rajkumar, please.
Yeah, your mic is muted. Yeah, now it's okay. You can present now.
Is it okay?
Now it's okay, right?
Okay. Now, in case of experiment, the problem is there. All the case, it is not no need to go for the final optimization. Here, in this particular case, the industry is checking in the shampoo is there. They want to fill up the shampoo inside the packet. So they don't want to increase the mass. If it is mass increases,
Sir, excuse me. Okay, thank you.
So here the mass increases, it is a loss. If the mass reduces, the customer complaint is there. So if they are concentrating on the both, the fill up the quantity of the shampoo inside the sachet packet. So here the variable thing is the suction height, suction tube length, viscosity of the liquid and the voltage applied. So now these parameters they are analyzing and preparing. Now they are finalizing. This is with respect to factor A. Factor A is with earlier we are finalizing. Factor A is suction height. So if you want to minimize the mass, fix it at the level 2. If you want to, then for the factor B, you want to fix it. This is the condition we are giving into the shop floor using the DOE. This is called process characterization. This is the first level. I am not going for the next level of process optimization or robust design. This is the first level of process characterization. Next, in case of nested design, because these are all the special design, it is applicable for with respect to each cases. There are some CDs.
Sir, excuse me. Kindly make it full screen, sir.
Is it okay?
No. Still it does not come. Okay. Now it's okay, sir. Thank you. Thank you.
Right. Now, there are seed is there, tree is there, forest is there. There is a relationship between tree, seed and the forest. Even though these three are the variables, but one is depend on other. For that case, you have to go for this nested kind of design. Here you can see there are three different forests. Each forest you are plotting different trees. Each trees there are seeding is there. So this is relationship between each factors. So here you cannot use for a conventional Latin soil design. Here you can go for the nested design. So now this variation understanding, if you take this mean, then these are all the obtained data about, for example, you take growth of the trees or the replica of the final output. These are all the outputs. But I am taking the mean of these, then I am putting it, this data is related with respect to the trees. So this is with respect to the forest. This is with respect to the seed. So now among this mean is the final mean. So this nested design going for protruded with respect to one, with respect to the other, with respect to the other. So this is very careful why you are going for which category, which one plays a role. A seed plays a major role, or trees plays a difference between trees is there, or difference between seed is there, or difference between forest is there. So that you have to be understand based on the application, you have to choose the design. Then next comes the design selection. So now I am putting up with respect to my experience, I am putting this particular framing of this particular chart. If you go for a screening type, then with full factorial or fractional factorials, then it will be depend on the number of factors and number of levels. Then type of design, full factorial or central composite design. For that, these levels and factors is based on the researchers, those who are conducting the experiments can finalize them framing the designs. Then further after conducting these, you have to see which level, whether you are doing screening or modeling purpose or optimization purpose. If you go for optimization, you can go for response surface. If you go for modeling, go for the boxman. If you go for screening, blanket burner. So each things where you can very careful in choosing the designs. Then comes for the next part of regression. Already, the coordinator Dr. SRK is going to explain in detail, but as a part of the basics, I am saying the regression in the, we are predicting the future of Y using the X. But X is known variable which is in our control, but Y is the result. There are something which is not in our control, uncontrollable factor as a error. So Y is equal to X plus E, or E is nothing but the error. So now this x has been varied, the y is varied, fine, it is directly proportional. If it is vice versa, then the component of error plays a role. But there are certain things there, dependent variable, independent variable. This dependent variable is, it is what we are vary with respect to, which is in our hand. Independent variable, which is not in our hand, but it is a variable. So here you can see this intercept. I will explain the next slide. This is the general equation, same thing what I am explained earlier. Y is equal to x plus c. I am adding y is equal to mx plus c. Little bit increasing the same concept. M is nothing but the slope. That is how far the x is vary, the y is vary. If I am vary the x, how the y is vary. If it is directly vary, fine. If I am vary x by 2, then I am vary by 4 or 5, then it means 2 into 2 plus 1. So the 2 is nothing but the slope. So this is the m. This normally we call it as, in case of exponent we call it as a coefficient. For that, this is a fundamental. So this c is a constant, which is, otherwise we call it as a error. As much as possible, the c minimization is better. So now, after we are framing the equations, the next part is how far it will be really predicting. That we call it as a prediction and reality. And with respect to prediction, there is a y is there. But reality, by conducting again the experiment by setting the same variable, earlier I am saying there is a shampoo filling. I am saying this is the level you have to set it. I am giving it to the shop floor. The shop floor they set it. But again, the problem is there. I am saying the mass to be fill up is 2.2 grams. But the reality is 0.25 grams. Then it means 0.05 grams to fill up in the settled condition. But that error or the difference is significant or not. Is it acceptable or not? For that, again also I am going for ANOVA. Then I am checking whether the difference between a prediction of my equation and the reality, is it acceptable or not. So for that, I am giving a simple example. There is a house we are purchasing and there is a square feet. In Chennai and all, they are putting a square feet, there is a rate is there. But there is nothing called 0 square or 10 square feet. The cost will be there. So there is a minimum cost is there. That is called such a y-intercept or called as a slope. That is always it is there. So that will be there. Then plus based on the square feet added, this additional cost will be there. So this is for you to general understanding purpose I am saying. This 98.24, irrespective of any number of square feet, you take 400 square feet or 600 square feet, this is constant. So with respect to square feet, they are varying the charges. For example, the land cost and all, this is the standard. So here, this is the variable things are consumable or variabilities. This is vary with respect to square feet, what you are saying you are purchasing. So based on this, you are further extended. This is the line what we are calculated. Then here you are extended for the other square feet. If it is less, what is that? So now I am explaining that concept here. You can see this is the estimated value. This is the actual value and this is the estimated value. Now we can see how much variation is there. That we call it as a sum of squares of the error. This we can already predicted. Sum of squares of the residuals, what we are find out from the regression, we find out this is the values. So now this total is the sum of the squares. So it inclusion of this and this. Here by means of seeing itself, you can see the error value is more compared with this. So this total will be predicting the prediction of this particular individual regression plus error. As much as possible, the error rate must be minimum. Next, for this R squared, we are saying that how much determination you are making it. How much among the total variation, how much variation you are explained in your model. That is the only thing explained in R squared. Total variation is there. how much variation you are explained. But you cannot say 100% explanation is explained when this equation. It is practically impossible. Always there is a error is there that you can go for further prediction. That is what I am saying as the next level, that is R squared, that you can explain in the next slide what we call this a mean sum of errors. So here you can see the temperature or catalyst and the viscosity, and then we are estimating the equations where we are calculating the error that you can understand by means of this R squared. So here I am saying that 89% of the variability has to be explained. So now R squared is the prediction. That R, what we are call it earlier, we are saying with respect to from the model I am explained. But R squared is used for estimation towards the future. It means 89%, 93% is with respect to the current data. 89 with respect to future data. It means you are estimated using this equation. If you estimate anything, then 89% of the variation has been explained. That is the meaning of R square prediction. Next comes optimization. The optimization part, it's a motion where majority of the literatures, I mean, going further, peoples are working out. I am explaining a simple for the purpose of optimization. Here you can see there is a time is there, temperature is there, yield is there. There are 4 set of data I am putting it. Then I am putting a plot the graph. Then I am plotting the graph. Here I can get a linear graph between these two readings. While I am saying that it is a relationship, I cannot predict further. Then I am increasing earlier 4 readings, I am increasing 2 readings, then I can understand the graph. It will be rise up and then reducing. If I am not consider this, here also, that, then that, it is like this. So in that case, I want to go in depth further. In between the values, I want to study. For that, in between the values, I am that's a part of this optimization. Going in depth into the specific. For that, we are people are go for this responsive methodology because it's 3-dimensional surface. In a surface, you can identify, you can plotting a graph where the center point is there, where you can identify whether it's increasing trend or decreasing trend. Increasing means which point it is increasing, whether x-axis, y-axis and z-axis. Simultaneously seeing that with common point centralized. In that we can go for a central composite design where there are points choosing it with respect to center point or star point or node point. This is how you are taken into account which parameters is possibility or which factors is possible. One is central composite, then central composite design. Another one is central composite inference point, in between the points, and the final point, face point. So here I can visualize these in terms of the graph for you to understand. But always it is better, central composite CCC is better compared with CCI and CCF. This is CCA and CCF is where CC is not able to execute. You can go for this. So these are all I am executed, and you can seeing the result by doing this under this CCD design. Identify where the strength is maximum at more number of runs executed. Then next one is the BBD design where cuboid shape is there instead of a single point analysis. It's the next further analysis where cuboidal shape, in the cuboidal where the individual point in the box has been chosen. Next, statistics have been applied in the different areas: engineering, business, quality control, economics, health and the social areas. Then there are different tools they are adapted: SPSS or MATLAB or the Prism aspect and the Minitab. Very easy and simple. Majority of the people are using Excel for their application. So in this total we are visualizing it. So the summary part, what I want to say is you cannot change the direction of the wind, but you can always adjust your size. That is the things where the people need to work. Every night we go for the bed, but no assure about we are wake up. So hope using the current data, execute it as much as possible in a statistical way. Thank you. Any doubt is there, you can ask.
Thank you, sir. That was a great session. Now the session is open for discussion. The participants are allowed to unmute their microphone and clarify their queries, or by sending the text message through the chat box. Is there any queries?
Sir, shall I ask a question to you?
Please, sir. Please, Anish, sir, please.
Okay. Sir, how much influence this kind of hypothesis testing involves the practical experiments like welding, like manufacturing processes? Is it audible to all?
Right. I can understand your question, sir. But all the tests you need to be compulsory, right? The testing of hypothesis, it is must. For example, if you are having a pieces and you are joining by means of two material, you are joining and say that material removal rate is less or the wear resistance is less. That's what your inference is. That you can write it as a hypothesis that there is no difference because of this particular treatment. There is no benefit because of this type of building. There is no strength improvement in this. These are all the basic hypothesis writing. That is all the hypothesis. Then alternate hypothesis, you can write it as there is a increase in the strength because of this kind of building. For that, you can do this particular test and you say that not only you are measuring the welding strength or finally you are measuring the Y response, Y yield strength or your output. But that output need to be tested and you can say that really there is a difference compared with the ordinary type of building. This welding technique is better. That you can say the hypothesis.
Sir, I am sorry to interfere to you. Sir, I am sorry to interfere because sir, I have another question. Right now, you told like that. Okay, if I am setting an hypothesis, it is as a negative one, and I am setting an alternate hypothesis as a positive one. That is okay. I got the basic understanding of these things, and okay. Thank you so much, sir.
Sir, there is another question in the chat box, sir. Sir?
Yes. That is which design is CCD is better. Because that's up to you. That is what I want to say is BBD, you can constrain, you can fixing a boundary. You can, if you are clear cut about your boundary variables and it is possible for you to control within the boundary variable, then you can go for BBD. But you cannot controllable factors up beyond certain limit, then you can go for DCC.
Sir, Nachiappan, sir, I am having another question. Shall I ask to you?
Please, sir.
Sir, how normally if I am reading a journal paper, but I didn't see this kind of null hypothesis and alternate hypothesis inside. Okay, so how I can represent these kind of things inside that? Is it valuable? If I am setting null hypothesis like null and alternate, is it we have to show inside the journal paper? Is it relevant or not?
Correct. It's a very good question. That's why I'm saying any experiment, that's what my professor Anandaraman is also saying, anything is there, you have to do validation part. You are by means of regression or you are using a modeling, you are suggesting about this is better. But what is the guarantee that this is better? Then you can go for validation. But validation, you are saying that I can check with respect to theoretical and experimental, both are same. But my intention or my professor point is whether it is by random or really the difference is there. For that purpose, it is compulsory. You have to prepare the hypothesis, then you have to test it, then you can say that statistically you have to say that this concept what my experiment is valid. It's a significant difference is there.
Sir, one more question.
Yes, sir.
Sir, if I am iterating by using some optimization software like MATLAB and some other Python or extra, I'm optimizing, try to optimizing. So I need a lot of data, isn't it? So that values I am not taking from the experiment. It is a random values that is set by the system itself. So if some of the readers, those who take my paper and they consider, okay, if he done actual experiment, and so it will makes a negative impact or not.
Right. But first of all, I want to say one particular point. If you are not conducting the experiment, you are taking others' data. What is the purpose in which you are doing it? Point number one. Point number two, if you are optimizing it, it becomes ideal waste. It means there is some experiment or some condition in which data has been taken. You optimize this, what is the use of it?
No, sir, I am asking about the iteration process. Okay. If I am done a little part and the remaining values I am taking as an iteration. I done 10 experimental or 10 iterations practically. Then the remaining 1,000 times I am taking random values. Random values we can set. I think we can set in MATLAB. It is normally iterated continuously.
Okay. What you are saying about mingling of machine learning system?
Sir, machine learning, yeah,
many people are doing these similar kind of things. What the people will do is, now they are doing 3 experiments, and based on that they are putting into the system and making the machine learning using neural network, and that will be framing further experiments, and whatever be the X and whatever be the Y, based on that it will be further doing. But it is, I'm not saying this is applicable where if the data obtaining is very difficult, then other one is the quality of the initial data, initial feeding data is very important. If the data is error, then the total will be collapsed.
So, be frankly, I'm asking to you, sir. I am doing welding process in CMT and plasma arc welding. So, if I am producing a paper, okay, if I am producing a new research paper, if I am whatever the values I am getting from the experiment, that is good, or I have to show more, like system oriented values.
No. The thing is, the thing is, if you are asking me to be frank, it is better to conduct full factorial experiment. That's what I am saying. 2 power 3. That is number of factors power to the number of levels. That is where you have to. There I can put some equation in the presentation. That is a full factorial you have to conduct. Because of your practical difficulties, you are going for fractional factorials. You are reducing the number of experiments and you are presenting it. You must have some evidence that why you go for fractional factorial. Then among that, whether you are reducing the number of experiments means there is a clear-cut statistical evidence is required in order to execute for reducing the number of experiments. Practically easy to say, conduct full factorial. But when you are presenting in a paper, if it is go to a statistician, known person, he can immediately ask why you are choosing this particular design, why you are going for fractional factorial design. In that, why you are particular, that you must have statistical evidence towards establishing this. Maybe the literature reviews or practical explanations.
Sir, sorry to say, I am not getting your points exactly. What I am asking is, if I am showing the right experimental values, experimental parameters like temperature, pressure, whatever the external influences over the system, that I have to show in the paper. That I will show surely. Then,
Yes. I can understand your point. That is, you can put it, you can use the same values, or sometimes for your exam, for your understanding, I'm saying there are some cases where we cannot give the direct values. If you go for an industry, they cannot give the real output. For example, cement factory, we are already tested the strength. What we are doing is we are converted this input variable as a categorical variable plus minus higher lower. Then we are doing this instrument also.
Okay, sir. That means, sir, you're saying if I'm having set of values, what is the minimum and what is the maximum? I have to show like that.
Correct.
Okay. Thank you so much, sir. Nachiappan, sir. Lot of thanks from our side. Okay.
So I think this is Anish Raj has inquired what is called as a categorical variable. What we call is a quantitative variable we are obtained from the equipment what we are measured, or we can tell it is a categorical variables. For this, if he is interested, I will show one particular videos at the end. Anything is there, any question is there, I can solve it, then I can go for that.
Sir, there are no questions in the chat box, sir. Shall we close the session, sir?
Just only one particular video because of Anish. I want to show one particular video, then we can finish up.
Okay.
Sorry to disturb for the others because he has
Okay, sir.
inquired for the categorical variables and then quantitative variables. For that, we have to choose which particular test. If it is combination is there, if you go for categorical variables and combined variables, it is must for us to understand which particular things. For that, I will explain this. One particular show video is there so that you can understand that.
Welcome to Unfold Data Science, friends. My name is Aman. These tests, T-test, Chai, ANOVA. What kind of test to use when? And of course, the significance of p-value in all these tests. After that, we will try to fill these boxes here. So what these boxes are about? So categorical versus categorical variable, what kind of test? Categorical versus continuous variable, what kind of test? So these boxes we will try to fill out with the help of a sample data. Let's talk about this data. So I've created a simple data here. I have a gender column, I have a marks column, and I have a subject column. Imagine this is a class data, a student's data, okay? So we have gender, marks, and subject, okay? To start with, what is one sample versus two sample test? Before even going into that, I want you to write me in comment, what do you mean by sampling actually? So tomorrow, if somebody asks you in an interview, what is sampling? What would be your answer? Just write me in comment, okay? I want to see what is your understanding of sample. 3 columns here, right? Let us consider we have to do some analysis on this particular column, gender column. So what kind of analysis can we do on this one column I'm talking about, one sample, okay? Means one column. So we can do a, percentage distribution analysis. For example, if male is more or female is more. Similarly, we can do if we take example of a numerical column, we can say something like mean is above this or mean is below this. For example, I take a number 81 and I make a statement saying mean is above 81. That is my null hypothesis. My alternate hypothesis will be mean is not above 81. Those kind of analysis, when you take into consideration only one sample. So previously we were considering only categorical column. Now we are considering only numerical column. These kind of analysis or test is known as one sample test. Now talking of categorical and numerical, if some of you are having little doubt on what are categorical and continuous variable, continuous variables are all the variables in your data that can be counted or measured. I'm repeating it again. Continuous variables are the variables in your data that can be counted or measured. For example, what is your height, what is your weight, how many students were present in the class, these kind of variables. On the other hand, categorical variables are the variables which cannot be counted or measured. They can have specific values. For example, gender, city, color, these kind of things in your data. Okay. So any type of test that you do on one sample is known as one sample test. The examples which we took, mean is above a number or below a number. That can be done using something known as t-test. Okay. One sample t-test I'm talking about here. Here I was talking about the proportion. This can be done about one sample proportion test using one sample proportion test. These things are known as one sample test. But in data analytics, we do not limit ourselves to one sample only. Many a times we need to do different columns analysis, right? So we need to see how a column is dependent on other column, or we need to do some hypothesis validation on how the columns are interdependent. Let us take the example one by one of something known as two sample. Two sample means two variables you are taking, for example. Now, what happens if out of those two variables, both are continuous in nature? Both are continuous, okay? So this is simplest one. All of you know something known as correlation. Correlation is a measure of strength between two continuous variables, okay? So continuous to continuous, we can write here CORR, correlation, okay? This is also commonly known as Pearson correlation. The range of this number is between -1 to +1. More it is towards -1 or +1, the magnitude wise, the higher the correlation. Okay, this is about two continuous variables. Now comes what is the use of a t-test. So we spoke about one sample t-test when we try to test if the mean is below a number or mean is above a number. Now let us consider a two sample t-test using t. How we do that is, let us say there are males and females both in this class, right? I make a statement like male's average marks is higher than female's average mark. Just a null hypothesis. I was discussing about null hypothesis in my last video. Just a null hypothesis. Male's average marks is above female's average marks. Now we need to validate this hypothesis using this data. And what test we will use? When there is one categorical variable and one continuous variable, and you have just two classes in your categorical variable. This is very important, guys. If we have just two classes in your categorical variable and you have one continuous variable and you need to compare that, then we go for something known as t-test. So categorical continuous two sample t-test, not one sample, two sample t-test. But there will be cases when the number of categories in this will increase. So two sample t-test is applicable only when you have two categories. What if there is a third category? In that case, you go something known as ANOVA. Okay? There might be cases where you need to see the correlation, or you need to see the association between two categorical variables. For example, one categorical variable is gender, other categorical variable is subject. Can I make a statement like all the subject distribution, I mean to say the count of male in subject A, count of female in subject B, count of male in subject A, are all these numbers same, which means the distribution is equal or distribution is unequal. So the null hypothesis here will be the distribution of gender and subject are equal. The alternate hypothesis will be it will not be equal, there is some impact of gender on the subject. You can make a generic assumption like there are less women in mathematics and more men in mathematics. To test that using data, when you have two categorical variables, you go for something known as chi-square. Okay, chi-square. Now chi-square is the base for many advanced, testing techniques as well. I will discuss those in my upcoming videos. But chi-square is the basic technique when you have two categorical variables and you want to test your hypothesis that is there an impact of one category on another? Are males taking more of subject A or females are taking less of subject B, something like that. General assumption is all are taking in equal proportion. That is about chi-square test. So ANOVA and t-test, you understood the difference. Chi-square, you understood the difference. Now what is this box? This box is about continuous to categorical. Okay, so there is one continuous column, for example marks, and there is another subject. So all of us know that when your target is a categorical variable, think it from model building point of view. When your target is a categorical variable, your independent is a continuous variable, you can do something known as logistic regression, right? Logistic regression.
Right. Is it clear? Right. Any other doubt is there?
Yeah, sir, I saw your presentation, but something is there. Okay, but we I am doing the PhD program, so I know this research methodology things. Then also this video shows the chi-square test are analyzing two variables like men and woman. These kind of things are they are doing. Okay, and how we can according to that, if I'm taking welding program, sir, you know very well, lot of parameters, dependent variables and dependent variables are lot of there are there. So which one is very suitable for that process?
No, if you are going for observed and expected, better you go for chi-square test is enough.
So if I am taking the dependent variable as a material and independent variable as temperature, and some of the independent variables are there, pressure or something is there, then how can I analyze and how can I set the things?
Technically, whether it's independent variable or a dependent variable, the researcher can finalize this independent variable or dependent variable. You can finalize that. Then if framing the design, you can send it to me by mail. I will suggest which test is suitable for that particular area.
Sir, I don't know, because this is a management paper. I don't know how we can incorporate these things into research.
I am also belonging to management purpose industry.
Anish, sorry for the interruption, Anish.
Okay, sir. Okay, Rajkumar, sir. Yeah. Okay.
Yeah, I have given Dr. Nachiappan number. You can directly contact to him. So almost the time is 5:30.
Okay, sir. I can understand your. I can understand the situation.
So we have to start tomorrow function also.
Okay. Sorry for all. Okay.
Yeah, because only 30 participants are there.
Okay. Because if you provide
we have to close it today.
Yeah, Rajkumar, if you provide somewhat time for some doubt clear.
Yeah, no.
Okay.
I will give my lecture is almost somewhat advanced for this Dr. Nachiappan lecture. So maybe he has given a basic idea about the DOE and RSM everything. So I have given for the specific application of DOE and RSM in detail in my lecture. You don't worry. So we have discussed on my lecture. Okay.
Okay. Thank you so much.
So can you send me PPT, sir? PPT. Can we get a PPT for all the session today?
So yeah, all the PPTs we will share you. You don't worry. So and also the lecture videos also we have to post it in your maybe in. You don't worry.
Because every day if we go through it, then it will be easy to recollect and our cumulative finding difficult. So then and there I can once again revise it today. Some can go through it.
Okay. Anyhow, thank you for Dr. Nachiappan for your wonderful lecture on today. So maybe we have to utilize for the somewhat in different occasions. Thanks for your I think very informative lecture. Thank you, Dr. Nachiappan, sir.
Thank you.
So maybe today we will close it today. So tomorrow morning we will start 9 a.m. Maybe NIT Pros has given a lecture on wire arc additive manufacturing. We'll meet tomorrow morning session. Thank you, one and all.
Sir.
Thank you.
Thank you, sir.